I think it's recording. Hi everyone, we're gonna get started now. Unfortunately, we couldn't get the microphone to work for some reason, so you're just gonna have to listen very carefully to the sound of my voice. So yeah, welcome everybody to our FINCH Critical Design Review, or the big closing design review of summer 2023. Thanks everyone who was able to make it. So just a little bit about, I guess, our team. If this is your first design review with us. We are the University of Toronto Aerospace Team Space Systems Division, fully undergraduate student-led and funded aerospace design team. Our little shtick, I guess, is we design, build, and launch 3U CubeSats with scientific payloads. So a quick overview of our missions. So our first mission, Heron, which is a radio comms mission, actually just got packed up and shipped off to our launch provider the day before yesterday. And we'll be launching this fall. So that's exciting. And in our current mission that we're talking to you today about, FINCH, its payload will be a hyperspectral remote sensing imager, set to launch in a couple of years, hopefully. So before we begin, just a bit of recognition for all of our advisors. A lot of these organizations really helped us out with giving us access to different softwares and components and things like that that otherwise would have been hard for us to access. So thank you very much, whether you're here with us today or watching this later in the recording. So my name's Rosalind, by the way. I am the outgoing director of space systems and also the mission science lead for the FINCH mission. So I'll be starting off by, also here's a bit of an agenda for today in case there's just one specific one that you want to stay for and then, run to something else. And also make sure that, wait, what is that?
That's like the Zoom.
Yeah, okay. If you're not on that already, that's how you join the Zoom. Okay, so I'm going to be starting things off with a little bit about our scientific objectives for FINCH before we jump right into all the different engineering subsystems. So like I mentioned before, the FINCH mission overview is we're going to be imaging over an agricultural test site in Manitoba called Rutherford Farms. And the objective of the satellite is to collect data in the form of hyperspectral data cubes so that each particular spatial coordinate of the image that we capture has a unique absorption spectrum that we can then analyze. So just very, very quickly, the scientific experiment that we're hoping to be able to achieve is called spectral mixture analysis. Basically, it's a method of using hyperspectral data in order to measure the different compositions of each pixel in the image in order to assist in an agricultural technique called crop residue farming. Yeah. But I won't go into that too much. If you have questions about this method, I'm happy to answer questions about that after. So we also hope to supplement our satellite data with ground truth validation to see how the compositions that we return with our data of the different fields in the site match up with what we actually measure from the ground. And additionally, we're also looking into collecting some supplementary reference data using the Nmap satellite, which is like a current, established hyperspectral imager currently. So just in case anything happens to go wrong with, FINCH imaging, our folks that are collecting ground data will still have an additional source to reference. And if FINCH data does go correctly, we'll have an additional source of data to reference. So either way, it's a win-win. So a bit of a summary, I guess, of our mission objectives. One, we want to take images of data cubes of our imaging site with a hyperspectral sensor. We want to sort of calculate the composition of the fields using spectral mixture analysis using our data. And then third, we want to compare what our satellite returns with ground truth validation as sort of a technological demonstration of this method with our form factor. So yeah, a little bit about the different levels of mission success. This is a very ambitious mission for a student team and of our form factor. So it's sort of like staggered levels of if we're able to succeed in just taking and downlinking an image, that in itself will be a huge measure of success already. But just building on top of that, like each additional level of success we're able to achieve is, one step closer to achieving our most ambitious level of performing the experiment, I suppose. So our second level of mission success, for instance, would be to succeed in not only taking and downlinking an image, but also of actually having hit the target imaging site that we were going for. If we were able to do that, the next level would be to actually succeed in qualitatively being able to identify distinct fields in the image. And if we're able to do that, the next level of success would be to actually be able to perform the experiment of spectral unmixing on the data that we get. And I guess furthermore, if we're able to do it once, we'd like to be able to do it several times successfully in order to expand our data set. So a little bit about the background for some of our scientific requirements. So for instance, regarding our spatial resolution of the sensor, something that was driving that from sort of the science end was we needed fields to be much larger than our spatial resolution, or from the other direction, I guess, we needed our spatial resolution to be much finer than the size of the individual fields. So the best compromise we're able to land on is to aim for a spatial resolution of about 90 meters or so, with fields that are about 800 by 800 meters. And this is also just sort of a summary of some other scientific requirements that have been imposed on the rest of the team. For instance, like the spatial resolution that I mentioned, the spectral resolution of hopefully less than 10 nanometers. The spectral range we're going for is the shortwave infrared, so as close as we can get to the range of 900 to 1700 nanometers. Signal to noise, and of course, temporal resolution. So we're aiming for a revisit time of at least twice a month, or as often as possible. So that's a quick overview of the scientific mission. I guess we've got, I have a lot of time to spare because I was really worried about going overtime. So I guess I shortened it a little bit too much, so that we've got a lot of time for questions for me if anyone has any. Yes?
Is the temporal resolution of twice a month based on the orbit you guys have chosen, or is that like availability of checking the same site, or is that a choice on top of that?
So this particular, I guess, requirement is sort of just based on how much data would be nice to get. I guess just based on also considering our other, campaign to get ground truth data, and also supplementing the data with synchronously with another satellite. So that's just what would be nice to have on a science perspective. Of course, there's the other side of the constraint of how often we're actually able to, revisit within the constraints of our orbit. So perhaps this would be more frequent if, we revisited it more often. Does that make sense? Yes.
Your data, are you processing the data on the ground? Or
yes. Yeah, we're processing the data on the ground. And you'll hear more from our data processing team, I think, near the end of yeah. If you're able to stick it out, you get to hear more about the data processing pipeline.
Excuse me, room 1130. Did you call?
Hi. Oh yes. So we have AV for today, but we noticed the microphone is not working.
Which microphone? The podium microphone?
The podium microphone, yes.
Okay, and you unmuted it in the volume tab there?
Yes. Yes, it is unmuted. So I just don't know why it's not working.
Okay, just one moment, please.
Thanks.
And sorry, room 1130. Are you getting anything from the wireless microphone?
The wireless microphone. What is that?
There should be a wireless microphone inside the podium. Just at about waist level, there is a sort of kind of a hutch.
Is it the?
Press the unlock microphone cabinet on the
it's
touch
got a
screen there.
keyboard
it should
in it.
unlock the cabinet there.
It's
Is it?
This
Oh,
one.
wait. What? You know what? Can everybody hear me fine, just like without the microphone?
Yeah.
Okay, you know what? That's all right. Thank you, sir. I think we'll manage for today.
No problem.
Sorry about that. Par for the course. Anyone else have any questions for me? If
So
not,
you've got a question online.
oh, we have a question online. Okay. The question is: the tech demo spectral mixture analysis, or doing hyperspectral imaging with the CubeSat, or is it both? I would say it is both. So the entire, I guess, technological demonstration we're trying to do is to use a hyperspectral imaging CubeSat to see if we can get good enough data to perform a demonstration of spectral mixture analysis, if that makes sense. But in case we're not actually able to, fully achieve the level of data that would allow us to do a good job with the unmixing, that's why we have the staggered sort of levels of mission success, if that makes sense to whoever asked the question. Aiden Miles raises it. Oh my gosh, hi, how are you?
Long time no see, Rosie. How's it going? Nice presentation. I just had a quick question about the SNR requirement that I see on the screen.
Yeah.
What's the basis of the SNR equaling 30 as your
I think that was just from some literature review of some like papers we found about similar like hyperspectral data, SNR experiments. If you want, I can go back through like our like research from way back and see if I can find it again. I think it's cited in like the FINCH paper we wrote a while ago. But yeah, it was just based on
Sure.
like a literature review.
Yeah. I just that's fine. Just because you have like spatial resolution and spectral resolution have been kind of I suppose relaxed over time.
Yeah.
Uh, Perhaps the SNR becomes really important for getting good data. So I just wanted to make sure that whatever you were using as your SNR requirement had some good foundation. But literature reviews are great. So yeah,
Great, thank you. Like that's a good point, and maybe worth going back to double checking if we've got time. Yes.
I guess kind of maybe following on to that a little bit. I notice you have like a couple of like or as small as possible or as wide as possible on those. Do you ever is there any situation where you might have to trade against like getting performance improvement in any one of those four categories, and is any one more important than another? Like if you can increase the spatial resolution at the expense of the spectral range, is that something you're able to do, or
Yeah, so that's definitely like an ongoing discussion. It definitely applies. There's definitely a lot of trade-offs going on in terms of resolution. It's very precarious in terms of like, for instance, the volume we're able to allocate to the actual optical components in the imager, and that like directly impacts, for instance, our spatial resolution. I would say at the current stage of the mission right now, like at the current like stage of design, the most important thing is to preserve as much of the spatial resolution as we can. The nature of this experiment means that the spectral resolution can be a bit more forgiving. So I would say that's the most important aspect right now is in the trade-offs is to try and preserve as much of the spatial resolution as possible. Oh, Shiki has your hand up. Oh my gosh, how are you?
Hello, hi everyone. Speaking of spectral resolution, and you mentioning that it's a bit more forgiving in this case, what's the information density across that fairly wide spectral range, and specifically of like the types of spectra that you might be expecting over like croplands? And have you looked into how that influences the spectral resolution requirement?
So I guess the difference between a mission about spectral and mixing and some of the previous missions the science team had looked into in the past that involve more specific absorption features is that this method doesn't actually really depend on any one specific absorption feature. It's more so like the overall differences in absorption patterns across the entire band for each different, I guess, component or like end member. So for instance, one soil type versus another soil type, or like one crop type versus another crop type would have just overall differences in its absorption that sort of the algorithm is able to pick out. And it's actually achieved some level of success already, even just using like multispectral data, which is why anything like approaching hyperspectral data with like a lot more bands is expected to perform a lot better. But the requirement is like not as stringent as like say imaging like a molecule in the atmosphere where it needs to be really, really precise because you're looking at like a specific feature. Did that answer?
Right. Yeah, no, I have a quick follow-up, which is, from my understanding of spectral mixture analysis, the more different the spectra of the end members are, the more accuracy you'll have on mixing them. Have you looked into how distinct the spectra of the different end members you expect to see over these farmlands are, and from that, sort of how much you can distinguish the different end members in these spectra?
So we're actually having an ongoing discussion with some of the folks that are helping us collect ground truth data, as well as like collecting some like additional reference data. And something that they're looking to do this coming fall, hopefully, is to actually use I think drone data to collect some preliminary like spectral data of the different end members as a start to start putting together like an end member library so that we can actually start looking into that a bit more. And then I don't know exactly how much control we'll have over deciding which which crops we want planted in which fields. That will sort of be like an ongoing discussion with the imaging site itself. But yeah, it's being looked into in that way, if that makes sense.
That's cool. It looks like you have some cool collaborations going.
Yeah. Okay, we've got two more minutes for questions for me, probably like 1.5 minutes. So 90 more seconds for anyone to think of and ask me a question. Yes?
Is your spatial resolution at all limited by XC or
oh, yes.
optics, or is it, and what is like your data capture time? Like how long is your exposure time?
That I don't know. That might be a question for someone more on like the optics team. I don't know about that specifically, unfortunately. Does anyone here know? Yeah, go ahead.
By data capture time, like how long?
Yeah, like what's your exposure time with the camera?
The
data
takes
and
around like 10 seconds.
about 10 seconds.
Yeah. I can answer in terms of planning accuracy, that's like yes, but yeah,
is the capture time a problem that you have to correct temporally, or the position as like smear? You need to, is 10 seconds long enough that like you have to correct for like a smear of the image, because over time your data is going to be like the image looks different from the perspective.
So we'll talk more about this at the systems presentation, but we're leveraging a Fishburne acquisition method. So yes, pixel smear is a problem that we're dealing with, but we don't take one full frame picture for 10 seconds. It's more like we take ribbons of pictures over the course of 10 seconds across a track.
Okay, we have a message from the chat. Can people shout a bit more if they're speaking from across the room from the laptop? Okay, so I guess what we'll do going forward is we'll repeat the question at the podium for anyone who asks a question. Sorry about that. In the interest of time, though, I think we do have to move on to the next section of this thing. Oh, I was supposed to have it on that slide. Never mind. Okay, I'm going to pass it off to our wonderful chief systems engineer for the systems part. Thank you.
Okay, all right, well, hello, I'm David Moranto. I'm the Chief Systems Engineer for the FINCH mission, which means that I'm responsible for the systems level design, integration, and testing of the spacecraft. I got a lot to get through, so I'll move swiftly. But yeah, let's jump right in. Okay, this is our current roster of system leads. I'm extremely honored to be driving our collective passion project alongside this incredible team. Each of the individuals you see listed here and their teams have been honestly instrumental in driving the FINCH mission forward. So big shout out to the technical leads, past and present, who have gotten us to this point. Okay, let's take a look at what's in store for the systems session. I'll start off by presenting the engineering frameworks we've adopted on space systems to give you a good sort of background understanding as to how we operate as a team. Then we'll go over the roadmap. I'll present the requirements model driving the design of the spacecraft. We will take a look at the architecture we've come up with to satisfy the requirements. Then I'll showcase the artifacts we've produced to arrive at that particular architecture. And finally, we'll close with some next steps. So again, feel free to post questions in the chat as they come up, or raise your hand during the Q&A. Okay, allow me to introduce you to FINCH. FINCH is a 3U plus CubeSat carrying a novel hyperspectral imaging payload, of course designed to conduct crop residue mapping over Canada. The plus in 3U plus is because we're leveraging the additional tuna can space. That's that top cylinder there, provided by CubeSat design specification for our ADCS module. As you'll see from the requirements model, and as we touched on already, one of the most important technical challenges we have to solve as an imaging mission is achieving the high degree of pointing accuracy required. So we're leaning heavily on performance ADCS and star tracker modules to accomplish this. Leveraging the tuna can volume is therefore necessary for us to accommodate these performant but larger systems. This is a snapshot of our current team structure. We have 5 mission cores and their associated systems. I'll talk about some notable changes that happened this year. So in the past, we had a dedicated payload system. Now that responsibility of the payload AIT, that's assembly, integration, and testing, is shared between optics, payload mechanical, and systems. What else? ADCS transitioned into more of a systems level integration and testing role now that their component selection is complete. And their focus has shifted to building up our ADCS test bench, which we'll talk about today. You'll notice that this diagram has no notion of a power hierarchy. While our responsibilities as technical leads vary, of course, in terms of breadth and depth, and our level of technical experience differs between our respective fields, we of course value each other's opinions with equal weight. So that's the kind of culture that we've nurtured on space systems. And of course, our team structure will continue to evolve to best suit our needs as we migrate closer to AIT in phase D. Okay, now I'll talk about the systems frameworks in which we operate. We follow the standard NASA mission program phases. So phase C, phase D, etc. But within that, we operate in an agile-inspired approach to engineering design and project management. So basically, that just means we try to embrace iterative design wherever we can with tight feedback loops, more so than in a traditional waterfall framework. The reason we've adopted this approach this year is because of the success not only we've seen in industry, but it also aligns well with our value of continuous growth and improvement. So for a team of young engineers who are always learning, this is key for us. We have 3 levels of granularity to our project management framework. These are epics, stories, and chapters. Epics are one-to-one with the NASA mission phases, so phase C, phase D. Epics themselves are composed of stories. Stories are typically large projects which are themselves composed of chapters, but they run on the order of about a school semester. And chapters are smaller chunks of work that can be tackled within a few weeks. We'll see examples of those in the following sections. So we rolled out this framework over the past year in response to a need for better task tracking at both the individual's level and the team level. And honestly, we've seen great improvements in terms of inter-team project coordination, task tracking, team scalability, project ownership, and also our ability to plan with longer time horizons. So it's been working out for us. Okay, let's take a look at our roadmap, see where we are, where we've been, where we're going. These are the epics for the FINCH mission. Like I said, we're currently in phase C, which is concerned with the detailed design of the spacecraft and all of its primary systems. We've been in this phase since April 1st, 2022, and we're expecting to complete a semester from now for a total duration of 21 months, after which we transition to phase D. So in phase D, we move from design into integration. We expect phase D to begin in January of 2024-ish, so again, 1 semester from now, dependent, of course, on the kind of feedback that we receive today, and our progress on critical aspects of the design over the fall semester. One of our overarching team goals as a team has been to accelerate the rate at which we complete missions, to give members the opportunity to experience the full mission development cycle, basically, within their undergraduate term. That's 4 years, while continuing to uphold the culture that prioritizes member learning and personal growth. And to accomplish this, we're heavily leveraging the lessons learned from Heron. That's our last mission. We're applying ways to operate more effectively as a team through well-defined project management frameworks like the one I showed you, better documentation practices, better onboarding processes, and leveraging commercial off-the-shelf components where possible. So Heron, our previous mission, will have taken about 10 years from conception to launch. Went through Heron Mark 2 and Mark 1 and Mark 2. We are targeting a spacecraft readiness date of September 1st, 2025 for Finch. If we can meet that milestone, we have taken 6 years from conception to launch, which would be an amazing achievement and improvement as a whole. Okay, so these are the stories that we took on this past year. The 2022 fall semester marked an important pivot point in our approach to design. So the team made the decision to start leveraging commercial off-the-shelf components for major spacecraft systems on the basis of accelerating the mission timeline and increasing the chance of mission success. So with the trade-off, of course, being increased cost of the spacecraft and potentially reduced member exposure to the design of these systems. We deemed this at the time to be an acceptable trade. So notably, the ADCS module and RF module are now off the shelf. This is also around the time that we revamped our product lifecycle management. And then in December, that's that deorbit handling story. In December, rumors surfaced that the FCC might drop our deorbit requirement from 25 years down to 5. And so we launched an investigation into the regulations and ran orbital simulations. I'll talk about the results of that in a second. Following that, we revamped our spacecraft stack-up based on our new off-the-shelf components to simplify the assembly and integration. And now the team is at a point where the groundwork for end-to-end structural thermal optical performance analysis, that's STOP analysis, can begin. So we've been defining workflows, coordinating work across thermal, mechanical, payload mechanical, and optics for that. And looking ahead, these are the stories we've planned out so far for Phase D. We expect we may be able to conduct soft stack and flat stat development in parallel, depending on where the teams are at, as well as field testing and operations testing in parallel. So field testing, this is where it gets really fun. Field testing will involve verifying payload level requirements by conducting flyovers over crop fields in Ontario using a drone. Hopefully they'll carry the payload. This will allow us to test our data acquisition workflow end-to-end, including data processing. Operations testing will leverage the ADCS test bench that ADCS is graciously building for us to conduct modes of operations testing in the lab. And then finally, protoflight testing will involve TVAC, of course, and vibration testing. The dates shown here aren't truly yet representative of Phase D, so keep that in mind. Okay, let's go over the requirements model for Finch. Requirements, of course, drive all we do on space systems. So these are the requirements at the spacecraft level. Our launch service provider requirements are under NDA, so I'm not showing them here, but this is a lot to digest, so let's dive into a few of these interesting ones. So the Finch spacecraft autonomy requirement defines a need for level 2 autonomy as defined in the table. So Finch must be able to execute pre-planned, ground-defined mission operations using an onboard scheduler. On top of that, it must be able to execute event-based autonomous operations, particularly in the case where the satellite experiences a fault. It needs to execute corrective actions to survive. The rationale there is that as a student team, our mission control operators will not have the ability to continuously monitor the spacecraft from the ground and respond in the case something has gone wrong. So during exam seasons, you're looking at an absence of ground control for up to a month. And so we need to be confident that when we leave for a month, the spacecraft will still be alive and well when we get back. In exchange for a generous discount to our ADCS module, the vendor has asked us to supply them with the performance data over all ADCS modes for the duration of an orbit. So this is something that is driving our telemetry and operational requirements. It means that we must be able to command the spacecraft to enter each of these modes manually. And a child of that particular requirement is the Finch spacecraft command list requirement, which we're building on currently, defines the commands the spacecraft must be able to interpret and execute. Commands might be real-time or scheduled. These include scheduling of image acquisition, remote programming, firmware resets, setting camera configuration, requesting telemetry, and of course setting the ADCS mode. We have requirements that state we must be able to conduct remote image upgrades, which firmware we'll talk about later. And now we'll talk about the architecture for the spacecraft. Of course, we're designing this architecture to satisfy those requirements and more. Okay, so this is FINCH at a very high level. The spacecraft is generally split into two regions, the spacecraft bus and the payload. ADCS and RF modules, like I said, are COTS, commercial off the shelf. Those two modules in particular interface to the spacecraft bus via OBC, whereas OBC, EPS, and payload will interface through a shared data and power bus. This was necessary because our choice of off-the-shelf components do not both have PC104 standard connector that would have enabled them to be part of the stack. The payload controller is responsible for compressing the hyperspectral data cubes that we acquire, which are fairly large in data. You're looking at data on the order of several hundred megabytes per acquisition. The optical system is going to leverage novel components to enable high efficiency diffraction in the SWIR spectrum. Again, that's 900 to 1700 nanometers within a tight form factor and with a linear optical axis. We have two places for data storage on board. That's OBC for telemetry and the payload controller for the actual image storage. What else? At the top right there, mission operations is building us a UTAP mission control center that we can leverage across missions moving forward. And of course, our data acquisition and science teams will be able to pull that data down from the mission control center's local database eventually for processing. This is a diagram of the FINCH stack up to relative scale. All the major spacecraft systems that you see here are in line to streamline the mechanical design and assembly of the spacecraft. We have 3 custom PCBs. That's OBC, the onboard computer, the EPS, electrical power system, and payload controller. The ADCS module makes use, like I said, of the tuna can envelope at the very top there. That's above the plus Z face to provide the payload as much volume as possible. The payload sensor is the FLIR Tau SWIR. That's a 640 by 512 pixel InGaAs sensor. We had previously designed the battery module placement to be alongside the payload in that same optics volume. We deem this to be a violation of the singular responsibility principle. If the payload had blown up in terms of the required volume allotment, the battery design would have been in jeopardy. So this stack design, we think, yields better separation of concerns. That's why we pursued it between the spacecraft bus and the payload. Okay, let's take a look at some of an assortment of the prototypes, test plans, analyses that myself and the team have been working on to arrive at the architecture. This is the FINCH test harness. So the test harness is being designed to enable us to conduct end-to-end functional testing of the spacecraft in its soft stack and hard stack configurations. So again, this testing will happen in phase D, mostly. We define a couple of requirements. So it needs to be able to run automated test cases to facilitate and accelerate testing. It needs to be able to remotely program the onboard MCUs. It needs to be able to power and charge the spacecraft so we aren't waiting on the solar panels to run testing. And most of these requirements, as well as others, are based on lessons learned from Heron. What we're calling the test harness consists of both the PCB that interfaces with the spacecraft, or the systems PCB, the spacecraft umbilical, and the test script stored on the lab machine. We conducted a trade study for the selection of the controller, and we ended up choosing the ST-Link v3 mods, which can communicate via SWD, UART, and CAN. We're going to need one ST-Link per MCU that we want to be able to debug and program. So we need 2, one for OBC and one for payload. And electrical, we'll talk more about the exact makeup of the umbilical. And we're currently in the process of doing schematic design in Altium for this test harness. This is a sequence diagram that illustrates at a very high level how we expect the spacecraft to action on an image acquisition command. It's a little blurry to see, but I'll spell it out. So the workflow looks a little something like this. An operator schedules an acquisition through the Mission Control Center interface. Ground station sends the command up on contact. OBC then schedules that acquisition on reception. When the acquisition conditions are met, commands are sent to ADCS and payload to prepare for imaging. So for instance, rotate to initial attitude, cool camera to operational temperatures, that sort of thing. FLIR has an integrated thermoelectric cooler. OBC then commands the execution of the push broom slew maneuver over a target. That's the particular image acquisition method that we're using because of our choice of payload design. Once that completes, the payload begins compressing the image. Once that's done, OBC is signaled and then prepares the data for downlink. On contact, the image is downlinked with additional telemetry and metadata, and then that data is then stored in the MCC database. I alluded to this earlier. So as a result of the reduced deorbit time requirement from the FCC, which is coming in, Previously it was 25 years, now it's 5. We conducted a deorbit analysis based on Finch's current cross-sectional profile to determine how long it would take for us to deorbit. And we leveraged NASA's DAS tool for this, debris assessment tool, assuming failure of ADCS. So the question was, even in the case of ADCS failure, so random tumbling, could we still deorbit in time? And what we learned was that we actually had to impose a new requirement that said we cannot deploy any higher than 500 kilometers. Doing so lets Finch deorbit within 5 years, even if we are at the edge of our maximum mass requirement, which is 4 kilograms according to the CubeSat spec. The next step for this is to conduct higher fidelity attitude modeling that accounts for gravity gradient, solar radiation pressure, etc. That's being worked on by ADCS. Based on our updated max initial altitude, we then conducted a new investigation to compute our downlink pass metrics, and this time we leveraged FreeFlyer, which is a tool that resulted in the following metrics. So we expect to see about 1 contact pass over Toronto per day, with a mean duration of about 97 seconds, assuming we can scrap out a 45-degree ground station elevation mask horizon. In the city, that might be tough. We'll see. This analysis does not account for impediments due to weather, so we should expect a much less frequent downlink frequency. And of course, these metrics are then feeding directly back into Pay Firm's performance requirements for image compression. So how long do we have to compress between passes? And finally, the phase C completion criteria. So this is the criteria that we're using to determine whether we are ready to move into phase D. This particular selection of items was driven partly by the NASA Systems Engineering Handbook and our understanding of how to give us the best possible footing as we move into phase D. So we've set the phase transition to January 2024. That's a semester from now. We suspect that even with this additional time, we'll probably be entering phase D early by most conventions, which brings me to our next steps in terms of what we want to focus on. So to try and meet these objectives, these ambitious timeline objectives, we're going to allocate attention to 4 key projects at the systems level. So those are the FINCH flight payload design, stop analysis, 1 round of it, image compression, FDIR, and then we are also going to start coming up with descoping plans in the case that we fail to achieve the phase C criteria in time. We are also going to start writing systems level functional test plans and code that eventually will run on the FINCH test harness. And we are beginning contract renegotiation with our LSA. There's some risk associated with that right now because our LSA was bought out by another company with a different launch vehicle with, of course, different interface requirements. So this is on our radar. That's it from systems. Open the floor to any questions. Yeah, Zach.
Hey, so 2 right off the bat. First is during LS, which sounds like it's going to be most of the time by a big margin. What's data storage look like on board?
What does data storage look like on board in terms of quantity?
So in terms of image capture, assuming you've already indicated that there's going to be some level of autonomous operation, so you can send it to make certain passes and capture images. What's the maximum number of images?
Oh yes, so we have a requirement that specifies we must be able to store at least 1 image acquisition, which is on the order of 380 megabytes. Well, that's with margin. So we actually margin for 2 data cubes. Yeah.
Okay, so there's one stored on board, and then second question is sort of related to that. It goes toward the data processing side of things. Is flow diagram at a high level, blurry gives me a bit. Didn't indicate anything on the ground side other than the acquisition of that data. Is there any processing pipeline or receipt of data that is part of the nominal flow?
Yeah, Ian will talk a lot more about that data processing. Yeah.
3:40 p.m. Stick around till
that. All right, I have a question here from an anonymous participant. Is the tech demo?
That was for Rosie.
Oh, sorry. How are we obtaining this? Was that also for Rosie?
No, that was for you.
Okay. How are we obtaining scientific data during the field test? Are we providing the drone? Do we need another fuller tau STBAR? No, the intent is to use the flight components. This is still further out, so there's no solid plans for this quite yet. But I would imagine that the idea is that we would be testing using the payload data to complete the end-to-end verification for data processing. Yeah, I know there's risk with that, but we'll talk about it. We'll talk about it. Cool. Yeah, good question. Aiden, you have a question?
Yeah. So you mentioned some of the other considerations you're looking at, some of the key requirements. For the test harness, were there any considerations made for TVAC functionality?
Yes. Yeah. This is something that I don't think the requirements model currently captures. But the intent with this would be that the test harness would be compatible in the TVAC configuration as well. I know that, well, Thermal, maybe you can talk more about this later, but the umbilical has to be piped through a different set of connectors, of course, to go through the TVAC chamber and then back out. But the intent would be that we leverage the same test harness at the other end to run testing.
Cool. Is it time for another question? Do you need to proceed?
Yeah, go for it. I got 2 minutes.
Cool. For the ground station stuff you're talking about, now that you've done more development on the Heron ground station, to what degree would you think Heron is able to de-risk some of these concerns you were talking about with those downlink pass metrics that you were discussing?
Good question. So, well, I'll start by saying that we are building the FINCH ground station partly in parallel to the Heron development right now, just because we have people who are building up that knowledge that can carry it over to FINCH. So now is a good time to more convenient for us to start thinking about those designs. In terms of de-risking, I think the only risk I mentioned was not having a sufficiently high like ground mass horizon. I suspect that I'm not sure. I suspect that even in the case that we don't have sufficient time during each downlink pass, if we set up our ground station like the Heron's is over the Bain's roof, there are other options for placement. That may be a little further ways out, but that could be something we investigate. Yeah. One last question? Yeah.
Given that you mentioned you have quite limited downlink opportunities, have you designed your algorithm such that you're able to process incomplete downlinks?
You guys want to speak to that?
Yeah, I think we're sort of starting to look at the structure of how to store and accurately. So the idea is that we can hold back data that we haven't sent down to our process.
All right, well, that is time. If you have any more questions, again, we'll have a big Q&A session at the very end of the presentations. With that, I'll pass it off to optics.
Okay. Hi, everyone. We're going to start talking about optics now. I'm Abir, the optics lead, and this is the rest of the team. I have to say, thank you to everyone who's on this team. We've made a lot of progress this past year, but especially this summer, it's been very productive. And every single engineering artifact that I go through, at least one of these members has contributed to. So huge kudos to them. Also, side note, if you see a member's name on the top left of a slide, it means that member's contributed to the technical work. But yeah, so the agenda for today, we're going to be looking at our roadmap as a team. We're going to be looking at the optical payload as a whole, so our requirements model and then also our systems architecture. We're going to be breaking it down into the components, and then we're going to be talking about how we're analyzing payload performance. We're going to look at next steps in order to transition from phase C to phase D, and then there will be a portion for Q&A. So for our roadmap, I'll keep it simple. Optics basically has 3 goals for phase C. We want to have a bill of materials for our payload. We want to have an optical simulation model in ZMAX, and then we also want to have test plans for phase D. So these are our 3 main goals, and any and all decisions sort of contribute to these. Okay, so for the optical payload, let's zoom out and look at it as a whole. We can see here that this is the optical system architecture. It shows how the payload interacts with the rest of FINCH. So as you can see here, we capture light from Earth, and then that light goes into our payload. We do a little bit of light bending there, and then it goes to our camera, which is the FLIR Tau SWIR. This data, the data that's collected by the camera is processed by Payload Firmware. The temperatures of the payload and also the camera are monitored and regulated by thermal, and then Payload Mechanical is what houses all of the payload components. So what are these payload components? We have a couple of things. So you'll notice here that we have a 4-optic, which is what focuses light from the Earth onto a slit. The slit is what allows us to have spatial filtering perpendicular to our sweep direction, which was mentioned earlier. The light from this then passes through a collimator, which collimates the light into a parallel beam, which then goes through a VPH prism in order to separate the light into all of its wavelength components. And then these are focused by the focuser onto our camera. But how do we design, or in our case, source each of these components? So earlier, Rosie mentioned our scientific requirements that need to be met in order to achieve our scientific mission objective. So these are them. So we have swath, we have spatial and spectral resolution, spectral range, and then SNR. These are the main ones that we consider. So essentially, they're the bare minimum in order for our design to be considered feasible. And you'll notice that our optical requirements sort of trickle down from each of those scientific requirements. So I've color-coded it for ease. The dark gray ones represent requirements that affect the entire payload. Red represents 4-optic. Orange is for the slit. Green is for our collimator and focuser, so the relay lenses. And then purple is for our VPH prism. A couple of these requirements you might notice are undetermined. So we have beam diameter and we have slit width. For these, we're conducting trade-off analyses using trade books, and we will hopefully be determining those very soon. Okay, so we'll move on to the payload components, where we'll zoom in on each of the components. So this is just a basic drawing to illustrate what the payload's going to look like. Our volume constraints, as you can see, excluding the sensor, are 100 by 100 by 140 millimeters in the X, Y, and Z dimensions. This informed a lot of our component selection. It was a huge constraint that we had to keep in mind, and I guess we'll find out whether we met that constraint. But please note, however, that any and all component selection that I'm going to be talking about is preliminary. So this isn't even like version 0 of the payload, it's like version -1. This is very first draft of the payload. But I'm putting it out here to get feedback. So any and all questions, comments, concerns, welcome. Yeah, it's very subject to change based on the simulation results we get from ZMAX, based on, again, the feedback we get here, based on testing of our prototype build one, and any other scientific discoveries we make along the way. So another thing I should mention. So for this payload, we've been able to make preliminary selections for our 4-optic, our collimator and focuser, so our relay lenses, and then also our prism. The slit has not yet been selected because of the slit width requirement that hasn't been finalized. Okay, so for the 4-optic, we've gone with the Solo 50 by Sensors Unlimited. We had to conduct several trade-off analyses to determine the requirements for the 4-optic that were shown earlier. An example is here, where we have SNR and spatial resolution against aperture size. But a really important one that we had to consider was the focal length of the 4-optic. So originally, our requirement was 100 millimeters. But what ended up happening was that when you have a focal length that's that long, you also have a 4-optic that's very long. And because of our payload volume constraints, we knew that we would have to compromise on that in some case. But the reason that we're confident in how much we can compromise is because of something that data processing is working on, which they'll be talking about I was going to say in a bit, but like in quite a while, which is super resolution. So I'll keep it brief. The literature on super resolution says that this process can improve the resolution of our image by at least 2 times, which means that on optics end, we can compromise on our spatial resolution by that amount at a maximum. So that's what we've done here. That's why you'll notice that the EFL here is 50 and not 100. A couple of things that still need to be ironed out. We need the back focal length of this, which is quite important, which is why I said this is a preliminary selection. And then also image diameter, we're creating a trade book for that. Next, we're moving on to collimator and focuser. There's really not much to say for this. We selected Edmond Optics near-infrared spheric lenses. The diameter of the lenses helped determine the beam diameter for the beam that would go into the VPH prism, so that was important. And then we also prioritized having minimal focal length, again, because of volume constraints. Moving on to the VPH prism, we were lucky enough to have a contact from Wasatch Photonics from quite a while ago when we were working on our prototype to source the GRISM. This is our payload's only custom component thus far. And a couple of important things to note here are that the grading of the GRISM is made of fused silica, but the prism itself, the prism of the GRISM is made of sapphire. So the reason we chose sapphire was because it has a higher refractive index than fused silica, which meant that this would reduce the length of the GRISM, which was important for us. And also sapphire is a space-ready material. It's used in a lot of space applications, so we're good with that. But one of the things that we want to look into, just to finalize, is our spatial frequency. We have it currently at 600 lines per millimeter, but we know that spatial frequency and bandwidth can determine our required refractive index for the GRISM, so that's something we want to iron out before we make our final selection. Okay, so you've seen 3 of our components. Here's a diagram to show vaguely the volume allocation within the payload. Once again, everything is very preliminary, but this basically gives us confidence and hope that it is possible to fit a payload within this volume, which is good news for us. And at this point, the most important thing for us to figure out is our 4 optic, so sort of the dimensions and then also the back focal length of the 4 optic. Okay, cool. Now we'll be moving on to payload performance. So payload performance is determined in 2 main ways. We have experimental analysis, and then we have optical simulations. So for experimental analysis, it consists of several steps. First of all, we need to be able to integrate our camera with the optical payload, which is something we're currently working on. Secondly, we're going to be looking at a spectrum alignment test to make sure that the wavelengths hit the sensor where they're supposed to hit them. Next, we have our stray light test. We have a modulation transfer function, or MTF test, and then we have an SNR test. So these are going to be conducted for our prototype FINCH eye, but then also our main space-ready FINCH eye. But I'm not going to be going into too much detail for that just because of time. But I will be going into detail for optical simulations. So the optical simulations are mainly going to be happening in ZMAX, which is our simulation software. We're going to be conducting what's known as stop analysis, which I'll talk about in a second. And the requirements for that are that we create an optimized model of the FINCH eye in ZMAX. And then we need to conduct different analyses with different performance metrics to determine how well our payload performs in different conditions. And then there's also tolerance analysis, which a couple of our members are working on. Okay, so for stop analysis, STOP stands for Structural, Thermal, Optical Performance. You see 3 keywords there: structure, thermal, and optical. So this is an intersystem project. There are 3 systems involved here: payload mechanical, thermal, and optics. I've color-coded it here to match the diagram, which I totally did not steal from SIGFIT, so that it's easier for y'all to understand. But basically the goal here is to model changes in optical system components because of the external thermal or structural loading and stress in order to see how these changes impact our optical system performance. So this diagram here, this flowchart, determines our workflow and our task division. What effectively happens is that thermal provides a thermal model that it created in NX to Payload Mechanical. Payload Mechanical also does structural analysis in Nastran NX, and it uses what thermal provided for that. And in the meantime, optics is sort of working on its optimized model of the payload, and it's conducting tolerance analysis so that Payload Mechanical can ensure that its displacements are constrained within the tolerance. And then after that, we move on to the part that's yellow, which is SIGFIT. So we run SIGFIT analysis, and the outputs of SIGFIT analysis are given to optics to work with in ZMAX. So that's like the final step, is that we have our optical analysis model, we have our outputs from SIGFIT, and then using that, we determine how well our payload performs. So Payload Mechanical and Thermal are going to be talking more about what they do in STOP analysis later on, but now we'll zoom in on what optics does. So optics is mainly involved with the SIGFIT and the Zmax portions of STOP. So we know that external loads cause structural deformation and then also refractive index changes because of stress and temperature. And we obtain these values from SIGFIT. This is then transferred into our Zmax model of the payload to see how these changes, again, impact optical performance. So the main performance metrics that we're going to be looking at least for now, are MTF and RMS wavefront error. So I guess in short, our work is threefold. We want to create an optimized model in Zmax. The very startings of which are shown up there. There are a lot of issues with that, which is why it's not a complete model, but that's somewhat what it's going to look like. The prism doesn't have a prism, it's just a diffraction grating, and then the slit's not really a slit, it's a hole. It's a work in progress. But yeah, so there's that, an optimized model in Zmax, tolerance analysis so that we can give those values to Payload Mechanical, and then SIGFIT and optical performance analysis in Zmax just to round things off. And like David said earlier, our goal is to complete at least one iteration of STOP analysis before the end of Phase C. Okay, so next steps. As we transition from Phase C to Phase D, we have a couple of things that we need to complete. We need to fill in some gaps in our requirement model. And then we need to finalize and purchase our FINCH components for the payload. We also need to complete and analyze an optimized model of the FINCH in Zmax. We need to execute tests on our prototype FINCH, and then we also need to finalize the tests that are going to be conducted on the real FINCH. And then finally, we need to complete, like I said, at least one iteration of STOP analysis. But yeah, there's quite a bit to do, but I have hope that we'll be able to get it done based on the productivity of our team thus far. Yeah, that is it for optics. I'll open the floor to questions. Oh, wow. Okay, lots of questions. One second, what's the first one? Okay, is there a backup to the 4 optics in case super resolution is not valid? That's a good question. So the 4 optic decision was one that was based on trust and a lot of literature review. Yeah, it might be worth having a backup of a 4 optic, but the question, I guess, in that case would be how would we fit it into the payload? We can't, there are some constraints that we can't sort of like go around, but we can stay as close to the requirement as possible. There is the scenario that we don't meet our spatial resolution requirement, like that's our worst case scenario. But in that case, we just have to adjust our mission objectives accordingly. But the goal right now is to meet the requirement, obviously. So yeah, there's no backup as of now, just because it wouldn't be possible to fit it in the payload. Do we have a ROM cost? What's a ROM cost for the custom GRISM?
Rough over 90.
Oh, yes. I believe it is 10 to 12K, as far as I know. Yes.
So minor thing, I've seen commercial optics fail under very rapid pressurization. As you might see from launch. You're going to want to look at that, see if they're either effective, or if you're going to do it effective yourselves, a little bit like that. Good news is it's easy to do. A small vacuum chamber, just a small pump, which is like press rates.
Yeah, so we are going to be testing our FINCH payload, the official one, in a thermal vacuum chamber. Earlier than that. Okay, gotcha.
If your optics crack or deform, you don't want to catch it at the end of the day. You want to catch it.
Got it. I'll look into that. Thank you.
Related point is any of the components of this that are off the shelf. Do you know yet if they have any legacy of use in this environment?
That's a good question. So for the 4-optic, they do have experience in space. So it does have flight heritage. For the relay lenses, they are not exactly made for space, but they do have a life based on the material. They do have a lifetime of at least a year, which is what's the goal of our mission, is for it to last at least a year. So that's all right. And the Grism, like I said, the materials are, they do work in space, and Wasatch Photonics has worked with other space companies. Yes.
What is UTAT's build space like for integrating, working with objects for space environment? They can get dirty really fast. So, do you have a clean room space available to UTAT?
That's a really good question. Yeah, so this has been an ongoing discussion, sourcing a clean room. It's shifted over time. Right now, I believe we're sourcing a clean table, which is just like a table space that's covered and there's ventilation and it's clean. But yeah, we've shifted from a clean room to a clean table. So that's what we'll be working with for now. Okay. What is the source of your structural stresses or deformations on the payload? Is this just structure preloads and stresses from assembly? Any thoughts about the impact of permanent deformations due to launch loads? Thanks. Okay, I think this is more of a question for Payload Mechanical. I think we can answer that later when Payload Mechanical presents their presentation. But thank you for the question. Any thoughts on stray light? I saw a requirement, but you don't have it mentioned further. Do you have a space for baffle or any considerations for anti-reflective coatings? Thanks again. Yeah, so we don't have a requirement for stray light just yet, but we do know that it should be related to the noise levels on the sensor. So that is something to look into. We do need a requirement 100% because we are going to be doing stray light testing, and we're also going to be conducting stray light analysis in ZMAX. As for anti-reflective coating, yeah, like when we're sourcing components, that is one of our things that we keep in mind, is that they do have anti-reflective coating in order to minimize stray light. Okay. Yes.
So just like I said, that too many questions.
Okay.
You mentioned the analysis cover a number of things, including thermal looking on the camera. And today, I guess my question is that focused on mechanical deformation of the elements of the eye? Second, does it account for noise in the infrared spectrum?
Okay, sorry, do you mind repeating your question?
Sorry, I guess two questions. Does the analysis of the FINCH eye account for deformation in the lenses of different optical components? And secondly, does it account for noise in the optical sensors and what's captured, because the craft itself is hot or can be hot and we're in operating in the infrared spectrum?
Okay, yeah. So with regards to the first part of your question, that's, again, it's part of stop analysis. That's more of what Payload Mechanical is going to be doing, which is like the stresses and the disturbances that are going to take place with the optical components because of it being in space. So yes, it is being considered in stop analysis via Nastran and then also via SIGFIT. And then for the second part of your question, in terms of noise, yes, we are taking the sensor's noise into consideration. Like I mentioned, there is an SNR requirement, and that takes into consideration the different types of noise that result from the sensor. Okay, I think those are all the questions. Oh, yes.
You mentioned using super resolution. Is that something, just for my clarity, is that something physical that you're doing with the sensor, or is that just like software processing?
It's data processing that's going to be happening on the ground. Oh yeah, sorry. So the question was, for super resolution, is that something like a physical process that you're doing, or is it something like software related, right? Yeah. And the answer is that it is data processing related. So it's an ML algorithm using code, and that's going to be done on the ground. Yeah. Okay.
But it's done on the ground, right?
It's going to be happening on the ground. Yeah. Okay, cool. I think I've taken up a lot of time. So thank you, everyone. Okay, on to mechanical.
Hello, I'm Chris, the mechanical lead. And yeah, we'll go over the structural stuff, mechanicals. This is the team. Small team, but we get by. Yeah, so what we do, we're a mechanical team, not payload mechanical, so we don't really deal with mounting the optical stuff, but we mainly deal with mounting and support and just the main structure. So mounting and support, mainly for ADCS components and electrical, the stuff like the boards. For ADCS, we have the star tracker and that tuna can. More stuff. So we're responsible for assembly. We got to make assembly plans. We got a prototype to find out how we want to route these wires. And then at the end, we need to do design validation, right? Test plans and test reports to make sure kind of everything's good to go. So we have some requirements. Mechanical requirements are quite simple. You have like mass, volume, whatever mounting requirements we have. For us, since we have our stack order, kind of mechanical needs to follow that and make sure everything is in that order. This was already shown, but just another show. And then we have other requirements, stuff that come from the launch provider. Shock requirements, the allowable like vibrations, outgassing, and stuff like that. So now we'll go over some of like the design work. So this is the assembly that we have. It is quite preliminary. Some of the components are on here. So stuff like the antennas and the deploy switch won't be on here, but the larger components are on here, and you'll be able to see kind of the internal components, the larger ones, how they're stacked up. So yeah, we'll have 3 kind of solar panels on the other sides. And then we have the cutout for the star tracker on one of the panels. This is an exploded view. So you could kind of see the stack up here. We have the payload at the bottom, followed by star tracker, the electrical stack up, and then the tuna can. One thing is that in the past, the slide's not in here. But in the past, FINCH has always had 4 panels or 6 panels, like no rails, as a main structural kind of support. But when we went over kind of a lot of component selection and a lot of parts were changing, it gave us an opportunity to decide if we want to continue with going with just panels or also add rails to our design. We decided to go with rails just because we found that using panels takes a lot more weight just because you need those panels to be wider. And although they do have less fasteners, which fasteners are weaknesses, rails, we just thought it'd be stronger due to the geometry and kind of stuff like that. Also, we found that bracket mounting, so having a separate bracket that mounts onto the 4 rails would be more effective than panel mounting, just because panel mounting, when you're mounting like one component onto one panel, you're kind of biasing the weight, and that could cause issues in the future. So we'll go over some of the specific designs. Mainly mechanical, we've been working on a lot of the electrical stuff, so we'll be going through that. So this is the model of the PC104 stack up. We have 2 of the boards. I believe they'll be the OBC and EPS boards. There is another board on this, which is the payload controller. It won't be in the stack up just due to height constraints, but it is something that we'll add probably embedded within a bracket. So on the stack up, we'll have the battery pack at the bottom. We'll have the 2 boards and then our RF module at the top. You have 2 aluminum brackets, and that'll just kind of hold these things in place. The bottom one's tapped, and the top one is just clearance. Currently, the height's 80 millimeters. It is quite tall, but the standoffs can be reduced. We just have to find out. We're just waiting on electrical for like component selection and making sure that we could reduce these standoffs. An exploded view. Yeah. Next is the battery pack. So the battery pack consists of kind of 2 brackets or housings that will come together with M2.5 screws and a nut. The main difference with this one is there'll be 2 millimeter gaskets, kind of like this, that will compress and hold the batteries in place while also maybe preventing some vibrations. The main idea was to actually kind of not have the aluminum edge on the battery. One of our constraints is because we're to avoid like high costs, we're assuming that we're just going to use kind of simple CNC machining. So it's hard to make internal fillets. So having these gaskets will mitigate some of those problems. So yeah, our next steps, mechanical team needs to finish a lot of these designs. So star tracker mounting, stuff like the deployment switch, we're gonna mount that. And then at the end, finishing up the panels and rails. After that, testing and prototyping and having our assembly. So we're gonna be 3D printing, making easy prototypes, just to kind of lay out our assembly plan, make sure everything kind of fits together, and then determine wire routing. At the end, kind of structural analysis. So we have access to NX. We'll be doing analysis on that just to make sure all of our designs won't break. Yeah, that's it. Any questions? Oh.
I noticed that I was wondering if the battery pack if you have like access to the
Yeah. So
like just say the question.
yeah. So the question is, are there going to be openings at the poles of each battery? So there are for the middle two, and it's easy to add them to the two on the outside. So yeah. Yeah.
Yeah. You mentioned launch requirements for a launch provider. Does this mission have like a selected launch vehicle, or are you guys still picking between a few? One bit based on it.
So we're in contract with Spaceflight for launch. Spaceflight was bought out by Park, who have their own launch vehicle, and it's possible they may make a switch over from a Falcon 9 to their own launch vehicle. As far as we know, Fireflies haven't taken launch yet, so there's risk there to be renegotiate their contract in terms of like, this is not what we want to out of the contract, or do we stay with them? We don't know yet. Those are ongoing conversations.
Recommendation to that would be if you can have, if you compare the requirements between the selection of the likely launch vehicles. Yeah, don't at this stage in your design, if you can design for many launch vehicles, that'll really help you.
If just reading out from the Zoom chat, has the Star Tracker cutout been given based on some analysis done for the placement to ensure that no stray light enters the Star Tracker?
Oh, in terms of that, I got the Star Tracker recently, and I just added a cutout for the assembly. So not much kind of thought has been made into that. But when we start designing the mounting for that Star Tracker, we'll definitely keep that in mind. Yeah.
There's more Zoom questions. Do you want me to keep reading them?
What is the source of your structural stresses or oh, that one's not it. Wait, I'll have to scroll down. Yeah, so the question is, PCB stack up brackets, will these be solid plates? Yeah, no, these won't be solid plates. So for now, since we don't have kind of the design finalized, I don't know the final weight that we'll have, which means that I kind of want to keep everything quite simple because it'll be easier to kind of make cutouts than try to build upon it. I don't want to just add cutouts and then find out that I added too much. So I found it would be better to just kind of have the weight that we currently have and then make cutouts to whatever I need at the end. Next question, how are the battery cell contacts connected electrically? Just make sure there's space in the housing for this.
Yeah, I think that was similar. They're connected electrically.
Yeah.
Which I can talk more about in the power presentation.
Okay, so they'll talk about it more in the power presentation. In terms of the clearance, there's quite a lot of room for the battery pack, so clearance can always be added. For now, between the batteries, there's 1 millimeter, and then from the faces of the battery to the side of the housings, there's 2 millimeters. Yeah, I think that's it. Yeah.
Is there sufficient clearance around the battery pack to be able to route cables from the payload board to EPS and also battery to EPS?
Within the battery pack.
Like just on the sides of the battery pack. Does it take up the full like 100 by 100 space, or is it smaller?
No, it's smaller. There'll be room because since I'm following kind of the standard threaded rod placement, there's a good amount of room on the sides to route wires. Yep.
Do you have any idea where your center of mass is? It's very heavy, four optics look heavy, and at the end, and just looking at the diagrams earlier, it looks like the mass distribution might cause like this here around.
Yeah, so that is a problem because the payload probably does take up most of the weight. Kind of to mitigate that, we have our ADCS module at the top, and then that stack up can always kind of how you stack it. So maybe we'll want to move the battery pack a little higher.
Just keep an eye on that.
Okay.
Balance area
All right. Thank you. Yep.
Do you have a sense of both like static misalignments and thermal deformation that could happen between the star tracker and the payload? Because that could contribute to pointing error.
Yeah, in terms of thermal, I'm not sure. That'll be probably something that the thermal team might talk about. And then again, I'll need to design the mounting, or we'll need to design the mounting. So I can't say much about that for now, but I'll keep them. Yeah.
Sorry, not to keep on, but the battery. But have you accounted for like battery swell, like fluctuations when we launch?
No, but if we have that gasket, I'm thinking it might kind of be built in to help out with that. The gasket could be larger if this, I don't think you'll saw that much, but yeah.
It's like usually like
10%.
The battery pack discussions will be had, I think.
Chris, can you just hit the questions and answers?
Oh. Yeah.
You're marking them as being answered live, not as answered. I don't know if it's
Done.
button, David.
There should be two.
Okay, well.
It's fine.
Thank you.
All right, hi everybody. So we've sort of been talking a lot about the payload and we've been talking about the structure. So now we need to talk a bit about the structure around the payload. So for those of you who don't know us or who don't know me, my name is Noah and I am the Payload Mechanical lead and I'm here today with Aaron. But I also wanted to mention that Bettina, Noreen, and Siddhartha have been extremely helpful in actually putting together these slides with us. And then the whole rest of the team has been so instrumental, especially over the past semester, in actually getting all of this work done. So what exactly do we do? It sounds pretty self-explanatory, it's in the name. We deal with the structure around the payload. So the assembly, integration, testing, design, all of that of the actual structure itself. In optics, we talked about the optical components. This is not fully up to date, but we have the four-optic, the slit, the collimator, the grism, the focuser, and the sensor. And to note that the four-optic and the sensor do not actually need a housing around them, and then all the other components do. So we deal with that. In order to do our design, we have our requirements that govern what we're actually doing, and we've sort of split this up into three core sections. We have the first section, which is about mechanical. It's sort of the mass, the volume, the actual positioning of the payload. As you saw in Chris's stack up, we are along the z-axis, so making sure that it's perfectly centered there. We have requirements on optical performance, so basically making sure that all the optics are completely aligned, that the tolerances are sufficient, that it doesn't misalign during launch or anything like that while it's experiencing acceleration and vibration. And then we have lots of testing and verification requirements, basically to ensure that it will survive. So here we have things like working with thermal in order to have sensors to be able to monitor the temperature. We have lots of different simulations in order to determine the frequency to make sure that resonance doesn't occur with the launch vehicle. We have simulations on quasi-static loading and a whole bunch of different things, basically to make sure that everything we do, that when it goes up, it will survive. As for the system architecture and sort of where PayMech is situated and what we do in particular, so we are within the payload sort of subsect. We are also within the mechanical subsect, again, pretty self-explanatory by the name. We deal a lot with optics, thermal, and mechanical. And sort of, we kind of split into two core things. We have the payload housing, and then everything within it, which includes mounting of the payload housing to each other, mounting of the optical components within the payload, and then we have the mounting of the payload to the outer structure. And then we also do simulations, making sure that it'll survive, writing an assembly plan and doing prototyping to make sure that we can actually assemble it, writing verification plans and test plans, things like that. So let's delve into the actual design a bit. So as you can see here, we've gone through a few different iterations. These are just a couple of them, and none of them on the slide here are the final one. I'll get to that in a moment. But sort of, we've gone through ideas of having essentially just like an optical bench within the satellite. We ultimately decided that the best case scenario, also the one with the most flight heritage, would be something like a tubular design where each component is sort of housed in its own little compartment. Not necessarily each component is separate, but sort of like it's encased in its own diameter, etc. And the idea of this is that it would maintain alignment of all the optical components and that it would protect the optical components, reduce the mass, reduce the volume, basically adhere to a lot of our different requirements. And so how have we actually gone about designing this? Or what are the actual components of our design in more detail? So this is the most updated model of our payload housing so far. And this is situated within the actual satellite, so you can see the rails there. And so essentially what it is we have 4 components of the payload that we deal with. So we have the camera on one side, the 4 optic on the other, and then we have what we call the primary housing, which essentially connects the 4 optic, it connects to the 4 optic and contains the slit and the collimator and the grism. And then we have a secondary housing, which connects to the camera on the left there, and that contains the focuser. Along with all of this, it's important to note it's all made out of aluminum 6061. Everything will be mounted by M2.5 and M3 screws, except for the 4 optic, which is screwed in by a C-mount, and some of the optical components within, which we'll talk about in a moment. And yeah, one other thing to note is actually we came across through a lot of our assembly processes and prototyping that we don't actually have a lot of space to actually assemble here, because the FLIR Tau has a C-mount, but the idea is we want to try to avoid C-mounts as much as possible because that would also challenge alignment and actually how we're going to be mounting it within the satellite. And so the only holes they had were to screw them in vertically through there. Now we don't have enough space here to actually have a torque wrench, and so we came up with another solution to basically remove the C-mount off the FLIR Tau and replace it with a new piece that we can actually screw in through the sides.
Okay, next we're going to talk a little bit about how we're mounting the payload to the rest of the satellite. I know we touched a little bit in Structure's presentation on this, and we were collaborating with Structures to work on this particular project. So we had a couple of iterations for our design, and we ended up with the bracket mount, but we also considered isostatic mounts. The reason for that is because through our review of literature, we saw that isostatic mounts were used for optical components quite frequently and circular components, which we have quite a bit in our design of the payload. However, ultimately, we decided that it was not the best idea because we would need multiple isostatic mounts to just mount a single part that was circular. So for example, if it was the four-optic, we would need like 3, for example, around the four-optic to be able to properly mount it. So we decided to pursue the bracket mount, which would be a singular piece, and it would just go around the component, and we could mount it to the rails that way and ensure the alignment in the z-axis. All of the axes, but specifically centered on the z-axis. In addition, we're planning to have 3 of these bracket mounts for the proper alignment of the payload and the proper mounting. However, each bracket mount will be slightly different and altered in our CAD, so we're going to be changing the inside of it depending on which structure it's going to be enclosing. In addition, we're planning to test if these mounts will hold up using Nastran and INEX to run various simulations to ensure that it does survive the flight and the orbiting. So we're also going to be talking a little bit about our assembly plan for the payload and how we're going to be mounting it. For starters, we're going to talk about how we're going to be mounting the focuser, which you see right here. This is one of our optical components that we're going to be mounting, and we have decided to pursue retaining rings, which are threaded components that go around the optical component, and you thread it in, which will ensure that the alignment stays precise and exact, and we're able to proceed with the mounting of the outer components, which is what we're aiming to do. In addition, one of the ideas that we've been pursuing for the slit and the collimator have been structures like these that you see on the left side. These are lens tube drop-in mounts, meaning that the specific optical component would go inside of that specific mount, and then we're able to drop that in to the outer enclosing, the bigger structure that we're going to be mounting. Which will allow us to keep the alignment exact and precise. And in addition, we're just able to drop in the components rather than having to manually place them every single time because they're rotationally symmetric. So we only have to ensure that they stay in place, specifically for the collimator. The slit, we've been pursuing other options in addition to this particular mount, which I will get into in the next slide. So we've been looking at different space-grade glues for the GRISM and the slit, potentially. We've discovered that there are different levels and different types of space-grade glues that have been used throughout. However, we've specifically focused our attention into exploring through the optically clear grade of the space-grade glues. This is because we don't want the glue to interfere with any of the optical components because the imaging is quite sensitive and we don't want any interference just in case. So we've dedicated our attention to this specific glue, also because it can survive the temperature of our mission, which we wanted to keep in mind. And in addition, it's classified by NASA as a low outgassing approved adhesive, which means over time, the components from the adhesive won't adhere to the other parts of the payload or the satellite and cause any kind of harm or damage to other parts, which is something we wanted to keep in mind. In terms of thermal and electrical concerns, we are not very concerned about thermal since we are using a thermal strap and different methods to pursue that, to ensure that the satellite and the payload stays within the constraints for thermal. However, we are going to be running, as we said, NX and Nastran simulations to ensure everything works smoothly and everything works fine. So if one of the glues don't work out, we can pursue other options, or we can continue iterating over our design over time.
Something that I just wanted to mention for this slide, I realized it wasn't fully updated. Sorry. Oh, it looks like we're missing a slide. That's okay. Anyway, so at the bottom of the GRISM housing, I wonder if I have a better image. You can kind of see 2 holes there. These are basically holes from the exterior that we'll be using to inject the glue in order to adhere the grism. We did have one quick comment also about ADCS microvibrations. We have another member joining us here. It's Noreen. Do you want to quickly mention?
Yeah, sure. Hello. Sorry, I'm late. I just wanted to speak a little bit about the microvibration projects that we're working here in Payload Mechanical. Essentially, in the attitude determination and control system, we have what we call a control moment gyroscope, and this is integral to the being able to control the orientation and the attitude of the satellite in space. However, the downside of this is that it can affect the payload structure in terms of microvibrations. So for this project, we had basically two main requirements. One of them being that the natural frequency of these microvibrations weren't equal to the natural frequency of the actual payload structure, and that the pointing error, which is an effect of the microvibrations, doesn't severely affect the optical quality. So essentially, pointing error is, like, very simply put, just this misalignment between kind of optical axes with or without wavefront aberrations. And this could be detrimental to the actual optic quality. So we got word from Tensor Tech, which is the ADCS supplier, that the pointing error was tested and came to less than 1 arc second, which is definitely below our tolerance. And the reason, and it was even like in the hundreds and thousands decimal places, which was very, very encouraging. However, the negative downside to this is, remember I was talking about like the two requirements, we still don't know how the resonance will actually affect the pointing error of the satellite. So right now we're kind of in a limbo where we're still waiting on Tensor Tech to give us more information about and more imperial testing regarding resonance, because it is also dependent on our specific CubeSat, because not all CubeSats are the same and all of them have different resonance. So we're still trying to explore that and exploring whether or not we can do our own testing in regards to that. But for now, the microvibration projects are kind of put on hold. So.
And then finally, so once we have all of our design work done, we have to verify it. And we have actually just started to do so. And Eric, I think that this answers a bit of your question from before. And so we've been starting to run Nastran simulations. So for those of you guys who don't know, we use a software called Siemens NX called Nastran. And this stands for NASA Structural Analysis. Essentially what it is a structural analysis where you take a simplified CAD model of whatever you're making. So here we have a very simplified model of the satellite. We're focusing on the payload, of course. We tried to include most of the bulky components, like the bracket, the battery pack, the tuna can on the top, a couple brackets that are right above and below them that are incorporated into there. The big bulky component that we're missing is the star tracker, just because of the mounting considerations that we weren't sure about quite yet. So that is the next step that we'll have to add. We're also here missing the PCBs and the panels. So that is also a next step, is to add those as point masses. So once you have that and you mesh it, which basically means splitting it into a bunch of different components, a bunch of different elements that you can run nodal analysis on, we then run the simulation. So, I realize I'm away from the mic. I hope you guys could hear me. I'm sorry about that. So to run the simulations, what we have right now is boundary conditions. So we have all the rails and the tuna can are constrained. They have fixed constraints, basically because they will be enclosed within the deployer. So it'll kind of be tight along all faces. And then we have loads. And Eric, I believe that this is what you were talking about. We have here that we will be applying 70.5 Gs of acceleration, basically to mimic random vibrations and run a quasi-static analysis. 70.5 Gs comes from the NASA GEVS standard, which stands for the General Environmental Verification Standard. And this is sort of like a worst case scenario. We've been reading this paper from Spaceflight Laboratory on somebody who did an analysis on a bunch of different launch vehicles and launch providers, and this 70.5 kind of encompasses them all. So we will be digging a bit deeper into the specific launch vehicles once we get them, but this is sort of a safe case that we're using. So once we apply the constraints and the loads, we then run the analysis, and so far we have these two outputs. Well, another thing to mention is we run them along all different axes because we don't actually know which direction it'll be launching and which direction it'll be vibrating. This is the worst case scenario, which is along both the x, positive and negative x and y. It's symmetric in this model. So here we have the stress, and we have the maximum stress here of 105.45 megapascals. And you can see there that all of the kind of higher stresses are around the points where the geometry changes sharply. And you can see up there, based on the yield strength of aluminum 6061, it is pretty good. We have a margin of safety of 61.8, but combining this result with the assembly concerns, we are actually choosing to eliminate any of these sharp geometry changes, having a single barrel tube, things like that, which will make it even better. The other thing is displacement, which we can also get from these simulations. And here you can see that the maximum displacement is at the bottom of the four-optic, which is 0.183 millimeters. And it's kind of expected because the upper two brackets around the payload are actually mounted to the payload, whereas around the four-optic, because we don't actually know if there are any mounting ports or anything like that, it's just kind of sitting around it. So it's just kind of hovering there. So we've decided that we have to kind of look deeper into that, figure out a way that we can actually mount that at the bottom. Currently, the displacement is actually larger than the tolerance of the bracket, which means that there will be significant deformation and damage. So that is 100% something that we're going to be looking into. And finally, we have stop analysis, which Abir from optics was mentioning before, and thermal we'll talk about a little bit later. So sort of going through the same sort of flow that Abir was mentioning, we start with thermal, and thermal will provide us with temperature maps. We'll apply the temperature maps into our Nastran model, run some structural simulations, get the stresses and displacements, and then pass it on to SIGFIT, where we will get things like, rigid body motions, deformations, polarization and wavefront errors, and then we'll pass it on to optics to continue to continue their analysis. And along the way, we're also going to be outputting optical tolerances, so how much each component will rotate or move around and displace. And that'll basically make sure that it's within optics' requirements. And finally, next steps. So the simulation, the structural simulation that I was showing, that's not the only simulation we have to do. So first of all, we have to update the model to be more accurate. But once that's done, and once we can actually apply other things like bolt preloads based on the actual bolts that we're using and things like that, we will continue to run these stress analyses. We will also run things like frequency analysis to make sure that, again, we want it to be above 150 hertz so that it doesn't match up with the launch vehicle. We're also going to obviously run stop analysis, as I was just mentioning, both with Nastran and SIGFIT. We're going to be continuing with the assembly plan, which we have an initial copy of that, but we want to continue iterating, actually test it out with a 3D printed model, see if that works. And then yeah, basically finalize the design, create a bit of a mass budget, and then we'll actually get to, in phase D, physical testing. That's basically it from PayMech. That's basically phase C. Does anybody have any questions?
Okay, so doing assembly testing with 3D print models, great idea.
Exactly.
So that's good. I have one thing to say. I understood correctly, gluing the prism and a couple of other components in?
We're intending on gluing the grism. The other components will likely be within the drop housing.
Drop housing.
Great.
Yeah.
Glues forever.
Okay.
So it sounds like your grism is a custom thing, so that sounds expensive. just be aware that once you do it, it's not come out again.
Yes, absolutely.
Also, you want to keep your data sheets very carefully. For structural applications, a lot of glues, I'm not familiar with the master boxes here. A lot of glues have some pretty strict rules about surface prep.
Okay.
And you want to make sure it's compatible with your materials.
That's great to know. Thank you.
Your prism sounds like an exciting operation, and I would want to.
Yes, thank you. That's really great. Does anybody have any questions? Any other thing? Yep.
Just comment on this. It's not a question, just a great level of thought and detail into actually installing and assembling this. Yeah, that is often a missed or thing that's overlooked at this stage. So yeah, really good definition.
Thank you so much. Yeah, we have been considering that a lot this summer and trying to kind of flesh that out. We're still going to be going and digging a bit deeper in the next few weeks and months to basically make sure that we choose the best solution. So thank you.
I have a question, if I can go hot mic.
Yeah, absolutely.
Okay, thank you for the presentation. If you can go back to the slide where you had isostatic mounts and then the alternative design. Yeah, okay, I'm just gonna annotate on the Zoom call. What is this interface here, the actual contact between your component and the inside of the bracket?
So that's a great question. We haven't fully fleshed that out yet. I know that Chris and I were talking at one point about potentially having some sort of layer in between. Maybe we'll put glue, maybe we'll put a little bit of foam. It will be screwed in on two of the sides. But yeah, we haven't fully fleshed that out yet.
Okay, so you're gonna have like a set screw coming in the side like here? Is that
yes,
right?
exactly. Yeah.
Okay. Yeah. So it's just like in particular with this kind of funny wavy shaped geometry, you might have problems with tolerances for getting this machine. Like a CNC machine, you can typically pull off like 0.1 millimeter tolerance, but you have a funny shape here and like a sharp edge.
Yeah.
And so this interface, you need some way to have preload between your component and the interface. And ideally, like a set screw could be good, but that applies a point load to your component, which is probably less ideal. So like my suggestion maybe would be to break this kind of bracket into two parts, and then you could preload as a clamp.
Oh, I see. Mm-hmm.
And that way you're preloading against your component, and you can coordinate. You can tune that preload based on like your torque spec of the screws to a comfortable load, and then you know that you have contact all along a surface on both sides of the bracket onto your component.
Mm-hmm. That's very smart. Yeah, thank you.
You're welcome.
That's awesome.
So a question is, does optically clear glue mean optically clear just in the visible range or a wider range? As it is a space grade application of the glue, it is supposed to be wider range. However, we're not sure the exact range. So that is something we would have to double check to make sure that it does apply to our purposes of the mission. However, it is likely that it does apply as it is meant to be designed for space grade applications. Yes?
What is the justification for using clear glue? Why are you choosing clear glue over non-clear glue?
A concrete decision hasn't been made yet. It's just that is the option that we explored the most out of all the different possible glues. Because part of the reason is because we are using it near a lot of optical components, so we don't want any if there is any unexpected like developments during our testing or the actual application, we don't want the glue to interfere just in case as a secondary measure to prevent anything. However, if in our testing it doesn't seem to be working well, we have other options that we have as a backup that we're further going to investigate just to ensure. And in addition, we don't want the particles of the glue to adhere to other components and disrupt them, including other optical components, which is why.
One thing I wouldn't, optics is my area of specialty, but even if the glue is clear, it's going to have a refractive index, which is different than that of vacuum. So if you get clear glue on something and it's not a uniform sheet, it's going to wreck your optics, whether it's clear or whether it's black.
Okay.
So it might not be that much of a concern to use like a clear one versus using something else, because it's kind of the case of like, if it gets on there, it's probably wrecked anyway.
Okay, yeah.
So you just have to be careful with it. But yeah, it can kind of maybe widen your range of stuff that you look at.
Thank you. Yes.
So the refractive index point was 100% where we're going. I will also say though that from a tooling perspective, one of the benefits of an opaque glue in that case is that it'd be more obvious if a mistake was made to the devices when you're putting it together. Just because the refractive index things can kill you.
Inspect how the glue flow where you want it to flow.
Exactly. Like it's clear, it's going to be much harder to assess those things, especially against clear components. So optimal assessment of where it is. Once you look at like raw, if you're like actually checking where the surface get disrupted, it's a lot easier. It's flagged when it gets.
That's a really great point that we hadn't considered. Yeah, thank you. Chris.
You might have went over this, but how are we making sure that the glue is in the right spot? Like, will you have a fixture to make sure that everything's assembled well?
We were considering a fixture.
And that's where it has to do with one of the questions that we have about alignment to make sure that when we're actually gluing it, then it should all stay. I know you did some research. Do you?
I don't really have anything new
or
innovative to add. This was a long time ago with Maggie.
Sure, yeah. I'm pretty sure, yeah.
We were considering a fixture. However, because the glue idea isn't fully fleshed out as of yet, and we haven't decided on an exact glue, like a suggestion was made to have the glue opaque to make it easier for us to tell. So we were considering using fixtures throughout the process of alignment. It is in our preliminary draft of our assembly plan to use a fixture to hold and support things. However, there's no concrete decision that has been made yet regarding how we're going to hold the GRISM in place and consider all those aspects.
Yeah, and I also noticed some questions here. I'm sorry, I realized that we're running out of time. There's a question about incorporating the refractive index and other optical properties into stop analysis. Maybe that's something that you can answer?
In terms of incorporating the glue and stop analysis, I don't think that's the same on index. Yeah, I don't think that would be an optics edge. Like if it's part of the mounting, I think that's something that you might say.
With the actual mounting, that is something that we can do with Nastran. I don't know about how we would incorporate the refractive index into our simulations, but that is, yeah. Oh, sorry, I realized I'm going bottom up. Are there any plans for how to do payload alignment or plans for the equipment you will need? So for equipment, there are different things depending on which part of the actual assembly we're using. So for the part that we're doing, like where we're putting in the focuser with the 2 retaining rings, we need things like a spanning wrench, to make sure that we can screw it into the right positions. Things like spacers, if we want to make sure that the optical components are the perfect distances between one another. For the so I think the spanning wrenches and different wrenches like that would basically thread things in would be ideal. Other things like torque wrenches, of course, for putting in the screws. For the actual payload alignment, I think it would probably be best. So we kind of are trying to design it in this way. We made our changes to have sort of the tube, the GRISM, and then another tube so that we can kind of align all those individually. So we could like align each individual component like one by one. And that's also sort of why we chose to have things like the threaded positioning, so that if we need to adjust anything, we need to rotate anything based on like the slit position or anything like that, we can do so. We haven't actually gone too deep into the alignment processes. We'll have to definitely work with optics on that to see if they've done any research or know about what they were intending to do. But we're trying to make it as seamless as possible, but that's definitely something we need to look into. I don't know if we need to move on to the next question. I know there's one online and one here. I can answer the one online when I get back to my seat. Do you want to ask during the Q&A later? Or,
yeah, absolutely.
Or if you can ask online, that'd be great.
Yeah.
Cool. Thank you, everybody.
Thank you.
How do you control this guy?
I'm going backward.
Okay, there we go. Okay, guys, I promise it's the last one before the lunch. We have a, yeah, we have a long morning already. So, yep, I'm the ADCS lead for the team. I just want to show you like all of the hardworking members that have been on the team for a long time over the summer, and we made a lot of progress. So without them, we couldn't get this far. Yeah, so just a little bit about the ADCS design that Connor, Max, and I are working on. So here's the current ADCS requirement. So the control requirement is less than 0.6 degree with the jitter of 0.02 degree and knowledge of 0.02 degree. So due to the strict requirements, this makes the ADCS system more complex, and we have a short amount of time to develop the system. We have tried to make something like Mirage, SFLU, but we didn't have time to finish it. So we decided to outsource this and buy from two of this company, TensorTech and RSec. TensorTech, we will buy the ADCS module from them. And RSec. And these modules will meet our requirements, such as control of 0.46 during imaging, and jitter is less than 1 RSec, 10 milliseconds, and the knowledge of 2 RSec and 1 sigma, and this is static. So here are all the ADCS components. So on the ADCS module, we would have a control moment triangle, a magnet worker, a 6 fine sun sensor, and we will have a star tracker on board, and all the components would be the GNSS and an IMU. So here's a ADCS system diagram. So the ADCS module would mainly interact with the OBC. So the OBC will connect to the ADCS module to the register map to trigger every mode. And also the sensor and actuator will connect with a hardware peripheral to change mode, and we can download the sensor and actuator information down. So the ADCS module already come preload with some mode that we would use for our FINCH operations. So there are 6 basic modes, such as safe mode, detumbling, and sun pointing, and some advanced mode is fine pointing, LVOH mode, and tracking. I will go to the mode transitions in a sec. So it's organized like a finite state machine with mode transitions if something happens. So the first mode is save mode. The save mode will be triggered when soft error occurs, such as high voltage, high temperatures, high currents. And if the detumbling rate is higher than 260 degrees per second, the ADCS will enter save mode and will stay there and periodically check in on health, tumbling rate, and speed. And when the satellite is passively detumbled, less than 360 degrees per second, it will enter detumbling mode. So tumbling mode. So this would use B-dot control law to detumble, and with RSec, with TensorTech, Test Wi-Fi ADCS simulator, the detumbling will take about 12 hours. It will bring the satellite down to 5 degrees per second. So we will have sun pointing mode on the ADCS module as well. Due to some phases have more solar panel than the other, we would want to point the main solar panel side toward the sun for charging. And target tracking mode. So target tracking mode we manually set by putting the longitude, latitude, and out and height of a locations on Earth. The ADCS module will perform target tracking when it's in the line of sight of the target. And the accuracy using the ADCS simulator from TensorTech, we will get to 0.457 degree, which meet our current requirements. The next one is LVOH mode. So LVOH mode is triggered, so we perform nadir pointing, keep the attitude under control and without tumble much. And the next one is fine pointing. Fine pointing requires us to perform attitude planning on the ground and send the attitude quaternion to satellite to tell at what time we would be at this orientations. and it's achieve quite high accuracy as well. Yep, so that is the ADCS module. So right now, since we have an ADCS module, we will give that to system to integrate the module into FINCH. The next step for ADCS is to design a test bench that we can use to perform the system testing for FINCH and other mission as well. So we want to validate if the calibration is correct and the integration went well, and we want to be able to say, hey, FINCH, can you operate in these conditions or not? So we plan to build that. So why we want to build it? We have contacted a lot of suppliers from around the world, and the cost for it is extremely high. We also contact some labs, such as the Hawaii SFL. They have an ADCS tester in Germany, but since they are far away and the high cost of it and lack of accessibility, we decided to build one for ourselves, and this will help us to develop more reliable and complex ADCS subsystem in the future. So to able to do ADCS testing, we have to be able to simulate space environment on Earth itself. So we have a star map to simulate the star, home house cage, sun simulator, and OBC. This is very preliminary, so some of the simulator might not be there at the end. Yeah, so right now, this is the current testbed design. So we would have an air bearing to simulate the frictionless environment up in space to test if it be able to control in the frictional environment. So we have a home house cage that simulate the space magnetic field to validate the tumbling. The home house cage is a 3-axis, create a 3-axis magnetic field with the strength of 2 Gauss per axis. We want the variance at the middle of the cage to be 0.5%, and it's vary about 50 centimeter. That's just the length of FINCH. That's why it's just 20 centimeters. The home house cage can test the tumbling, and if the Earth magnetic field would interact with the satellite really. And we might have some other sensor to simulate automotive operation as well. Like I mentioned, H-mode is we use different sensor. So we might have a star map, a sun lamp, a motion tracking camera, but these are still very preliminary, and we will keep research on these. Yeah, so just about the test spec, that is the current design. So the air bearing will be able to rotate 3 axes with plus and minus 45 degree tilt, and it's made from aluminum, so it would not have any magnetic interference. The home house cage structure also made from aluminum frames, and there are coil around it, so we can put wire around it to run the current through it to simulate the magnetic field. So just some calculation about how big the cage would be. So we use these equations from IEEE to calculate the variation magnetic field. So we want a 0.5% drop off within 50 by 50 centimeter cube. So we would create a length. The side length of the cage would be 1.7 meter. So this is a home house cage electrical design. So we would have a power supplier. It would create about, current calculation is max of 10 amps to create the 2 gas magnetic field that I mentioned. So we will have a H3 controller to control our directions, and we currently design software to control the electrical components of it, and we would have a sensor to do calibration and control the cage magnetic field. So this is just a control software that we are trying to creating. This is preliminary, but during the semester, we would have a capstone team that currently want to work with us on designing the software for this. Yep, so this is not valuable anymore, I guess. So testing conditions, so we currently, like I mentioned, the cage would be 1.7 meters. So we want to have a clean room that be able to fit the cage. We're thinking of renting a clean room somewhere on campus or create one ourselves. So the clean room must meet the ISO standard and it's large enough for us to perform the testing in. We're still looking for the clean room, so if you have any connection, that'd be great. Okay, so next step for ADCS. Toward the end of FINCH, we would help support integrate the ADCS module inside FINCH. There's still a lot of analysis from structure and electrical need to be done, so we continue to support that. And we also continue to design and develop the test batch for FINCH and design the testing procedure when the system is completed. So it's just a timeline. So we will finish the design, the preliminary design for the cage now, and then we'll finalize the design and start prototyping. And when FINCH finished soft stack, we would use this test bed to validate FINCH operation in the space environment. And yeah, we continue to support the integration of the ADCS module into FINCH. That's it. Q&A, guys? Yes.
So how do you get 3-axis attitude control with a single CMG? Is it a variable speed CMG?
Yeah, it's a variable speed CMG. So the so the CMG can spin in 3 directions. So it's designed to be able to control 3 axes. Yeah.
Yeah, it's a complicated beast.
Yeah, they say it's the most advanced CMG on the market for small satellite. It's had flight heritage since 2020, so we. Robert.
Have you looked at ensuring that the star tracker won't be obscured by the sun or Earth?
Yeah, so right now I think we just have a discussion of like where to mount the star tracker. I think we're thinking of planning to mount it on the 2Y side because we are on sun synchronous, so maybe the sun is only think of in one direction. So we try to mount the face that the sun doesn't point it at the most.
Yeah, but the sun will always be somewhere else in the sky.
Mm-hmm. Yeah, so I guess we still have the conversation of like mounting that, the sun sensor. But I wonder, is that any other way to like prevent the sun and earth to point towards us?
Well, you can control your attitude like about the roll axis of your payload to try and keep the star tracker potentially.
Yeah. So I think there's also sun pointing mode. So we want to point the main solar panel toward the sun, and the star tracker could probably mount on the opposite direction of that.
Also, I was curious, why is the LVLH errors higher than target tracking? I would have assumed that target tracking is
I don't know. This is a simulator that they sent us, and they say the LVLH mode would we achieve this pointing accuracy. This is done by using a less advanced star tracker as well. So the pointing accuracy probably increased with the current star tracker that we selected. Oh, forgot about online. What is the design redundancy as in do you have backs? Huh?
The first ADCS question asked about the flight heritage module.
Yep, so like I said, the ADCS module have flight heritage since 2020. Oh, okay. Is there any? Oh, there are more? Okay. Aiden, ADCS CMG typically have singularly saturation concern. Have you talked to Renda about this risk? Yeah, so the saturation and desaturation of the satellite. So right now it's advertised to us that it's automatically desaturated when the saturation is get higher than a certain limit. It will automatically do that. And this can perform that during fine pointing and use a magnetometer to control it. Yeah. Yeah, the saturation. Is there any onboard orbital determination happen? Is this only changed GNSS space, how are the PV vector providing the event of GNS outage? Yeah, so in the ADCS software, there's already GPS4 orbital SGP4 orbital propagator on it, and GNS can update that orbital propagators as it's go on. But right now, the pinging location is the GNSS. Take care of that. With the GNSS, we can increase the pointing accuracy. But what is the ADCS mode run during eclipse, and how do when to manage the spike and add to when the satellite assists eclipse? Oh, Suraj have so many questions. Yeah, so how the mode operation will work is still under talking with the mode operation teams, and we would probably do attitude plannings on grounds somehow to know what would happen to it. But yeah, the operations mode is still under discussions. Yeah.
So I mean, this is quite capable ADCS system. I would be hesitant to never vendor build it. It's all done automatically. So you've got a lot of constraints, in particular in your operating pattern. You've got to keep the sun out of the Star Tracker. You've got to keep the payload towards the Earth. You've got to keep the Earth out of the Star Tracker. You mentioned what the exclusion angle for. You've got to keep the moon out of the Star Tracker. You've got to point your GNSS antenna somewhere useful. And I didn't see where the location of the GNSS antenna is on my mechanical models.
It will be
actually use all these requirements.
The plus set.
So it's worth doing some detailed open analysis. You can actually meet all of these requirements to meet your twice a month.
Okay, so we'll do some attitude planning right now and see.
You mentioned earlier that the modes, you mentioned something about like if the satellite's spinning too fast, the ADCS would switch into another mode, like a detumbler?
Yeah, if it's been more than 260 degrees per second, it will enter safe mode. And then
Is that mode transition, is that something that the ADCS will see and just be like, oh, I'm going to do this on my own? Or is that commanded by the computer? So like, is there potentially the computer is trying to control modes and the ADCS is overriding that since it's an integrated system? Or is the ADCS just spitting that out and you're deciding with your computer that if it's going too fast, we're slowing down?
yeah, so for the tumbling in safe mode, it automatically triggers. Okay. So if the IMU say it's been faster than this, it will enter the safe mode or the tumbling mode.
Yeah. I would just be maybe a little bit cautious with that because you don't want to have your computer trying to issue commands to do things while your ADCS system is like trying to do something else. So just be very careful with your expectations, I guess, with that, and make sure that like the ADCS system is not going to like go rogue and start doing something you don't expect it to.
Okay.
Do you know what the maximum rate of tumble is? Back in the day, I was at a couple of degrees per second, really fine. I recently have seen 2 different spacecraft get spun off the launch vehicles at like hundreds of RPMs.
Yeah.
Can't blame them for having problems. Nobody was designed for that. But it's good to know where the things are.
Yeah. So when it's finished tumbling, it's finished. Right?
How fast can you be spinning before the tumbling?
Oh, 300. So it's 360 degrees per second. Is when it's enters safe mode, and it's just use passive control to detumble.
If I spin the spacecraft off 10,000 RPM,
okay,
because I've got a garbage launch vehicle, will it detumble? There is going to be an upper limit of how fast you can be spinning before the couple, we just can't handle the phase lags are too large, and it's just not going to be.
Yeah. No, I'm not sure. So I think if it's more than 360, it will enter safe mode and will stay that way until it's less than 360 degree per second.
It'll depend on your update rate of your ADCS. The magnetic field is changing by more than 180 degrees per update rate.
That's basically what I'm getting at.
Okay.
It's like, don't necessarily design for it, but it's helpful to understand.
Okay. Oh. Questions here? No more.
Suraj probably is popping off.
Suraj. Sure. I'm not sure if it's overtime for lunch yet. It's 10 minutes over time, right? Yeah. Yeah. Anyway, I bring some Cokes and snack at the back if you guys want to grab some.
Yeah. Do you want to bring the snacks down here?
Huh?
David, pause the recording.
Okay, so we will be back at 1 p.m. See you guys then. At 1. We'll be back at 1 p.m. Okay, team.
We're gonna get started in like a couple minutes. Everyone go back to your seats, please.
Conversations. Oh, you know, I thought you were up.
Okay. How was everyone's lunch?
Good, thank you for asking, David.
Solid. That's great. Well, to kick it off, we will pass it off to
Did you start the recording?
Thermal. I did.
Thank you.
Before you do, could you drop the QR code once more?
Yes. Yeah, for sure. So the QR code is a long way away.
Sorry.
Yep, so again, the QR code is here. For those of you that are just joining us now, we have a QR code to join the Zoom link. If you have questions, please pop them into the Zoom link so that they are archived and our teams can answer them later if you don't get to answer them today. Give a few seconds. Sorry, Thermal, we're starting a little bit late. Okay. Thank you. Oh my.
134.
139, right there.
Alex, can you take the chair out of the door?
All right, give it up for Thermal.
Nice. Hello, everyone. Hello, everyone online. So yeah, my name is Oren. I'm the Thermal Systems Design Lead here for the FINCH mission. And yeah, I'll take you through some of our design we'll be doing on thermal for the past year and a half. Nice. Okay, that's on the agenda today. Similar, we'll go over a team overview, some requirements we have, some of the engineering artifacts we've been working on for the past year and a half, and then where we're looking to go as FINCH moves on into development AIT. On the right here, you can see some of the projects that we've been working on and some of the things I'll be touching throughout this presentation. Yeah, before I get started, this is the thermal team. This is the team that makes all the special sauce happen. Because I know thermal itself, we don't really have sort of a system on the spacecraft, but we're enablers for optics, for PayMech, for mechanical, for all the other systems to do what they need to do. And these are the people who make sure that gets done. So I want to recognize everyone here who's made an impact on all the projects that we do and the satellite as a whole. So we'll get straight into it. So what's our goal going into phase C? So coming into our coming out of our conceptual design stage and going into our detailed design stage. So we had a few projects that we wanted to have completed by the end of phase C. The key projects here are the NX thermal modeling that we've been doing to characterize the temperatures that our satellite will experience on orbit, as well as finishing up our TVAC plan and our bakeout plan, as well as finishing up our detailed design. So our surface design, our battery pack heaters, and some design that has to do with stop analysis. So we've heard this talk before, but thermal structural optical performance analysis is something that's been big over the past few months. So moving on to some of the thermal requirements and architecture that we have. So there's two high-level launch requirements that we need to meet to be on our spacecraft. One of them on the left is our outgassing criterion. So we need to have less than 0.1% collected volatile condensed flow materials and less than 1% total mass loss. And this will be characterized through a report that we write out to our launch provider that says, okay, these are the materials we've used, they are compliant to these standards, and that's how that will be verified. On the right here, we have our thermal vacuum bakeout, which is actually a should requirement, meaning we don't have to do it, but it's recommended. So we've opted to take the path where, yes, we are going to do bakeout, and alongside with that, yes, we are going to do TVAC, and the requirement specification for this is 60 degrees for 24 hours at 10 to the negative 5 torr. Aside from that, there are some self-imposed requirements we have on the thermal subsystem, and these are split up into two different flavors. The first flavor here is the temperature and telemetry requirements. So these specify what sorts of telemetry we're collecting and what sorts of temperature ranges our satellite can be in. So these manifest themselves in the operating temperature requirements you can see on the left, the telemetry requirements you see on the right, and they have multiple child requirements such as non-operating temperature ranges, what telemetry we're actually sampling, and the sort. The second flavor of requirements we have is design requirements. And these are the requirements that we have for our sensors. What specifications are they going to meet? Our actual radiator panels. How much are they supposed to radiate? How are they going to be designed? What tapes are they going to use? So these are some of the things that we've been considering in our design. And coming up with that, this is our thermal architecture for the FINCH mission. So specifically, there's a lot of things going on and we're interfacing, but the key things to notice is that for thermal control, we have two types of passive control. One is surface tapes, which will be put on the outside of the satellite or of our panels and rails to affect our radiator properties. And the second passive design is a thermal strap, which will be used to siphon heat from the camera to the radiator panel during imaging. We also have an active battery heater for the battery pack to keep it in its comfortable range, as well as the telemetry sources where we have custom off-the-shelf sensors from our ADCS module from our camera that we can read from, as well as NTC thermistors for specific components that we want to measure temperature of, which I'll get into later. But yeah, let's move on to some of the engineering artifacts that we've created over the past few months. So the first one I'll get into is our thermal simulations. So our thermal simulations are a big part of what we do here on Thermal, and there's two models that we've been using so far. One is a low-fidelity MATLAB model. So this is a nodal model consisting of 6 nodes that we use to do preliminary thermal design and rapid iteration on some of the projects that we've been working on. The next model that we're working towards getting in a working state is our high-fidelity NX model. So you can see a CAD of this here on the right, but basically using Siemens NX, Space Systems Thermal, what we're trying to do is get a high-fidelity understanding of all the heat loads and all the temperatures that our components will experience on orbit. And this will help us verify that we're actually staying within our operating temperatures and help us inform our design moving forward into the future. So far, most of our insights have come out of our MATLAB model, but we're working towards building up our NX model. So some progresses we've had on this are that we verified the accuracy of our MATLAB nodal model using our NX model, and we have some preliminary sort of simulation data about what our temperatures will be. So these are very preliminary because they don't include many of the heat loads in our power budget. So we're working on implementing, okay, the heater is supposed to image once every, let's say, 10 orbits, and it's going to take up this wattage. How will that implement itself in the model, which is something we're moving forward to getting implemented in the next month or so. And this will also help us move on with our stop analysis. So thermal is the first step in that pipeline, and we're sort of moving towards getting this model pushed out in the PayMech so they can start using it to get their deformations. So as I mentioned, most of our design has been with the nodal model so far, and this is one case where it's helped out a lot. So our surface design. So as I mentioned before, surface tapes are important because they affect how much heat we obtain and radiate away from the environment of space. So currently what we've done is we've taken a low AE ratio and a high AE ratio. AE stands for absorptivity over emissivity, and a high AE ratio means that you're conducive to actually attracting like solar energy, so you'll have hotter temperatures, versus a low AE ratio where you have lower temperatures. On the side here, you can see this is our high AE sort of spreadsheet here, which outlines what our high emissivity tapes are. And basically, what this gives us is this is the high AE ratio. Sorry, that means that we have low emissivity tapes, high absorptivity, and our temperatures get well within around 60 degrees. And this is comparable to our low AE ratio, which is much colder and around 25 degrees. So we've been able to explore and see what are the temperature ranges we can reach with the tapes we actually have in-house on our lab. And we've decided that we want to stick with a colder sort of orbit to keep everything sort of more controllable from the thermal's perspective. Because I know that we have like battery pack heaters and things. If it's too cold, we can turn the heater off. But right now we don't have any sort of solution if our components get too hot, which is one of the reasons that we want to stick to this sort of cold-ish area. Moving on from that, for our simulations, our next steps are sort of going to be identifying our ideal properties for our thermal tapes, our heaters, based on our simulation results. As you might have seen in that slide I showed up at the very beginning, much of our design is connected to these simulations being in a working condition. So actually getting them in a working condition where we can make informed decisions about what design we're actually going to put on our flight model. One of the key things here is that also determining if we need a thermal strap to siphon away heat from our camera's thermoelectric cooler. Because one of the things that we're looking into is thermally isolating the payload from the rest of the satellite. And as we mentioned with the PayMech presentation, actually putting maybe a thermally insulating glue or something around the brackets that interface with the payload to make sure that we aren't getting any unforeseen deformations that we aren't accounting for on the ground here. And again, just drawing up our taping scheme, creating our taping diagrams, and being ready for assembly once we move on to the next step. So a project that we've actually completed thus far is our TVAC and our bakeout plan. So for those of you that don't know, TVAC is thermal vacuum testing. So what it does is you put your satellite in a sort of metal chamber and it'll simulate the conditions of space. Bakeout itself is that process of removing dissolved gases or volatile compounds that might damage the spacecraft or its launch vehicle. And the requirements for bakeout are actually specified by our launch provider, which is what the requirement I showed before was. So the main sort of design or the plan that we created is the TVAC plan, which I'll go into a little more depth on. So our TVAC plan, what we've decided to do is this is sort of the description of what our TVAC plan will be doing once we get it in the chamber. So we'll have a thermal balance for 3 hours, one non-operational cycle, 4 operational cycles, and 2 payload verification cycles, which will verify that our payload actually performs in the way that it's supposed to do. So such as straight light testing we're going to do in TVAC and other sorts of tests that we're going to be running. The specifications for this are outlined in the table here, and these come straight from NASA GEVS as well. So our operational temperatures will be 66 degrees, negative 29 degrees on the cold side. Non-operational temperatures will be 75 degrees to negative 40 degrees. We'll have an hour plateau at every operational temperature. For the non-operational temperatures, that'll be a half an hour plateau. And our ramp rate will be 2.5 degrees per minute, which is what our orbit currently gives us when we analyze how much we spent in eclipse versus how much we spend in the sun. A better version of this table and the other tables is this here, which is a holistic overview of our TVAC cycle. So as you can see, we have thermal balance at the start of the test, non-operational cycles, our operation cycles, and at the very end, we have our payload verification campaign. And if you zoom in a little closer, you can see that we have functional tests running all throughout this campaign. And these functional tests are really to test out our ability to image, our ability to perform compression. So a full compression, as well as we have the ability to split our compression up into stages. So testing that functionality, reading telemetry, seeing our safe mode, so how we perform once we simulate a safe mode inside the TVAC chamber, and other functional tests that we run through to verify that our satellite will actually work in the conditions of space. So one of the last projects we've been working here on thermal is our thermal sensor selection and placement. As I mentioned before, we have custom off-the-shelf modules that have their own temperature sensors that we'll be reading, but we also have our external thermistors that we're thinking of adding onto the spacecraft itself. So every sensor every board with an MCU will have one thermistor on it, as well as one thermistor on every panel of the satellite. We're actually debating and thinking of putting two sensors on the larger panels to quantify thermal gradients that we get, as well as sensors on the payload and battery pack to monitor these critical components. So in total, the minimum number of sensors we're thinking of putting on FINCH is 14 thermistors, but this is a lower bound, and if we can accommodate more, we definitely will put some redundancy in our design. So just moving a bit onto that, we've compared multiple different types of sensors, RTDs, thermistors, thermocouples. What we found to be best for our mission is working with thermistors, and specifically an NTC thermistor, because it works better in the temperature ranges that we've selected that FINCH will be in. And just a bit on the placement, we've drafted up some diagrams. We're in the stage of finalizing some of the diagrams we have on FINCH to mark out where our sensors will go. This is some example on the right here of where our sensors will go on the payload. We're trying to figure out a way to monitor the temperature of the optical components without actually having to put thermal sensors on the optical components. So one of the ways currently how we're doing this is that we're measuring the outside of the payload housing and using that as sort of a guide to perform further thermal modeling to infer the temperatures on the optical components. But then again, this is subject to change. And sort of this is where we're going with the next steps. We know what our sensor is. We know the general places we want to put them. So we're finding out specifically where do we want to place these sensors? Where do we want to place our sort of knowledge about where the thermal data is, so that we can make informed decisions about the data that we get on the ground. So just moving on to a little more summary of next steps that we'll be going into. So closing phase C, we finished most of the things that we wanted to do. We've created our testing plans, our TVAC plans. Everything has been sort of finalized except the actual detailed design, which is what we'll be working on throughout the next few months. So our phase C completion criteria is that we'll have our testing plans done, we'd have a bill of materials, and that we'll have performed thermal optical stop analysis by the end of phase C, and we're well on our way to do this in the next 4 months. So looking at that, just closing out phase C, like I mentioned, finalizing our design, updating our NX models to actually inform our design, and then tracking our mass, our CVCM, to make sure that we comply with all the requirements that our launch provider provides. And yeah, plan for phase D, systems verification, actually conducting TVAC testing, updating our simulations, as well as making sure that all the other subsystems have what they need to make their design a success. And yeah, that'll be thermal. If anybody has any questions, shoot away. Awesome, yep.
A few things. So that 2.5 degree per minute speed rate, that comes out of what you think you need, or out of facility capabilities?
Right.
Pretty ambitious, but that's pretty fast moving.
Right. That comes out of, so we made the assumption in our modeling stage that our satellite will spend half of its time in eclipse and half of its time in the sun. And based on that, we've made our slew rate to match what our slew rate would be if that were the case. And that came out to be 2.5 degrees. Most of the TVAC vendors we've talked to can do up to 5 degrees per minute. So we haven't run into that issue yet of not being able to achieve ramp rate.
It's not my experience.
Yeah. But yeah, thank you for the question.
Maybe a third of that. I do have one other thing, and this is a bit deeper. So thermal analysis, you showed like one representative plot.
Yes.
I'm wondering whether you've done the analysis for your sort of worst case cold and worst case hot.
Yes.
And I'm wondering what your model inputs into that.
Right. So we have done our worst case cold and our worst case hot. The results up there were our worst case hot scenario. So our inputs when we change from worst case cold to worst case hot, what we're actually changing is the sun's the solar radiation that we're getting from the sun, as well as the solar radiation. Sorry, not solar, the albedo effect that we're getting from the Earth. So those are the two parameters that we are changing to get worst case hot.
Internal power dissipation. I imagine your spacecraft is not constant power. I imagine you've got a safe old mode where you dissipates a couple watts, and to an operating mode where it dissipates 50 watts.
Right.
That's going to make a huge difference.
Right. Awesome. Yeah, that's currently something that we haven't considered yet, but we're looking to implement into the actual NX model when we consider our power budgets. So not implemented yet, but looking into putting that in a case. Yeah. Awesome. Yeah, Aurora?
I have a kind of similar question. So when you have like your worst case hot and worst case cold, that's for the entire satellite, right? Is there more specific details for worst case hot and cold in different areas of the satellite?
Yes, we do. So that's where the NX model comes in. We have temperature distributions for every component since we've used the 3D mesh.
Okay, but it doesn't take into account like heat produced in the satellite.
Yes, it does. Yeah.
Oh,
It will once we implement it.
Okay.
Yes. I know we started late, but are we good on time for questions online or?
1 minute.
1 minute. Okay, let's take a few questions online. Okay, no hands raised. Okay, let's see. All right. What considerations are driving the placement and size of the radiator panel? Awesome. So our radiator panel, the biggest thing driving us right now is the placement of the star tracker and the placement of the solar panels on the satellite. What we found is that our thermal optical tapes can do well to make any of the panels radiate more than we needed to. So these decisions are really being driven by the other subsystems that need that space more than we do. Awesome. Do you have access to a TVAC chamber with an optical window for payload verification tests? Yes, we've only been sourcing TVAC chambers that have an optical window of sufficient size so that we'll be able to get data from the payload verification tests that we run. Is your sensor placement you mentioned for ground testing or flight? The sensor placement I mentioned right now was for flight model of FINCH. For ground testing, we'll have many more temperature sensors placed around the satellite just to quantify more what our temperature gradients would be. And the last question I have here, what factors are you taking into consideration when deciding where to place payload temperature sensors? Awesome. So payload temperature sensors themselves are an interesting sort of scenario because we don't sort of care about the temperatures of the payload. We care about the temperature sensors of the optical components. So like not the payload structure itself, but the optics. So the payload, placing sensors on the payload mechanical design is actually just a sort of pseudo method of getting the temperature of the optical components inside it. This is so far the way that we've chosen to do it is place sensors on the payload itself and then infer the components, the temperature components of the optical elements, but open to any suggestions on how that could be better done or like higher accuracy. And I think that should be all the questions.
We can ask at the general field.
Okay, so I'm now going to be talking about the electrical subsystem. Just a quick programming note, I'm only talking about the non-power aspects of power. Aurora is going to be talking about EPS in about 20 minutes. Here is a look at our team. We're a pretty sizable team, and everyone has been doing great work towards pushing us towards the design that I will be presenting today. And this is that design. This is a very high-level overview just of the fundamental components of our satellite. The three things that we are designing are EPS, OBC, and PALEC. These three we are designing the PCBs for to interface with all of the other things that you can see on here. The main things to point out, RF is a COTS module, ADCS is a COTS module, and the camera is also a COTS module. So we have to interface with those things. Physically, what this looks like on the satellite, you've seen this diagram before in the systems presentation, but now I've done a little annotation for electrical specifically. ADCS and RF show up at the top, then our OBC and EPS boards, battery module, large star tracker, and then payload controller with the sensor right below it. Here is a look at, we looked at the high-level overview, and then we looked at physically where everything is. So this is kind of trying to blend the two. So you can see our 3 boards, OBC, EPS, and TALEC, in the physical order that they come in the satellite, and all the things that they talk to in and out. The way that we are connecting all of these boards together is having a common spacecraft bus. We're trying to use the PC104 standard for physical size. Electrically, we don't need 104 pins. That's like a lot of pins. So we're probably going to use a condensed version of that, maybe 40 to 50, but using the same type of pin, so 0.1 inch headers going in between these boards. And I'll be carrying things like CAN bus communication between the boards and the various high-speed data links, again, in between the boards. For Phase C, what we've been working on is something I'm calling DevKit-SAT. As we all know, it is impossible. It's getting better, but still impossible to get a lot of silicon, and our microcontrollers are no exception. We ordered some about 2 years ago, and they showed up in May. So in the meantime, we have been working on building the OBC and PALEC boards in a DevKit fashion. So just something that can mate on top of a Nucleo DevKit, so we don't waste any of our precious microcontrollers on something that might not work. We only have 3. Let's take a look at onboard computer, or OBC. So this is fundamentally the brain of the satellite. This is responsible for the command and control of the satellite, as well as monitoring systems. So it does have control over EPS. EPS doesn't have a separate microcontroller. OBC handles all that, so it kind of acts like a sequencer and a monitor for EPS. It also does liveness checks on all the other systems. So that allows us to, if something locks up, we can just kill power to it, bring it back up, and hopefully that will help fix it. It also is a major hub for I/O. So because, if you remember the stack up, this is at the top of the stack that we are designing, that means that it has direct connection to the RF modules and ADCS modules. It also has a connection to the umbilical, which David talked about, and we'll be covering a little bit more in a moment. Here is a brief little block diagram of what is actually in OBC. At the brain of it is a STM32G4, that's kind of a mid-range STM32. We are using CAN bus to communicate to it, both from RF and PALEC on the other side. ADCS gets some control lines and has a pass-through to the star tracker. You'll see on the PALEC slides, the star tracker just goes through. That's just for wiring convenience. It's nothing special there. And then on board we have some NOR flash for telemetry storage and a watchdog timer for resetting. And then an RS422 line coming again from PALEC that goes to RF for high-speed data. Some details about this. Like I mentioned, OBC is the EPS hub. So we have control of a bunch of load switches, enabling us to turn on and off different subsystems, both for fault recovery and also just for load shedding. Power is very important. We also have a watchdog timer on this. This is the only system, or the only system that we're designing that has a watchdog timer, specifically because OBC can't reset itself. If OBC locks up, no one's it has control of the load switches, so it can't reset itself, and that's where the watchdog comes in. We also have NOR flash, and that's just for storage of telemetry and logs. As mentioned before, we have a lot of telemetry to deal with specifically for ADCS, all that engineering data that we need to send down, and that'll be stored on OBC. The umbilical, which is something David covered a little bit earlier, is primarily used for debug test and power delivery while on the ground. The OBC will take in this DB21 connector and break it out to the other subsystems. Through this connector, we get debug for both microcontrollers individually. That's a SWD port for flashing, and UART just for general communications and debug. We also have the ability to power batteries, charge batteries, and either charge batteries or charge the satellite as if we want to have the battery in or out of the loop. That's OBC. Let's turn over to PALEC. So PALEC is the main interface to the payload, as the name suggests. It interfaces with the FLIR Tau payload camera. We have some requirements about the data rates. We have to operate that high-speed data link at 34.4 megabytes per second. It's a 14-bus CMOS connector that goes into ST's proprietary DCMI peripheral. And we need to store 1 pass worth of data cubes at minimum, which is equal to 734 megabytes. We also need to control that camera over RS-232C. That's not too challenging. And the other major requirement is that we need to compress the data cubes. Our downlink budget is limited. Our images are large, so what do? You have to compress them down somewhere. The issue is that that's a very processor-intensive algorithm, so that's something we have to deal with on this. Here's a diagram of PALEC. As you'll see in the center, that's the STM32H7, the top of the line of the STM32 series for compression reasons. We connect to the FLIR tau over the CMOS and RS-232 lines as mentioned. As I pointed out in OBC, Star Tracker just shoots right through just for wiring convenience. The H7 uses the SD card to store data and then has a connection to the CAN bus to communicate to OBC and RF, and then has that high-speed RS-422 line for the actual transfer of data to the RF system. To connect to the camera, we are using a flex PCB. The camera by default has this Heroes DF13 connector, I believe, a high-density 50-pin connector, and it's a board-to-board connector, which is unfortunate because we don't know exactly where the camera is relative to the PALEC board. So we're using this flex PCB to be able to have a flexible, pardon the pun, way to connect the camera to the PALEC sensor. The issue is that this connector sucks. We had some members spend like 2 months trying to solder it, got nowhere. We brought it to like a professional who does soldering for their job. They were like, you guys are insane for doing this. This is really annoying. We're probably going to have to do automated assembly for this board because it is the only way to connect to the camera. To store data cubes, we are going to be using, well, we have to find something high speed. The issue, as I mentioned before, is that the camera outputs at 34.4 megabytes per second, which like isn't blazingly fast, but it's not slow either. And we need to store around 1 gigabyte per pass. Our available options based on what peripherals are available on the H7, we looked at SDRAM, which is super fast. It's the great-great-great-grandfather of DDR4, so it's like pretty speedy, but very low capacity, 256 megabytes maximum. That's not even a single frame of data, so it's not acceptable for us. QSPI swings and misses on both counts. It's very slow to write, and it's pretty low capacity. And then that left us with SD cards or MMC memory, but SD cards are the more solderable and accessible version of that, which has high capacity and can achieve high speeds. But there's a lot of weight on that can word because the new problem is we have to decipher the Delphian DDR documentation. Delphian is a synonym for complex. I just really wanted the alliteration. The issue is that at normal speeds, like 25 megabyte, it's pretty easy. You just need to have decent connections from the SD card to the microcontroller, but anything above that, you need to go to 1.8 volt signaling. STM32 is 3.3 volts, so we need a logic converter. Except it's not as easy as that because that logic conversion has to happen after a handshake at 3.3 volts, so you can't just only give it 1.8 volts. It's so weird, very annoying. Our workaround for this is a bidirectional auto direction sensing voltage converter that just has 2 different power voltage levels coming into it, and you can switch based on the mode of data delivery that you want. Also, to stay under a super high speed line rate, we're using DDR just to get a little bit more data out of our clock signals. Liam is now going to talk about RF.
Good job. Thank you. Yeah, so RF, the Black Magic subsystem. Firstly, I wanted to say all of our parts right now are commercial. They're off the shelf. And the reason we wanted to do this is because usually there's like one person at a time that knows about RF on the team per like cycle of people. And this year it's me. And yeah, we'd have it where we'd like make a link budget and then we get a new RF lead and they'd go, well, that was all wrong. And then someone else would come in and go, well, that was all wrong. And each time it would be like, we weren't sure what we were doing. And with Heron, there was also a whole bunch of complication where it was set to launch and then it got delayed by COVID. And then we went back and looked at it and went, wait, this thing wouldn't have talked to it. It would just been a floating box in space. And that's not what we want. The most important thing about RF is making sure we can talk to it. It's essential, and we didn't want to take any risks. So with this disparity of RF being like the functional thing of if we don't have it, none of this matters, we wanted to make it as safe as possible. So that's why we decided to go with off-the-shelf for the antennas and also for the transceiver. The transceiver we're going with is the SRS4 PC104 form factor. We're not going to be using the connector per se, but it's in our sizing. Yeah, it's 5 megabaud max speed. Can modulate up to 8 PSK. Hopefully, we don't need to be going at that rate the whole time. It's going to depend on compression. If we're sending down these data cubes within our limited pass range, there's a little bit of wiggle room there based off of like where we place the ground station or where, but it's flexible. It's you can see it has BPSK, QPSK, APSK with an adjustable thing of 100 kilobaud to 5 megabaud. We're probably going to be running it at 33 dBm. Yeah, well, 1 TX SMP port, 1 RX. Negative 122 dBm with RF sensitivity, which is quite good, but that changes if we're going to be going at a much higher data rate. And so our link budget kind of depends on how well compression goes. When we look at the internal of it, it's pretty standard. It's a single conversion super heterodyne transmitter and receiver. It has an FPGA, it has an MCU, it has internal telemetry sensors that you can just sort of ask and it will tell you. And then, yeah, it has a couple different ways you can process data based off of how much speed you need. And as Reed said, we're going to be doing RS-422. Yeah. And then going into the antennas of it. So we have the GNSS on the plus ed face, which is at the pointing up here, from the ADCS module, which is provided by TensorTech. There's a question in the chat when ADCS was presenting about what the test plan is for that. We'll connect it to OBC and we'll ask for data. Sort of how it goes. And then for the PX and RX, this is for TTNC and data. And this is going to be a point of contention that I want opinions on, is that we're having it only being on one of the faces. We're not going to have another set on the other face. So it's not going to be plus X minus X. It's going to be 1 on plus X. It has the complication of if ADCS fails, then we're only looking at it on one of the sides. And how do we recover from that? We were having this design decision on, do we want to split it and have both, or do we want to have a switch in there? And we hadn't really done all that much high-speed design before, and so we wanted to make sure, oh, it's as safe as possible, let's just have one and not split it. But that's subject to change relative to, as you guys, give feedback. And then, yeah, for phase D, we're going to be working on the ground station in parallel with the on-satellite RF and testing them with each other. If we can complete the link on ground, and when we send it 600 kilometers away, you just add what, negative 150 dB, and it should be fine. No, it's okay. But yeah, so we'll be testing it with the OBC, and then we're sort of working with half a link right now because we don't know what the ground station is going to look like. And so based off of the assumptions that we made with it being as weak as the satellite, we close. But as things change, if we have to go at a higher data rate for longer, giving our imaging passes being shorter than we expected, it's sort of a living document. But yeah, that's sort of how we're going. We're approaching this detailed design. Yeah.
Cool. So that is 15 minutes worth of a lec. Here's that diagram again, just for reference, with the little blinders taken off, so it's more complex, but we walk through it. So hopefully that's digestible. Yeah, we'll take questions at this point.
Yeah.
But okay, so gonna go backwards. E&M first. Electromagnetics first. Radio first. So sorry, did you say that currently the thought was to put the antennas on the Z-axis?
No. For the telemetry and data on one of the side faces, the X face, then have the ADCS module orient us when we're passing over a ground station.
Okay. Is there going to be any problem with that? Harking back to the point of two were making earlier. So you're going to be problem with that with the fact that you know that you're going to have to be, sorry, you know that in order for imaging to happen,
yes,
Z-axis will be oriented directly at the ground, putting this orthogonal to the ground.
Sorry, for imaging. We're not imaging and downlinking in the same pass.
Okay, so you wait for another pass.
We're having a separate downlink pass where it's just
understood.
yeah.
That is another one. The other question, I'm going to back up. Is there a testing regime where you're going to be rad hardening or rad testing the circuit boards?
No. So this is just a risk versus time that takes. We're in low Earth orbit. This is a 1-year mission. There's not much radiation in low Earth orbit. It's fine.
You can
That's not real. It can't hurt you. So I'm going to attack both. So if a thing that is little understood or little known, SD cards are.
They are okay.
And the destructive phenomenon, generally control themselves. It's single event, so it's statistical. Maybe 6 months, maybe a year, maybe it'll be fine. Maybe it'll die in a day.
So you're saying SD cards are subject to single event upsets or like catastrophic events? Okay.
So this is EMC is the same way. There are ones that are not. The last time I went around with EMC testing, I had 10 out of 11 part families fail.
Well, hope we're 11 out of 11.
So that's a choice you can make.
We'll look into rad hardening that specifically because thanks for bringing that up. I didn't realize it was so susceptible.
We did use a non-rad card SD card one time on a mission that I worked on, and it worked. It was only used for like 6 months, but every once in a while we would tell the payload to turn on, and it just that pass, it just wouldn't turn on. It would work fine the next time, but sometimes it just wouldn't boot properly. And we don't know why, but I bet it was because of that.
So you have it's a hard problem. You are putting in actually a fair 300 megabits of data per second is a very hard problem to solve.
Yes.
And I can see why you ended up on SD card. Just there's a paper from a few years back from SmallSat something in iPhones. Did a bunch of testing.
Okay. We'll take a look at that.
The other thing is now on the radios, single antenna, and why isn't your ACS to work? Be able to communicate.
Yeah.
That's what the trouble.
Yeah. We're mentioning that worst case ADCS fails. We're not facing it at all. We can't detumble because we can't get a signal up there. Finding some ways in software on the thing to recognize that that's happening, either send it into a tumble to hopefully reorient it, or blast it with a more powerful ground station.
Power splitters,
Yes.
are not expensive. Put an antenna on both sides.
Okay. Because it was a do we want to send in an SMP into a port that we make, split it out into 2 other SMPs, and all the matching that would have to go into that, and the loss that is baked into the circuit there.
It's seriously, you are really.
Okay.
I mean, your
This is why we have these. Okay. Yeah, go ahead.
Yeah. So I need satellites to work. But combining those 2 points, I do agree.
Yeah.
Of having 2 antennas.
Yeah.
I prefer.
Yes.
But student teams like yourselves, like you do, as you said at the start, there are a lot of unique restraints you guys are under that a lot of, we'll just use the term, bigger teams or more with companies behind them.
Yes.
Don't have as many issues with knowledge transfer and gaps of things, and so well done on considering that as part of your risk of implementing a solution where you don't think a lot of the team has know-how in that area.
Yeah.
So in this case, I do side with the opposite decision.
Okay.
But definitely keep that in your other.
Yeah, of course. Yeah.
Given you guys are not moving from SD card or anything like that, cold spare or dedicated?
A cold spare of SD?
Yeah, MC or SD.
Yes. Yeah, space isn't that big of a concern. I guess it would just be adding a mux.
Yeah.
That's not too bad.
That's not bad.
Yeah, that would be an easy. I mean, obviously, rad hardening would be a good first step, but having a cold spare wouldn't hurt. Anything else? Yeah, I saw Bruno's questions. I'll get to those after because we're just about at time. What's up, Ian?
Yeah.
What's your transmitter, the data rate is variable on orbit?
Yeah, you can send it a command to change the data rate.
Is the receiver also variable data rate on orbit?
I believe so.
Okay. Yeah, I would stick with one if you can, unless you absolutely need to have variable data rates on orbit.
Yeah.
For both TX and RX or just RX?
No, just RX. TX you can change.
Oh,
but
yeah.
RX,
We were planning on keeping RX
As
consistent.
low as possible, and
Yeah.
The other thing is the transmitter half duplex or full duplex?
Full.
It's full. Are those sensitivity numbers that they quote? What is the isolation between the ports that gives you minus 122 dBm while transmitting at full power? Do you get minus 122 dBm sensitivity? Because your frequencies are relatively close.
Yeah.
And there isn't a lot of space in that module to have a beefy filter. So just make sure that is actually going to work if you're counting on it.
Yeah. I'll double check the number, but 13 is coming from 13 dB. That could be good.
That seems really low.
Okay.
For isolation?
Yeah.
That's very low. Yeah. All right. Anything else? Cool. Thank you very much.
Okay. Hello, everyone. My name is Aurora. I'm the power lead, so I'm going to be talking about all things power on this satellite. So the agenda for today, we're going to talk about the team, which is basically the exact same team as electrical, because we work really closely together. A bit about the system overview of the electric power system, some of the active projects we're working on. So what we've done is that we are going to have one unified EPS board with all the components on it, but right now we're in the phase of development where we've broken out this PCB into a bunch of different PCBs where we can test individual components. And the power budget. So yep, this is the team. I will mention them as we go along in the presentation because a lot of them have worked on different projects and designing different boards for us and also testing boards that other people have worked on. I should mention Darian's been helping with the testing as well. He's not mentioned. But. Okay, yeah, so key requirements of the system, pretty straightforward. We need to provide power to all the subsystems on the satellite. So with the power budget, which we'll talk about a little bit later, we need to make sure that our net power generated and our net power from the batteries is equal to the power that is required by all the different subsystems. We also have requirements from our launch provider to have power cut off using a roof for launch pin, depth switch, and we need to talk about the storage of the batteries. So we're going to have to hand off the satellite, and there's going to be a period of time where we won't be able to charge the batteries. So we need to make sure that they can withstand a period of storage. And safety. So we have a lot of safety protection features, which includes overcurrent, reverse current protection, over voltage, all that kind of stuff, which I'll get into a bit later. So this is the system overview. I'll just do a quick run through of this, but essentially, anytime you see a plug, that's the ground support equipment, so the umbilical that you were talking a little bit before in Alec. You'll see a couple muxes there, and that's basically to select whether or not we are powering that section of the system from the ground support equipment or from either the batteries or the solar panel. So we kind of have two modes here. When we're in solar, or when we're facing the sun, we're not in eclipse, we're going to be generating power from the solar panels, which is going to go through the power converter called a maximum power point tracker. It also doubles as a charger, so that regulates the charge going into the batteries. So we program that, and that's a constant voltage MPPT. And then that power can go in to power the rest of the system. At peak power moments, we're going to be powering
the main voltage bus by the batteries as well as the solar panels, the regulated solar panel voltage. And during eclipse, it's going to be entirely powered by the battery. And then we have that main power bus that is controlled by the depth switch. So you can completely disconnect power from the rest of the satellite when it's required by the launch provider. And that goes to our buck converters, which will convert our bus voltage down to 5.1 volts and 3.3 volts. And then we have that power go to load switches, which regulates which subsystems get power at what time. And we have a bunch of power monitors, so ammeters and voltmeters, and all that telemetry data is I2C, and it all goes to the onboard computing MCU. Yeah. Okay. So as you can see earlier, actually, all the white boxes represent current PCBs that we have in development. So we have a buck converter PCB, we have a load switch and power monitor PCB, we have the battery monitoring system PCB, we have 2 MUX PCBs, and we have our MPPT. We're actually using an eval module for that. So the ongoing technical work is we have some PCBs that are currently in different phases of design on Ultium, and we have PCBs in the testing validation phase because we've Gerbered out, we've assembled the boards, and now we're just making sure that they work. Yeah, so here we have the MPPT chip. So the way it works is because it is constant voltage, it's not actually true MPPT. What it does is it compares the voltage coming into the chip with a reference voltage. And if that voltage is lower than what's required to charge the batteries, because the batteries have to be charged at 16.8 volts or somewhere around there, depending on their state of charge, obviously. But we program it to be kind of like a constant voltage that we charge the batteries at. So what it does is if the voltage coming into the chip is less than that, because for whatever reason we're not getting the amount of solar power that we're expecting, it will reduce the amount of current being used to charge a battery pack so we can boost that voltage back up. And that way we can move along the graph here and try and like get to an optimal tracking point, as you can see there. All right, so right now we are testing, hello? Okay. Right now we are testing the evaluation module. We're having some weird issues that we're currently debugging, and that's something that Nick, one of our members, has been working on, where we're getting everything is nominal except for the voltage coming out to charge the batteries, which is kind of the most important part, which is kind of a bummer. But essentially there's voltage coming out when the charge is not enabled, and when the charging is enabled, it's 0 volts on Vout. So we're currently trying to sort that out. We might have to contact TI because it might be an eval board issue. That's something we're working on. All right, next I'm going to move on to the battery monitoring board, which was yeah, we designed it ourselves. Essentially, we didn't get an eval module for this, and there's been a lot of well, these are the main functions of it, and I'll go into a little bit of how we've been testing it. Yeah, so it reads our cell voltages. Obviously, we have, voltage monitoring. And if there's over voltage event, we have 2 power FETs that are triggered by the chip and open the circuit to protect our batteries or to protect our system. And then we have temperature sensing on this as well. We have passive charge balancing. And then we have, status alerts that will communicate with our MCU. And those are things that we've been testing. So it's all I2C communication. And we've basically been using an Arduino to do that testing. Joe's been doing a lot of that testing. And right now we are working with firmware to develop a more robust, comprehensive driver because there is a lot of post-control features that we want to program on this chip. And we also want to test the cell balancing, which we have not done yet, which is, as we know, very important for the batteries because we want them to be at the same state of charge with the pack so that we can ensure the longevity of our battery pack. All right, here's the buck converter board. So we have our input voltage and we'll output 3.3 volts and 5 volts. And currently that's being tested using power supply. I think Joe and Darian are automating the voltage current sweeps on a power supply. And they're measuring primarily the efficiency of our chips, which is really important, obviously, the amount of thermal dissipation, which comes with efficiency, and the amount of voltage ripple on the output. All right, and the load switch and power monitor is another board that's being designed, currently in progress by Alex and Sarah, 2 other members that we have. We have an I2C IO expander. We just finished the schematic review for this, so it's still kind of in development phases, but there's going to be 6 load switches in total that are connected in series to power monitor, and then that goes to the output of the system. And then as you can see on the bottom, there's some protection built in to both of these, inrush current protection, thermal mitigation, and current and power monitoring for the power monitor, which makes sense. All right, and then we have the 2 muxes. So this is the last thing I'm going to talk about in terms of the boards that we're working on. So here we have the ground station equipment mux and eFuse board with the current monitor, so kind of all in one board. And here we have a truth table for selecting whether we're powering the satellite with the batteries or we're powering it with the ground station equipment. And here we have the solar panel mux, which is even before that. Are we going to be powering the main voltage bus with the solar panels, or are we going to override that with the ground support equipment so we can charge our batteries directly? That's just kind of like the schematic for, well, bare bones schematic. Yeah. Okay. Now briefly talk about the power budget. I think I only have like 2 slides for this. But yeah, so obviously we have some key constraints for the solar power generation. We have kind of a small area for the solar panels, and now we have, patch antennas, maybe more than 1. So that's going to impact how many solar panels we're able to have. But right now we're envisioning 6 panels on 3 sides, and we're probably going to connect them in 9 in series, 2 in parallel, just because the charge voltage required for our batteries is so high, which is going to mean that the efficiency for our power converters is going to matter a lot, because we're going to have to downregulate the voltage and increase the current to be able to provide enough instantaneous power to these subsystems. Yeah, and then also the other thing is our net consumption. We have a lot of different operational modes, and so we've kind of estimated how much power is going to be consumed in all those different modes, but that's still something that's a bit up in the air, so that's something we definitely want to confirm that our totals check out. For now they do, but a lot has changed in the past 6 months, so that's something we want to revisit. We talked about battery storage being kind of a unknown issue. Temperature, so the batteries obviously have to be above 20 degrees Celsius or higher, so that's something we want to keep an eye on. And yeah, the power storage is finite, so we want to make sure that we have enough time to charge our batteries in between our peak power modes, essentially. This is our chosen solar cell. Chosen because it's, has flight heritage, pretty high efficiency compared to what else is out there. Yep, so we've gotten a quote on that, and that seems to be working well for us. Our batteries are lithium polymer, pretty high density, pretty reasonable C rate and long life, and they also have flight heritage. All right, and my last slide, I promise. So the summary of totals required, I mean, these are just, some numbers that we have, but the maximum possible power, and this probably won't ever happen, but worst case, that's how we operate with the power budget, is around 24 watts. The solar generation numbers right now, like if we're at 100% solar incident energy, is about 17.36 watts, and we always take into account 20% distribution loss across like the voltage regulators and all the protection circuitry that we have, which is pretty conservative estimate. So that's kind of, as you can see, a bit lower, so we're probably at really peak power going to have to supplement with the power that we can discharge from the batteries, which at standard discharge rate, we can even discharge them at a higher rate, but we try not to, so they last longer, is 57 watt hours. Yeah, and I've talked about the rest of it a little bit earlier, so with that, I will wrap it up. Is there any questions? Okay, I don't know if there's any in the chat. Yes?
You said you have 9 solar panels in series or 9 cells in series?
Yeah.
And and that gets you your 16 volts that you need to charge the battery.
Yeah, 16.8. So if we do, like, we're originally going to do 6S3P, and that would have only given us like 14 volts, which is like a bit too low, and then that wouldn't have really worked with the MPPT chip that we have. So with 9 in series, we're able to have like an even number, for like the number of cells in series and in parallel, and that gets us like 21 volts or something.
Okay.
Yeah.
Does that assume that you're getting the same like voltage from each solar cell?
It does, yeah.
Okay, so you would have to basically like point your satellite in a specific direction to get
Yeah.
the voltages to charge.
Yeah, so that's for sun pointing.
Okay.
We're also in the midst of, sorry.
Sorry, I was gonna say, what happens if you spin? Because I know that if you
Yeah.
connect solar cells in series and like,
Mhm.
say one of them is getting no power,
Yeah.
all of those other ones won't give you any voltage.
Yeah.
But you get no voltage throughout the entire loop.
So actually, yeah, we have bypass diodes on each of the solar cells, so that if one goes down, like we can still access the other ones. That's a really good point. That is something that can happen.
Okay.
Yeah. Oh, yes.
A few things, minor, supposed to read your stuff that I'm going to talk to you after.
Perfect.
Cells, are you getting kicks or are you getting their cells?
Wait, kicks?
With a couple glass.
Oh, no, I think we're just getting bare cells. So yeah, the assembly is something we have not exactly planned out yet.
Recommend getting it with cover glass. Cells are very
Okay.
fragile, but
Yeah.
but recommend getting it with cover glass.
Okay.
Also, what should be time with cells? Right now, cells, cell lead times are very long.
Oh, are they?
In particular, there's a global cover glass shortage. Exactly why not?
Of course.
It's worth looking very carefully at your power and energy budgets and doing some timelines. So there you go. If you can show yourself to be power positive and stable, that is very helpful because if you're positive and stable, then you can be positive in all involved. You might get a bad duty cycle if you have to spend a lot of time recharging your batteries. But is there a reason why your bus voltage is so high?
Well, as I was mentioning before, because the charge voltage that we need to charge the pack is like at least 60. 4 cells in series.
Why not two series in parallel?
Well, the original reason was I can't remember at this moment. I'll get
That's not usually high voltage for
Yeah.
this small. And in particular, you'll notice it's driving things like your solar panel design.
Mhm.
If you have a straight buck.
Right.
Also,
That's
it's
true.
a very minor thing. It's a 1 year mission. If your depth of discharge is only 10%. It's a lot.
Yeah. Yeah, and I think we're planning like a 20%.
Adding problems that you don't.
Okay, so we don't need cell
I
balancing.
mean, it's worth it. You have to evaluate it, but
Right.
This is a fairly short range.
That's true. I guess like the main concern was that the storage time is going to be like 6 months at least, so we weren't sure if they would get like pretty unbalanced in that time.
Match them beforehand.
Yeah.
And keep them matched.
Mhm.
And don't abuse the pack.
Okay. Sounds good. Yeah. I don't know if anyone else has. Yes.
Thanks for the presentation. I might have missed it earlier, but I was wondering about the overall failure scenario. Yes, from OPC standpoint. We see that OPC as a watchdog. Yes, seems to have its own MC called load switch.
Yeah.
I'm wondering what the failure mode of operation is going to look like if, say, one of these two boards fails, and how they would cover each other.
Clarification, OBC and EPN microcontroller is the same thing. It's on the OBC board.
Right.
Yeah, but that's a good question. The way we designed it is that we are able to, I think, yeah, I mean, all the fuses are automatically enabled. So even when, we're in LEOP, the power should automatically flow, especially because the depth switch will be, turned off. So, but yeah, we can definitely talk later if you have like more specific question with that.
I think the one other thing is
Sure.
maybe you want to talk about it as well, but what's the reason for like regulating one board and then distributing over wires versus point of load regulation for some of the bigger rods like the ADCS?
Sorry, I can't really hear what you said.
It's why do
Yeah.
one regulator
Yeah.
versus like point of load regulators for like high?
Okay, I'm not sure if I understand your question, but okay. I mean, I can't really hear the question, so I'm not sure what the question is.
Why do you have one big regulator
Yeah.
instead of having a separate regulator on like the camera
Oh.
that's got a big load?
You mean like separate like buck regulators?
Yeah.
Yeah.
If you have like a wire going across the whole thing, there's some delay.
Sure, you mean like having, yeah, okay. I mean, that is something that we considered, and then we ended up, deciding to do one central buck and then just splitting the power that way because it seemed, a bit simpler, but it's definitely something worth considering, like the amount of like inductance or resistance that we're adding by doing it this way, which isn't something that we've calculated, so that's, yeah, definitely something we could look at. Yeah. Yeah. Any other questions? Oh, perfect. Okay, I'm not sure. Okay, that's link budget, never mind. Okay, are there any other power sources on the satellite besides the main batteries? Is there a backup battery for a real-time clock? If so, have you planned for how to disconnect its power with the RBF and or deployment switches? No, we don't have a backup battery right now. Yeah, we do not have that. We just have the main battery pack. Yeah. But that's an interesting idea. I'm not sure if that's necessary, but we'll talk about that after. Okay, if EPS elect ends up having too much complexity and not enough time people to implement everything, are there any features you could deprioritize and scale back on? I mean, a lot of them, I think almost all of them are essential. I think the only thing that we could scale back on is maybe like some of the telemetry. Yeah, I mean, otherwise, it's a pretty simple system. I mean, like we have power regulation and we have, battery monitoring, which are all like really important. Yeah, I think another thing we could do, or another thing that we are considering is to put load switches like directly on the boards to which they're delivering power. But again, like that's something that's going to be the same for every board that needs power. So, yeah, I don't know if that answers that question. Anyways, yes. Anything else? Yes.
We have time, I'll just ask, but I was
Sure.
wondering about the umbilical connections.
Yeah.
You mentioned having like a multiple levels.
Yeah.
Is there a reason you have a box for like umbilical versus non-umbilical? Like, is this just for testing when the whole thing is assembled?
Yeah. Yeah.
Because yeah, I mean, if you're testing on the bench, you could definitely have like a resistor, you just like solder another way so that it doesn't like fail on orbit by accident.
Sure.
Like an extra part, but like, I definitely want battery power like on orbit. So
Yes. Okay. Interesting. Cool. Other questions? Okay.
Help yourself.
Good. All right, cool. Yeah. Here, yeah. Come. So yeah, hi everyone. Thank you all for coming to the firmware part of the presentation. I know it's been a long day. It's 2 p.m., but I appreciate those of you who stayed so far. For those of you who don't know me, my name is Issa. I'm currently the firmware design lead for Utah Space Systems. I've been the lead for the past 8 months now. And so yeah, we have a lot to get through today, so I'll try to speed along as fast as possible. But the format of the presentation is pretty much the same as what you've seen before. I'll kind of go over the team, who we are, what our areas of responsibility are. Then I'll cover the requirements, kind of the things we have in the back of our head while we're doing our projects, what we use to kind of create our designs. Then I'll quickly go over the architecture, particularly what firmware's focused on. Then I'll cover some cool projects. We have a lot of things going on, so I won't be able to cover everything, but I'll cover some of the cool ones we've been working on, both technical and non-technical. And then finally, I'll go over our future plans, what we're looking at when we're closing off Phase C, as well as moving into Phase D. But without further ado, who are we? Well, firmware operates pretty interestingly. We operate alongside 2 other subsystems as part of a group of 3 that are all focused on the design and development of the entire software architecture on the spacecraft. Now, each subsystem is focused on a different part of the software. And what firmware is focused on are the low-level drivers on the microcontrollers that Reed talked about before. So anything for communicating between the subsystems, interfacing with different peripherals, anything like that, particularly on the spacecraft bus for like the OBC MCU. Now, there's 2 other subsystems, command and data handling and payload firmware. I'll let them introduce themselves later. But being integrated with these 2 other subsystems that are also working on the software allows us to have a team like this. So we have a huge roster. I think we just have under 20 kids. And the special thing about 20 adults, minus like the first years who might still be kids. But what's cool here is that if you're a firmware member, that means you're also a CDH member, and that means you're also a payfirm member. So members can switch between different projects however they please and get a mix and match of different experiences of the different types of software on board, because we do work with different components and then different levels of the software hierarchy. But now that you kind of know who we are, I'll quickly go over our requirements model, particularly what firmware's requirements are, just so you have an idea of what we're working with before I get into our actual architecture. So the main high-level requirement that governs is pretty much like the birth of the entire firmware umbrella, all 3 of those subsystems, is FINCH firmware platforms, which essentially just says we need to have software on the satellite to control the satellite. Now from that requirement, a child requirement is firmware interfaces. That's where I come in the subsystem I lead. Firmware interfaces basically says that we need to have some sort of mechanism where we can communicate between the different subsystems, particularly when it comes to OBC communicating. And that's kind of the 4 requirements at the bottom that you see: PALEC, ADCS, power, and RF. Those are the 4 main subsystems that we want to communicate with. We want to be able to send commands to them. We want to be able to execute commands. And then we also want to be able to collect data from them to get an idea of what's happening on the rest of the satellite. Some other requirements we deal with, one important one is telemetry storage. So we want to be able to store telemetry on the NOR flash that Reed was talking about earlier. But the idea is, how much of that memory do we need? That's something we've been investigating. I'll talk a little bit about that later in the presentation, but that's definitely a requirement we've been working on a lot. And then finally, remote programming. So because of our operations, we want to be able to remotely program the satellite while it's still in space. So we want to have some sort of mechanism where we can receive a firmware image and then be able to upload that onto the MCUs. So these are just some of the requirements we're working with. It's not all of them, but it's kind of the higher level ones that'll give you a good idea for what our design looks like. Now, the diagram I'm about to show you, it's going to look a little goofy. And the reason why is that our diagrams are kind of all 3 subsystems put together. I've tried, for this presentation, I've abstracted away anything that's CDH or payfirm related and specifically focused on firmware. So that's why it looks like this. So it's really empty, but I'll kind of quickly cover some of the main ones we're working with. So if we start at the top, the storage service and the time service. So the storage service, before I actually get into that, so all the green boxes represents RTOS threads, and all the gray boxes kind of represents just like libraries of functions that other threads have available for them in order to do whenever they want to do. So the storage service is kind of what are the drivers that connected to the NOR flash, the SPI memory module that we have on board that can store all of our telemetry data, log files, things like that, anything that's not the image itself. The storage service provides the drivers so you can read from that memory, you can write to that memory, things like that. The time service isn't its own thread, but it's essentially other threads might need timestamps for several purposes, such as logging or scheduling commands. The time service is connected to the real-time clock on board the MCU, or connected to the board. And it'll be able to read an accurate measure of the time directly from the RTC and provide that information to the other threads if they ever want it. But the 4 core threads that we really deal with, especially when it comes to firmware, is that PLC handler, the EPS handler, the RF handler, and the ADCS handler. Those are kind of our 4 interfaces. Those are the threads that are in charge of if the command service, the main central thread that is like governs the operation of the satellite, if it wants to communicate with those subsystems, be able to issue commands, or if it wants to read data from those subsystems, those handlers are what kind of facilitates that communication between them. And as you can see, it's a mixture of either communicating over the CAN bus or over the I2C bus. And then we also have one more thread on top for remote programming. Again, if the command service receives a firmware image from the ground and that we want to upgrade our software, that thread is responsible for doing that whole operation. And so yeah, that's kind of what our system diagram looks like, but I want to kind of expand into what our handlers are, because the handlers really are the core of firmware. So start off with ADCS. So the ADCS handler communicates with the ADCS 10M module. Because of the design of the ADCS 10M module, it kind of makes things really easy for us. When we're communicating, all we really have to do is kind of specify a reference frame, send attitude quaternions, select a motor operation for the ADCS module, and that's kind of pretty much all the things we need to provide, as well as collecting data on the statuses of the different sensors on the ADCS module and things like that. The power handler is a little special. It communicates with both the BMS and the MPPT chip. It kind of facilitates that communication that Aurora was talking about earlier for operations such as charging the battery. It reads all those signals coming from both chips and is able to kind of coordinate those different operations. The RF handler, similar to the ADCS handler, just communicates with the RF module. Again, because of the way the RF module is built, it makes our life easier. We just need to obtain any uplink messages, forward that to the command service so that it can read what we've sent to the satellite on the ground. And then if the command service wants to send anything to the ground, the RF handler will be able to send that information to the RF module, as well as read data from those telemetry sensors. Finally, the PLC handler is kind of a special one because it communicates with another MCU. It communicates with a payload MCU, and it forwards commands sent to the handler by the command service for things like image acquisition, and it's able to read data about things like compression status and information like that that it can then pass on to some of the other control threads. So those are essentially, that's kind of a pretty high level overview of our entire system architecture. Now I think we'll kind of go into some of the projects I've been working on. Again, like I said, we can't cover everything because there's just too much, but here's some cool ones, both technical and non-technical. The first project we'll present is a little bit different. It's actually kind of outside the scope of firmware. It deals more with the payload. So the payload has a camera and it has an SD card. Reed mentioned that there was a little bit of a problem that we needed to transmit a lot of data at a very high speed. So I'll let Vlad, a general member on firmware, kind of talk about how he's been dealing with this problem for the past few months.
Thank you. As you know, my name is Vlad, and I'll be presenting the SD card project and its progress. So the main issue that we were faced in this context is that there's not enough space on the H7 board to store the data cubes in between downlinks. So how we do that, how we solve that problem is, as you know, using an SD card. So how the process works is that data is going to be coming from the camera, and then this is then written onto the SD card, and these read and write operations are going to happen pretty much simultaneously thanks to the ping pong buffers that we plan to use. So these are our prototype projects. On the left is our image storage project, which uses an SD card and a H7 board. So we use this project to validate read and write speeds, which I'll get into a bit later. And on the right are the fruits of our image capture project. So on the top, you have our first ever color picture of the project. And we use an OV7675 Arduino camera to kind of get used to and familiarize ourselves with the DCMI peripheral that is used to sort of receive image data and handle it. And yeah. And then for the current state, so the SD card has a theoretical write speed of 25 megabytes per second. And so far, the best achieved write speed is 23.9 megabytes per second. So one issue that we have is that this goal of 23.9 megabytes per second, or this level right now, is not being achieved consistently, which we think is due to a bad clock signal, which might be caused by the quality of the wires that we're using in our prototype project. So obviously some more investigating is going to be needed to figure this out. And then another issue is our goal is 30 megabytes per second. That's the level we would like in order to be comfortable. And as you can see, that's greater than the theoretical maximum speed. So we'll probably have to enter the realm of voltage conversions in order to squeeze a little bit more speed. And then finally, so although we did kind of create the architecture for the image capture with the Arduino camera, we do need to make some more adjustments so that the FLIR Tau camera is 100% compatible with the H7 board. And once all of that is done, hopefully we'll be able to get the entire system working, and we'll have a picture on the SD card. Yep. Thank you.
Thanks. So yeah, that was a good example of kind of the type of work that we do in firmware. Kind of, that was with the payload, but we have kind of similar projects going on with ADCS and RF and things like that. But contrary to popular belief, we're not just code monkeys. We actually sometimes do non-technical work as well. So if you remember, I mentioned earlier about a telemetry storage requirement, being able to figure out how much memory do we need on board in order to store the telemetry data, log files, things like that. But in order to figure out an answer, we need to determine how much data actually needs to be collected by each of the subsystems. So to figure that out, we have this data budget project, which essentially does exactly that. We figure out what data is needed by each subsystem, how often do they need to collect like new measurements, how long do they need to store it, things like that. Now, we did this project last summer, and kind of our approach last summer was we essentially went to each subsystem and we asked them each of those questions. We asked them, what data do you need? What data types do you expect that data to be? How often do you need to collect it? Things like that. But the issue with asking questions like that is that we were asking these subsystems questions about our own domain, when in reality, they weren't really focused on that and they didn't have answers to those questions at that time. Before then, we were still kind of earlier on the project, but even now, they still technically might not have those answers. When we revived the project this summer, and because of that, like, the project did not work at all. Like, we didn't really get a good answer from anyone on anything. So our approach this time was different. When we revived the project this summer, instead of asking each subsystem questions about their own domain, or about our domain, we instead interviewed each subsystem and actually understood the projects they're working on when it comes to their own work. I got a sense of their different operations, what are they focused on, and the part that they play on the satellite, and then use our own expertise and knowledge on how this kind of stuff looks like in code to then estimate the data as required based on the answers that they gave. So we kind of came up with our own estimates in terms of how much data they need, things like that, and then we kept those subsystems in the loop just to make sure that we stay accurate to their operations. And because of that, our answers were a lot more fruitful this time. As you can see, that's our current table right now. It's pretty empty, but it's more than what we had last summer, which really goes to show how badly last summer went. But now our next steps for this project is to kind of follow up with each of the subsystems, because at the end of the day, we're kind of learning as we go along how we're going to approach this and the different types of questions we need to ask so that we get the most valuable information. Essentially, we want to follow up, fill in those missing boxes, and then we'll have a good idea of how much memory we need on board the satellite. And then when we develop kind of a higher level flight code with our housekeeping services and things like that, we'll know what to pull for each subsystem, get what kind of data we need to get from them. So that essentially covers some of the projects we've been working on in firmware, but I kind of want to cover next steps as well, what we're planning on finishing in the next few months when we're closing off Phase C, and also kind of the plans we want to have in place before we fully transition into Phase D. So closing up Phase C, our end goal is to complete all the low-level drivers and then validate them through software unit testing. So I kind of divided it up into these 4 batches. It's not necessarily that we're going to complete these things sequentially. This is kind of based on our current progress and the current status of each project. This is what I anticipate will get done first, and second, and third, and fourth. So the first stuff that we're probably going to end up getting done is first we're going to complete the ADCS emulator. Now, what the emulator is essentially for the ADCS interface, we want to have some sort of secondary device that we can test on. Now, ideally, we want to use the actual module, but the module won't be here for a while, so we want to have something else that behaves like the module so that when we're testing our actual code on OBC, we have something to talk to. So what we're doing is we're taking one of our own MCUs and we're programming it to essentially behave like the ADCS module. We're almost done on that, so I anticipate that's going to be probably the first thing we'll get done starting from this presentation. We're currently finalizing kind of our software unit testing of the RF drivers, as well as kind of filling in some last minute functionality. And then finally, we're going to complete the data budget project, get a good sense of what telemetry we need to collect from each of the subsystems. The second batch of things I anticipate we get done is we're going to complete the SD card and the SPI memory drivers. So the SD card, what Vlad was talking about earlier, and as well as the NOR flash memory connected to OBC, those drivers will be done, as well as we'll finalize our software unit testing of our ADCS drivers using our emulator to test. And then finally, because the BMS board is now finally ready, we'll probably focus on that and get that done, that being the first part of the 2 power components. In the third phase, because BMS is done, we'll try to get MPPT done so that now we have both components done and we can test using test communication between both of them. And then also complete our pay-elect drivers between the payload MCU and OBC MCU, making sure we can communicate, be able to send commands, and then the payload MCU executing those commands. And then finally, once the hardware arrives for the ADCS drivers that we can test on, we'll complete that kind of testing and then also assist CDH in developing the higher level flight code, making sure it connects well with our drivers. And yeah, so that's kind of what we anticipate for phase D, but we also want to plan for anticipate completing for phase C, but we also want to plan for phase D so that we're not just running in blind. So the first 2 things that I anticipate right now, we kind of want to definitely have planned out. So the first thing is flight code guidelines. Now the code we're writing right now is good enough to run on the hardware, but the question I have is, can this code withstand whatever outer space throws at it? I don't know the answer to that yet, but what I definitely want to do with the rest of the team is research how do you elevate your code from just working on the hardware to actually being able to survive in flight, be able to withstand all these unpredictable scenarios that we might come across. And then secondly, integration testing. So when we integrate the firmware drivers with the payload firmware drivers with the CDH code, how can we test all those systems together with all the hardware connected? How can we kind of simulate these unpredictable scenarios and then validate that indeed we can rely on our software to withstand all these problems? And that pretty much covers the roadmap. And that also concludes all I have to say for firmware. I'll open the floor to questions. Rip me apart. Yeah.
We're in the software world now.
Yeah.
So, okay, a bunch. I lost them all the time, so I get other people's space. But first one is, you guys have unit testing that you're doing now. Have you built a pipeline to manage regression testing? As this program is like a long program and there's going to be a million people churning through.
Yeah.
What's your CD pipeline?
We currently don't have one. I know we talked about that a few weeks ago. That's something definitely next on the list is start developing once we're kind of confident in our unit testing. But that's something on our radar for sure to get done.
Okay, and then related to that, this one bit additional is you listed integration testing as your work for the RSD. And integration, in the way you described it, involved integration into the boards and so hardware and load testing. Is there a plan right now for virtualized testing of the software pieces at firmware level or above down the road? But for testing, we would call it acceptance testing, but effectively testing of the functional behavior across multiple units. Unit testing is really granular and doesn't necessarily allow you to do regression testing of the actual behavior of the system, whether or not you're on hardware.
Yeah. So I think that's kind of what is like the first step. But when it comes to integration testing, like right now, we are trying to just go for the granular thing, make sure just our individual components, even like the super small ones, work properly. But yeah, next step is once we start kind of putting things together, is figuring out how we can test all these components together and kind of, get it working like that. Yeah. Yep.
When your code is flying and software's going to run it, the OBC crashes. How do you start?
Yeah, so I'm gonna let CDH talk about that because we have a whole section on fault handling. We have like a whole plan for dealing with several of those issues. So I'll hold off to the next presentation because that's a whole section. But yeah.
And so this is a more general directed question because as someone also working on the SD card project, I wanted your input on implementing some sort of software ECC memory for the SD card. So error correcting code. So this would have some sort of redundancy for different parts of the memory. And so if we do find it on like
as we do a read or write test, right? We find that something's wrong, we can just correct it. So is this like, are we like, for the SD card, is it just fine to do just a hardware like RAD hardening, and just leave it at that, or should we also implement an extra level of software?
So modern identity flash has both layers of built-in hardware ADCS because the cells still have 3 electrons, and sometimes those electrons so I would not problems I've seen with memories is they literally just stop working. Like it's not like you get a bad bit out, it's just they don't respond to command.
I think we have some questions. I'm going to answer some questions online. Sorry. So I think this is for you, Vlad. For Bruno says, for this clock quality issue, have you probed it using a short ground loop on your scope probe? Are you sure the bad quality is from the system itself and not your measurement?
Yeah, so first, the main issue is that we were trying to run a 20 megahertz signal through a breadboard and some fly wires. Like that's, there's not a lot you can do about it. Definitely some issues with measurement possibly, but we are building a actual PCB dev kit to alleviate these issues because clearly we can't hit 50 megahertz on the breadboard.
Also, you know, the vendor may be lying. Would be the first time over the last.
Yeah, we do have, you know, SD cards from multiple different vendors. Hopefully we'll find one that is less of a liar than the others. We'll see.
Honest people. Cool. I think Bruno has something again. Oh yeah, does the company manufacturing the ADCS module have some sort of emulator engineering module you can test with? So yeah, recently found out that the company can provide like their own kind of emulator similar to what they're doing on an MCU. But the lead time on that again is kind of long. So I think the module itself is coming sometime next year. This emulator, Kang would mention, is probably coming like October-ish. And we kind of started our own emulator project before that. So the plan is kind of, yeah, we use our own emulator for now because we're almost done to start off the interface. And then once kind of the actual company manufactured emulator comes in, then we'll be able to more high fidelity testing and be able to kind of do some work before the actual module comes in to like fix up our code so that it works more with the real thing. But yeah, that's, yeah, so they do provide some sort of emulator. Regarding flight code guidelines, do you have any specific guidance from the launch provider? I don't know if the launch provider provided any flight code guidelines, did they? Yeah, no, they didn't. So, yeah, I think it's kind of our own, yeah.
Two things on that. One is for a flight guideline thing, a suggestion
Yeah.
more than anything,
Yeah.
is NASA publishes and the ESA publishes and CSA, I don't actually know if they have, publish it. Actually publish guidelines on coding standards for space operations or things like that that can be leveraged and pulled in for reference. They're also just generally the standards practice writing in the language
For sure.
know where you're at. Usually good practice to pull in.
Okay.
To make sure to reference it, plus it provides some sense of onboarding material as you bring more people on the team and if there's churn, it's like, cool, this is the standard code to we check against them. The second thing is, and this isn't exactly part of the CD pipeline question, but maybe future thing, what's your code documentation look like? There's an assumption on the line that there is.
Yeah, there's documentation, yeah.
I said the quiet part loud.
Yeah, we're figuring that out. I think we're currently, we have some sort of documentation when it comes to our test plans, like a solid format that we all kind of follow just to make sure that everyone's testing to the standard we want to. When it comes to the physical code, I think we're still kind of up in the loop about what we want the documentation to look like. Right now it's kind of just like, just throw whatever you know into the Notion page.
I'm definitely asking like software engineering versus software cowboy coding questions.
Yeah.
So like that in mind, do you guys do merge reviews?
We do.
You do?
Yeah. We have that. Yeah.
So two things actually just written up that. So first guidelines, GPL also excellent, very terse, very pragmatic guidelines.
Okay.
They're a big board organization, but these are really good. And the other thing is what you're solving situation. Can you say at any given point, right now it's early, you're doing dev board stuff.
Yeah.
Like, we ran this test with this version of software built with this compiler. Because when a few months down the line something's not working and it's used to work and it doesn't work anymore, can I go back to previous configuration and get like bit for bit software on there that try to repeat what it is I have?
In terms of like version control, you're talking about?
Yeah.
Yes.
Configuration control in general.
Well, I think right now everything we have is on Git. In terms of configuration control specifically, I don't think we have anything for that. But everything that we have, including the MCU configurations, like the IOC files, are all hosted on Git. So theoretically, yeah, you should be able to kind of go back to.
You also need to record what it is you program.
So this might actually just to that point give again suggestion space.
Yeah.
Because if you're not already using tagging, if it gets your underlying system, if you're not using tagging for major version control, whether it's semantic versioning or otherwise,
Okay.
Do you start using tagging? Do you start using release notes?
Okay.
Because that is how you can effectively trace back to what the major milestones were.
Yeah.
And even code thing. Otherwise, you're going to be looking at hex data for the different commits, and that's a nightmare. So,
Yeah,
so just leveraging those tools helps with that on the systems you chose to use, which are already really great systems to use.
Okay, perfect. All right, cool. Thank you. Yeah, for sure. I think that kind of answers Bruno's question. Do you have a system method of documentation? Cool. Will you be open sourcing the ADCS emulator your team is working on? Yeah, I mean, I think currently all our code is technically open source. It's open source, right? Yeah. It's a crappy emulator. I don't know why you would use it, but like, yeah, sure. We will be open sourcing that. So yeah, everything, all the code we write is technically open source. It's available on our GitHub page. But yeah, I think we have more questions. Yeah. Let's go.
Okay. Two things. First one, I like the way you structured your data budget project. It's a good idea to be like, okay, well, we know this a bit better, but they know what they're doing.
Yeah.
So I like the way that you set up that project. It's a good idea. And the second thing, what is your, I guess moving away from general software stuff, your RTC that you mentioned you had, how are you syncing that? Like, what are you doing to make sure your real-time clock is actually tracking real time? Do you sync it with the GNSS? Do you just use ground commands?
Yeah, so I think we were talking about that like literally last week, and I think we'll probably end up using the GNSS to sync that up. Yeah, we're still like, we're not finalized on that yet, but I think likely we'll probably just use that just because we have that available.
It's a good idea.
Yeah, and I think you had a question. I think last one because we're running out of time.
Earlier, you guys were talking about software upgradability in orbit.
Yeah.
So it's one of the things that you should get done early on as well. Bootloaders.
For sure, yeah.
Consider how your failure, what happens when you have power failure during halfway through an update or loss of ground link. It's a challenging thing to get through.
Yeah, we're currently working on remote. Our Mirai, he's not here right now, but he's currently working on a remote program right now. We've been looking at that for a while. But yeah, cool. Thank you.
In particular, once you have that, and as soon as you have that, you should deploy your software development and code via that.
Okay.
That is how you will test that.
Nice. Okay. Interesting. Okay, cool. Thank you. Yeah. But yeah, that's it. Thank you for listening. Appreciate it. There we go.
Okay. Hi, everyone. My name's Khalil. I'm the lead for Command and Data Handling, or CDH. This is a new team. We kind of split off of firmware just to split the responsibility in a more organized way. And yeah. Again, this is our team. Like Issa said, due to the nature of the CDH firmware and the payfirm tasks, a lot of these members move around. And so they're not just CDH members, but they all fall under the firmware umbrella. And these are the people who have been helping us with our tasks. Over the next 20 minutes, I'll be going over the requirements model and the system architecture that it's informed. This includes the hierarchy of our hardware and software frameworks and how they've been used to implement our modes of operations functionality and the overall system diagram. Then there's the integrity of both the data onboard the satellite, the data that's being communicated between the satellite and the ground station, as well as the integrity of the running program and how we're going to deal with possible hiccups in space. And lastly, I'll be talking about our team's next steps as we transition out of our current design stage. Our requirements model basically formalizes our team's objectives, And these are the tasks that our team needs to complete in order to ensure correct functionality of the spacecraft when it comes to command and data handling. So first is our operating modes. This is the spacecraft's ability to determine its state and use the current values of our parameters, such as the location or charge, to determine whether to transition to a different state or operating mode, as well as the steps needed to transition to that state. The real-time operating system, or RTOS, is the way we'll be setting up threads and communicating between those threads on the satellite. And then the network layer is placed above the RTOS, and this takes care of communication between the MCUs, as well as some data transfer between threads on a single MCU. Command format is the structure that we'll need our commands to be in order to relay all the necessary information, arguments, and priority levels so our MCUs can queue up tasks and transition between the states correctly. And this is to be used by the network layer. The flight software is the highest layer, and it's meant to support the spacecraft's overall functionality. And this includes all of our services, such as the housekeeping, logging, and command service. And all of this ends up being related to the telemetry to RF requirement, which is how we'll be communicating with the ground. This requirement states that all our telemetry, such as the housekeeping data, must be organized, packaged, and downlinked down to us through the RF module. Moving on to our system architecture, this will be all the layers of our software frameworks and how they'll be interacting together. Firstly, everything will be running on our microprocessors. These are STM32 ARM chips, and they'll be running a real-time operating system called FreeRTOS. And all the OS-related calls will be made through an OS API called CMSIS RTOS2. These two layers are natively supported by our MCU through its development environment. Next is the network layer. We're using a framework called CubeSat Space Protocol to implement the communication layer between our MCUs and supported hardware, as well as data transfer between threads. And lastly, the highest layer will be UTAT-specific codes, such as the services, housekeeping, and logging services. The main part of our system is the modes of operation. These will be the states that the spacecraft is in when working to complete a current task. They're split into two categories, follow-through and passive modes. These modes have a priority levels, and so passive means that if the current state is passive, it can be paused and another higher priority mode can take its place. For example, if we're in charging mode and the command service asks to switch to processing mode, because processing is a higher priority mode, charging can be put on hold and the MCU can transition into processing mode. Follow-through means that if the current mode is follow-through and has not finished running, even if a higher priority mode is requested, it can't pause it. This is needed for modes that are strict on time, like downlinking, where we want nothing interrupting its processes. The follow-through and passive functionality of these modes is supported by the operating system synchronization features, where a third thread is used to ensure that no follow-through modes can be interrupted until it's finished running and exited. We move the responsibility of starting and stopping the follow-through threads onto a third thread to ensure that the current running thread finishes its very, very last instruction before the next one can start. Back to our systems diagram. Our modes of operation are controlled by our command service, which is informed by our parameter table. Here, all the relevant details of the spacecraft are collected, stored, and updated, and then used to decide the spacecraft's current mode of operation and then its next mode of operation. Beyond just the parameter service, our logging, storage, and time services are used to save snapshots of the system's current state, which will be downlinked to us periodically. Overall, all levels of our software come together to facilitate communication between our MCUs through our data buses and the sending of commands through our handlers to our external modules. As you can see on the Payload MCU, the one on the far end, it'll be running its own set of modes of operations, which are informed in a similar manner. Our code has a lot of moving parts and even more moving data. And so it's important to ensure that the program runs correctly and that the data is not altered. In space, the risk of radiation affecting the integrity of our data and programs are non-negligible. And these are called single event effects. Of our two main worries, single event upsets are basically bit flips, where radiation can cause a 0 to become a 1 or a 1 to become a 0 when transferring data or in memory. These can be solved by refreshing the affected memory or resending the data, but the difficulty comes from detecting these flips. Our other worry is single event lapse-ups, where a bit can become stuck in memory. This can be fixed by removing power, and if it's not done in a timely manner, it can cause permanent damage to the IC. Therefore, we need mechanisms in place to detect and correct these errors when they occur. Firstly, our two main data buses. The CAN communication protocol has built-in error detection mechanisms. These can let the sender know that the data received on the other end is incorrect and notifies the sender to resend the information. Our second data bus, the I2C bus, doesn't have anything built in, and so error detection methods must be incorporated into the data packet. This can be done through systemically padding the data, so we can either detect errors on the other side and request for the data to be sent again, or we can correct the errors on the other side. Outside of the satellite, the integrity of ground-to-satellite commands must also be ensured. This can be done by utilizing a digital signature through SHA-256 hashing. This hash function maps our data to a 256-bit string, which is sent along the data or alongside the data. Due to the nature of the hash function, a small change in the input, even 1 bit, can result in a huge change in the output, which is the 256-bit string. The input or command might be damaged when it's sent, and a bit can be flipped. If that happens, when the satellite receives the command and runs it through the hash function, a vastly different string is outputted. This is called an avalanche effect, where a small change in input can cause a huge change in output. So a command is sent alongside its hash, which is computed down on the ground, and then the received command is, again, run through the hash function up on the satellite. The two hashes are compared, and if they match, it means that the command that we received is correct. Lastly is our program integrity. We have a 3-tiered approach that utilizes a software watchdog, an internal watchdog, and an external watchdog. Watchdogs are basically timers that can be reset by a program to their initial countdown value before they hit 0. If they hit 0, they can kill a process or kill the power. These are used to ensure that a program doesn't hang. Our software watchdog will be a free RTOS thread. This thread will monitor the current process and ensure that they run within the allotted time. If they don't, it means that they're hung and the process will be killed to allow other processes to run. Our internal watchdog is hardware, and this is managed by our software watchdog. This timer is in hardware and sits on the MCU itself. If the dog isn't pet within a certain amount of time, it'll restart the whole MCU. This is basically used to watch the software watchdog in case that was unable to manage the hung thread on the processor, or if itself is hung due to a single event effect. Lastly is our external watchdog, which is also managed by our watchdog thread on the MCU. This is external to the MCU and is capable of causing a system-wide power reset. This is our last line of defense and can make sure that no part of the system hangs or fails. Basically, our overall approach to troubleshooting is, have you tried turning it off and on again? Okay. Next steps. Over the past few semesters, we've designed and implemented a lot of the requirements of Phase C. As we finish up, here's where we stand. Our OS and network layers have been finalized, compiled, and used to write programs that'll serve as outlines in how our modes of operations will work and how our threads and MCUs will communicate. We figured out all the nitty-gritty gross code stuff, and it's ready to be used. We're in the process of developing our UTAT services, which, if you remember, is our highest layer of code. We're also making use of our data buses alongside our network layer to get CSP working over the CAN bus instead of hard coding the CAN communication ourselves. And lastly, our internal watchdog, which is the one on the MCU, has been tested, and all that's left is determining timeout ranges for our processes. To finish up the phase, we need to get the software and external watchdog timers working, as well as our ground communication verification system. We also need to extend the data detection or correction support to the I2C bus. Thank you.
So a quick one on the systems diagrams you showed. It may well be a simplified diagram, but the state system or so it would seem, the point between the
I can go back to
but effectively the selector or the command handler, that's it. Command handler between modes, and you mentioned that the passive modes can be interrupted, whereas the follow-through cannot be. Right? So what is is there a defined fallback strategy for when a passive mode has been interrupted, an operation has been interrupted to do something like downlink? Does the command handler automatically then bring back what was left to be done on the original thread? Is that complete, or is the default behavior, I abandoned that thing? I'm going to restart it.
Mhm.
Or not at all.
So this is all taken care of by the scheduler on the OS.
Can you repeat the question?
Oh yeah.
Sorry.
So because our modes can be interrupted, basically how are they resumed or are they resumed? Our operating system scheduler takes care of all of that. So these are running threads. They're all concurrently running. Our command handler will start a thread. If a higher priority thread is started, then it can preempt the other thread. The way that the follow-through functionalities work is actually they'll start, they'll hit their first command, and then they'll try to grab a semaphore, which is a synchronization variable. They'll see that another follow-through thread already has it, and so it'll just stop running. So the threads, even if they're paused, they're still running. It's just the MCU will basically ignore them until the scheduler allows them to run again. So it's all taken care of by the OS.
Does the OS then, are you building in a thread pool to manage like the maximum number of interrupts that can happen? Or is that managed kind of by the OS and memory kind of behind the scenes?
Yeah, it's managed by the OS. Yeah, it takes care of a lot of the stuff behind the curtains. Any more questions? Yeah.
The previous UTAD mission, Heron, did you reuse any of their CDH architecture, any of their initial coding, or was this all from scratch?
I haven't actually read any of the stuff that Heron did. A lot of the decisions were made by the previous lead, and I just kind of went along with it, like the free RTOS stuff and a few of the frameworks as well. I probably should look at how Heron did it. Do you know if they did anything different?
Not specifically this. I'm just there's no right answer here. It's just a general question. Like I was wondering actually about the free RTOS, if that was like we've done this before. Is reasonable justification for picking something? Yeah, was this prescribed to you, or was this?
Yeah, this was chosen by the previous lead. There was a lot of research done on it, so I took it as a given.
Cool.
Yeah, I think when we kind of decided all this stuff, we didn't really like take into account Heron too much. We kind of just kind of start from scratch and did our own research outside of what we did for Heron, just to keeping in mind kind of the lessons learned, but at the same time trying to like start fresh and see what new things we can explore and what's kind of like a new approach when it comes to software development. It's kind of like an experiment to see, because I think this kind of strategy is a little bit more complex than what Heron did. So just trying to experiment just to see, does this make our lives easier, and does it allow us to do more complicated things that we weren't able to do with Heron. So kind of, we didn't really take too much inspiration from Heron, besides like absolute things don't do kind of stuff. This is like a new, just from scratch, just for our own experimentation.
Yeah, that's cool. Give all of you guys an opportunity to
explore it.
Yeah.
The answer to this might be no, or this might be the wrong level to ask this at, so to speak, in terms of software. But have you guys done any work on data modeling? Or what type of messages? Are there standard paradigms you're talking in terms of messaging? Use a PBM. No, but you know. But yeah, has there been work on data modeling for what kind of messages you'll put on the bus, what the patterns or frameworks are for those messages?
No. So between MCUs, we'll be using CSP, which is our network layer. It has its own thing that comes with it, and we'll be utilizing it, but I haven't looked too much into the actual structure.
Okay, cool. My only piece of advice is the sooner you can look at data models in order to arrive at what you expect, where there might need to be adapters or otherwise transformation between the layers, the better. Especially when, in this case, it's nice that you guys are also managing the uplink and downlink route, because you don't need to change for somebody else's standard or format. But it's important to know that if there's data transformation, you need layers to handle that, and if it needs to be transformed for packaging from flight to ground, for example, might be different than it is in storage, and that's something that's really fun. It becomes a pain in the ass if you don't realize you need to transform something, and then suddenly you switch to spacecraft protocol or something like that.
Yeah, for sure.
Yeah, right now we're kind of defining our command list, and once we kind of once we figured out all the commands that we need to have, all the arguments that kind of go alongside it, and like their priorities, then after that our next goal is to kind of create like a command format, like just to kind of bitmap everything. Awesome. But we kind of first need to figure out how many commands we have, just to assign like the correct number of business to make sure we have enough space for everything.
That makes a lot of sense. The sort of add on to that then is do also consider how that data is going to be viewed on the ground, both from a commanding and telemetry standpoint, because the bit masks used to transmit data, the way in which it's structured is all good and fine, but when it needs to be interpreted on the ground, there needs to be an element of that higher level data model that describes it all, that says, well, this is what this subset of bytes means in English or language 2, 3, and 4, so that it can be interpreted on the ground, regardless of which system you build to interpret it, what applications you use to interpret it. That's critical as well. Otherwise, you're going to have deserializers before you can even look at your own data, and you're like manually apply it, which is great for MATLAB, not great for operations.
Mm-hmm. Yeah.
This is kind of maybe a follow-on. Half of it is kind of the same question, but with regards to your transmit and your receive, like when you're doing that over-the-air communication, do you know what framing and like data whitening, if anything, the transmitter itself does versus like something that you have to do on your own?
It has a couple different elements that go into to expect certain frames.
Okay, so that defines the data structure.
Yes.
Okay. Yeah, just I was looking at the HSA, like the hashing that you're doing. If you have like an error correction code on the like transmitted frame, it might not be something that's necessary. You might be able to get away with something simpler. I don't know how much processing power like doing a like actual cryptography, like proper cryptography, like hash on your data would take. And it might be a case of like you could save a lot of processing power or something. I don't know for sure, but just
yeah, that's a good idea.
It's part of that too, just rectify, like if you have to, earlier part of the conversation talked about maybe the need or implied, maybe the need to chunk captured image data because it's just too big to send maybe on a single pass. And that's where I think the chunking also matters very much in terms of structuring that data, because rectifying a well-defined image format is one thing, rectifying subsets of an image format that you define is a second level of that problem. So,
Cool. Okay. I think there's any questions online. Okay. Any more? Yeah.
Yeah. So something I don't see here is you have watchdogs for kind of short-term resets, but something that you might want to consider is longer-term FDIR. So if you're, especially if you're updating firmware over time, if you don't have contact with the ground for like 2 days, 3 days, a week, you go for more and more aggressive fallbacks and resets, and even rolling back the software automatically.
Okay.
So that might be something you consider. You might want to save a little bit of state and hash that, so you know, hey, it's been quite a while since I talked to the ground. Maybe we messed up and we have to fall back.
Okay.
It's FDIR.
Okay, good idea. Thank you. Sorry? Wait. Oh, that if it's not communicating down to the ground, the satellite should be able to like kind of monitor itself and see whether it has like a fault in, I guess, like the program itself, and then be able to roll back to an earlier version if it sees that it hasn't been able to talk down to us for a while. There's something in chat. More of a hardware question. Have you considered creating a CAN transceiver daughter board to add important components using I2C like ADCS onto the CAN bus? Hardware people?
We have not. What would be the benefit of that? I don't know if you're
talk to chat.
Able to talk. Yeah, we can carry on in the Q&A.
Okay. Sure. Yeah, thanks everyone. Is this you again?
Just run real quick. I'm back. So yeah, for those who don't know me, my name is Issa. I'm currently the firmware design lead. So Murai is the lead for the Payload Firmware subsystem, but unfortunately he couldn't be here today. So I'll kind of fill in for him, kind of present the slides. He's made the slides that have been made in this section. I'm not going to take credit for them. They've been made by him, as well as Kevin, who's in the bathroom right now and will hopefully be back soon. So yeah, I'll try to answer any payload firmware related questions. I might not be able to answer everything. Kevin is pretty knowledgeable about the system. He'll try to answer as much, but if there's something we can answer, I'll definitely forward your questions to Mariah and he'll get back to you guys later. So what payload firmware is responsible for? It's responsible for the last bit of software we haven't really talked about today, and that's all of the low-level hardware drivers for the payload side. So when it comes to the SD card for storing the image data, when it comes to the camera itself, things like that, that's essentially what payload firmware is responsible for. Want to take a guess what the team looks like? It's the exact same. And so yeah, exact same team, exact same people working on it. It's kind of the system we've been going with so far. So requirements, so the payload controller payload firmware requirement, that kind of stems from the FINCH firmware platforms requirement I was talking about earlier. It essentially says we need to have some sort of software that is able to control the payload system. Under that, there's kind of three main things that we look at when it comes to the software controlling it. The first one, the one to my right, is storage. So we need to have some sort of mechanism to store the image data. As mentioned a couple times before, there's a lot of image data, 734 megabytes. We need to have some sort of mechanism where we can store all that data quickly, as well as be able to store all of that data at once. The next two requirements deal with controlling the camera. Actually, the next requirement deals with controlling the camera, being able to send commands to it, take a picture whenever we want, be able to transfer frames to memory, things like that. And then finally, any data coming from the camera, like the image, or even things like the temperature, any telemetry data, we need to have some sort of mechanism to be able to collect that data, request for it, things like that. So I'll quickly go over the system architecture. It's kind of a zoomed in view for what Khalil just kind of presented to you earlier. We're mainly focusing on the thing on the far side, that kind of PALEC board side. So starting from the top, we have a housekeeping service. The structure itself is very similar to what OBC looks like. It's kind of a condensed version. So we do have our own housekeeping service, a housekeeping thread that kind of runs periodically. It checks all the data when it comes to the compression algorithm or the storage service and the camera transfers, anything that has to do with data. The housekeeping service will collect it and then pass it on over the CAN bus to the parameter service on OBC. And then at the center of everything is the command service, kind of like the payload firmware version of it. Again, just kind of running through the payloads modes of operations. And that's particularly commanded by the PALEC handler. So the PALEC handler will receive commands from the OBC's command service, and then it'll pass it on, mainly communicating with the command service in the PALEC board. Command service calls on the command handler to wake up one of the threads based on the mode of operation it's in, and that's kind of the four things underneath it. So we have the storage service at the bottom. Again, that kind of implements the low-level drivers for reading and writing data to the SD card. Then we have the payload handler. That's kind of the main interaction, the main drivers for commanding the camera to take pictures or transfer bytes to memory, and then also be able to receive data from the camera. And then those two things in the middle, data handler is essentially pretty straightforward. It handles the data. It kind of writes things to it passes on information to the SD card. Any data it needs to pass on to the compression handler that it reads from the SD card, it can do that. The compression handler essentially implements the compression algorithm. So when we take a picture, as we've mentioned before, the picture's too big to downlink at one point. We need to compress it to a smaller size. And the compression handler is kind of the higher level thread that executes the algorithm we write for that, an algorithm we'll talk a lot about in a bit. And then finally, we have an RF handler, its own kind of like path to the RF module. Because there's so much image data, we don't want that passing through OBC. We have a direct link from PALEC to the RF module, and the RF handler kind of acts like OBC's RF handler, where it's able to pass on that image data to the RF module. So that's essentially pretty much the entire design of the PALEC, the PALEC software. Again, pretty similar to OBC, just a kind of smaller version. Next, we're going to expand on what I talked about in the compression handler. It's one of the main projects we're working on in PayFirm, and there's a lot to it. It's definitely one of the more important ones that David talked about earlier. So I'll let Kevin, a general member on firmware, kind of go through the work he and a lot of others have been doing on this very important project.
Perfect. Thank you. So this is all going to be about the compression algorithm. We know that the image acquisition process captures two 640 by 512 by 640 hyperspectral images. And so, yeah, that comes out to about 734 megabytes of data, which I'm told by RF that we need to compress to about 50% in order to be able to fit it within our RF downlink budget. Yeah, so to solve these hurdles, we obviously turn to some standards, and this one happens to be the low complexity, lossless, and near lossless multispectral and hyperspectral image compression standard, or CCSDS 123B2, CACHI. So the standard was established initially as a completely lossless compression algorithm, but recent revisions have added the near lossless as well as the multispectral capabilities. And it's also still backwards compatible. So by adjusting a few parameters here and there, you can still achieve the lossless compression, which is what we're going for in our case. So the standard is a predictive entropy compressor, and it's similar to the JPEG lossless standard, as well as the AV1 encoding standards, which are both industry practice for audio and video compressing formats. And so the encoding method selected for this standard is the Golem Power 2 encoding scheme, and so that shortens the bit length of a number using a reference to encode a shorter length. As a consequence, smaller numbers benefit from this encoding more than larger numbers. So the predictor, which is the second part of the encoder up there, is mostly designed to optimize whatever goes into the encoder. So trying to make the values as small as possible while making sure that it's still losslessly recoverable. And so it mostly uses two quantities, a local sum as well as a difference. So the local sum takes into account neighboring data values to calculate an aggregate, and the local difference uses not only the neighborhood but also previous wavelength bands to then find calculate a predicted local difference. And so this algorithm was meant to be implemented on hardware, specifically FPGAs, and so as a consequence of that, most of the operations are just additions, subtractions, multiplication, and divisions by powers of 2. And so this makes for an easy implementation on FPGAs because multiplication and division are just bit shifts by 2. So because as a team we've decided against using an FPGA, we've decided to go with a software implementation of this standard. Yeah, and so that brings us to our current progress. Perfect. So we've finished a complete implementation in Python with the predictor, encoder, decoder, and the reconstructor complete. But on the C side, we have a predictor complete and an encoder complete, but not fully tested yet. And the decoder and reconstructor are still incomplete. This is okay because we can still gather some preliminary testing results because we can use the predictor and encoder and then feed the data into the Python implementation to then validate our results after. The reason we're slowly going into a fully C implementation is because for testing results, the full 640 by 512 by 640 image actually takes around about 15 hours to fully predict, encode, decode, and reconstruct. However, on the C side, the predictor only takes around about 7 to 8 minutes, and the encoder only takes about 2 minutes to finish. So we can definitely use some more Python features like vectorization to speed up this process, but we've decided against it because it makes the translation and it improves the readability when you go from the C to the Python. And so here you can see some testing results. They're not exactly final, but this is it's a plot of the number of Voronoi seed points that I have versus the compression rate that I see. And so the general as the image becomes more and more complex, you get less encoding, less compression rates. And so we're slowly moving into some parameter tuning where we can accurately see, where we can say, okay, these are the things that we can adjust. And if needed, we will have to do some onboard parameter tuning as well, and send those down along with the encoded data. And so the next steps are to complete the C implementation, finish all of these incomplete stuff, convert it into STM32 code. And so this will be the majority of the complications, because the STM32 does not have enough onboard memory to store an entire data cube, because the data cube itself is some 300 megabytes, or well, 700 megabytes in our case, and the STM32 flash is only 2 megabytes. Yeah, so what we'll likely have to do is store everything on an SD card, and then just request pixel values as we run the encoder. Yeah, and so the current synthetic data generation models need to be switched from Voronoi to Perlin, or a fractal noise. So the good thing about Voronoi noise is that it helped us a lot with debugging. And so you can get these, because there are these like very defined boundary values, you can use that for debugging. But obviously it's not good for a real world test, and Perlin or fractal noise is more representative of what you would see in a hyperspectral image. And so, yeah, that's pretty much it. Any questions?
Not yet.
No.
All right, cool. So yeah, the next steps is essentially completing those Phase C projects, similar to the Payload Firmware's goal, similar to what Firmware's goal was, getting all the low-level drivers done. So the major kind of in-progress projects are the SD card that Vlad mentioned earlier during firmware, the compression algorithm that Kevin just talked about, and then also the DCMI DMA. We previously did it with an OV7675 camera. We want to actually do it with the Flirt this time. And then obviously getting the unit testing done of each module, and then finally getting ready for integrating the modules. And we kind of want to run a 1,000-hour test in Phase D, just to make sure the code can run for that long and be able to hand various scenarios during the 1,000 hours. And yeah, that's pretty much it for Payload Firmware. I will open the floor now to any questions.
Just in the interest of time, let's do just one question.
We'll do one question. All right, who's the lucky one with the question?
You said that your C implementation of the encoder takes about 7 or 8 minutes to complete. Is that running on a desktop PC? And how is that going to be affected by switching it to a microcontroller, which is a lot less powerful?
Right. So the desktop PC, yes, it did run 6 minutes on the desktop PC, but that was single-threaded on some 3 gigahertz. So if in a perfect world, it would just scale linearly, but it doesn't, because there's going to be some added latency, because we're now reading and writing from an SD card instead of just the soldered RAM. So that will dramatically increase our compression.
What's the clock cycle speed of the?
It can go up to 480 megahertz. Yeah.
It's like full throttle.
Yeah.
So yeah, is that it? We're just gonna do one question? Yeah, okay, cool, sounds good. All right, thank you everyone.
What do I press to get it to what button?
Left arrow. You want to click on the white space first?
Yeah. All right, so now we're going to get on to the mission operations. This will also include regulatory, but unfortunately the regulatory lead is not here and present, but he will be able to answer questions on the Zoom call. So going into our team for mission operations, this is everyone. Often the meetings can have an assortment of different characters and different people on the team. It often changes a lot, but this has been the main people showing up for the time being, and I'm really excited to share the work that we've done today. So the three main projects that we've had for mission operations is the modes of operation, the FDIR, and the ground station. I guess the FDIR is fault detection, isolation, and recovery. So what I'm going to do today is cover all three and then describe some of the next steps. So in terms of modes of operation, this is pretty much our way of determining where the satellite is, when, and why it's doing what it's doing. So I guess one thing I can do is kind of describe, this is our a good diagram to describe all the modes of operation and describe what the satellite is doing and when. So the first thing that we have is the launch and early orbit phase. That's LEOP in the triangle at the very beginning. That's pretty much 30 minutes after the satellite has finally been released from how it's been, like its transport thing. Pretty much what happens is that we have to turn the satellite on, we have to run a bunch of preliminary tests, ensure that everything's working, ensuring that everything's going as planned, and then we go into command mode. So the idea behind command mode is that once we're in command mode, our job is to get out of command mode as fast as possible and go to one of the main four modes, which is imaging, downlinking, processing, and charging. Now with these four main modes, they're kind of ranked in a certain priority, and there's going to be different system state variables that'll make us, that'll allow us to determine if we're going to any of these four modes. Those four system state variables are the amount of charge that we have, our location over the Earth, as well whether we have an image that is currently needs to be processed, and then as well if we're able to downlink at that moment. Or it also depends on stuff like our reaction wheel saturation and some other values. Now using these system state variables, we can pretty much determine which different group to go to. So for example, if we're going to be over Manitoba and it's looking like we're going to be able to image because we have enough battery, we'll go into the imaging path. Let's say we're not exactly lined up as well as we should be, we can go into downlinking. And let's say we know we're in really low battery, then we go into charging, and that'd be the mode that we choose there. Now, the key thing to do, and I think something Khalil mentioned, is that we have follow through and passive modes. So the idea, now you can kind of see the implementation of that. So for example, imaging, we've defined it as a follow through mode. And that means that once we decide we're doing imaging, we're going to keep on going through imaging until we're done the image. And the idea is like, let's say, because it's more battery intensive, let's say we're going to run out of battery, we're going to ensure that we have the right level of battery before we actually go into imaging mode. So we'll ensure that that doesn't happen. The next thing to know is that there's a safety mode. So if any error occurs, we go to safety mode, we immediately change the way that the satellite is reacting, and then hopefully we can go back to command. And then the last dot chart, the reason why it's blank is the idea is that the satellite can actually manage everything that's going on. We're going to not try to change the code, like send it up to the ground station as much as possible, but it should be able to manage everything and stay working nominally. So the next thing that we've been doing is FDIR, which is fault detection, isolation, recovery. And one of the things that also includes is the failure modes and effect analysis. So the key thing to note with this is that if the satellite detects anything wrong, so for example, let's say we're in downlinking and then we get an error somewhere, we go into safety mode and we'd start running the fault detection, isolation, and recovery. Now, how we've been able to how we've been able to get the satellite to sort of debug it is we need to do failure modes and effect analysis, and that's pretty much figuring out how it can go wrong, why it can go wrong, and what the effect of that on our satellite is. So does that mean it's end of mission, or does that mean we simply have to use one less solar panel? Now, that's been a pretty difficult problem that we've tried to accomplish and solve on our team, because if anything, there's almost like an infinite number of things that could go wrong. So being able to try to quantify that has been something that's kind of difficult. But we think that once we can quantify that, once we have a way of quantifying that, actually solving these problems and the process of going about and figuring out what we need to do is pretty straightforward. So our current method of solving this problem has been mainly relying on the data budget task. Now with this task, I think it's already been discussed a little bit within the firmware presentation, but how mission operations is using this is that we can actually leverage all that information that we get from the number of actual telemetry points to actually determine for our FDIR. So what that might look like is, let's say we determine all the different telemetry points that we're going to be sending back. We can request additional information, like finding out the nominal range of that telemetry point. We can find out the maximum, the minimum that it is. And then from that information on what we should expect with that telemetry, we can actually sort of gear what we want from our data budget. So a good example of this is with our ticket process. So let's say we know all about the battery telemetry points. So we know that the battery, from what I understand, should ideally be between 80% and 50% charged, somewhere in that range. But once we know that there's a set range that battery should be in, what we can do is we can say, okay, if we ever know that the battery is less than 50, that means there's an error, there's something going wrong. And then what we can do is with this ticket process, This is our current solution to determine how we can figure that out. And what it does is it asks a bunch of questions regarding that error. We can send that out and then actually find from the appropriate lead what information to do to solve this error and what we're going to have to code on the actual satellite to get it to solve it. So what we can do is we can find out all the different possible ways the satellite can go wrong according to telemetry. And then that gives us now a finite number of issues that can go in the satellite, which is a lot different than what we had before. So this is currently our attempt. So now what we can do is we can find out all the different error states that the satellite can be in, and then we can go through solving all these as we go on. So that has been pretty much our task to solve fault detection, isolation, recovery. And once we're able to finish the data budget is when we can really get on this. But everything else is in place. We have a whole ticket process. We have a way to start to solve these errors before we actually go and start to build it in with CDH. So the next thing is the ground station. That's one of the main responsibilities of mission operations, which is actually being able to build our ground station that will actually connect the satellite once it's in orbit. Here's a diagram of one part of it, but there's a lot of different parts within this ground station. The main parts is the RF parts, the mechanical power, and as well the front end. So I can kind of go through all those right now. In terms of ground station design, in terms of the front end, we need to actually be able to communicate with the specific RF system that we have on the satellite. So that gives us our own set of criteria. Part of that is now we're going to be using S-band, so we can transmit more information. We have to have specific sensitivity. We have to have specific gain. And it's a lot more specialized. And we're probably going to have to spend a bit more money than the money we spent on Heron with this. It's also important to know that it's a driver for the rest of the design decision. So I guess one example is that the actual size of the antenna can determine sort of our amount of gain that we need. And the size of antenna might also determine the amount of wind force that we're going to have, which will determine what we need to have for mechanical, which will also determine what we need to have for power. So we're really going to try to solve RF first. And then the current work that we've been doing has allowed for a flexible approach for how we can choose mechanical and how we can choose power. But pretty much there's always some constants that we know. Those constants are that we're going to have to be able to rotate anywhere to connect with the satellite. We're going to actually have to protect it from the extreme weather that we might get from once in a while in Toronto. We also need to ensure that we have like uninterrupted power and actually protecting these different equipments. So that's our ground station design. In terms of the architecture, some of the things that we know for sure is that we're going to need a parabolic antenna. That's going to be the only type of antenna that'll be allowed, that'll allow us to communicate within the S-band frequency. We need to have appropriate gain. As well, cost is a strong driver in this. We need to ensure that we're spending the right amount of money. And in terms of mechanical, aluminum frame, we need to know that it's strong. We need to know that it can actually stay up and not get blown over by wind. And then lastly, within power, we need to know that we have the right voltage bus. We need to know that the power management with the PCBs is proper and that we can have a digital telemetry collection for troubleshooting. Now, this gets into our front end. So how are we actually going to display all this telemetry and ensure that when you're reading it, we actually know what's going on? So what we've been leveraging is a software called OpenMCT, which is a open source mission control software developed by NASA. We're using it for our own project because it's pretty useful and it makes a lot of our work a lot easier. It's also useful because it allows us to test different steps of our modes of operation. So right now, even though we don't have the ground station built and the satellite built, we can actually test different things and visualize it on our mission control, which basically means that we can now see things in advance to prepare for potential errors that might go on in the future. So what we've been doing with this, here's an example of one really rough prototype that we've built, but as you can see, it's useful for displaying lots of different types of information. It's very flexible in terms of what you can do. You can have like different notes, you can have timers. It's a pretty neat tool and something that will become a lot more advanced as we get to know it better on the team in the future. I guess the current plan, how we're going to leverage this is we're actually going to try to build a live orbit app for Heron to show that satellite in orbit using OpenMCT. So there's a lot of interesting work coming this way with OpenMCT. So in terms of next steps, so for the three main projects, we have modes of operations first. I guess it's to finish the CDH model. I think Khalil talked about this a bit as well when he's talking about the follow through in the passive straits. It's to make sure that that high level is actually built. The next thing is that we want to have a Python simulation to pretty much go through and fine tune our criteria for choosing different modes. So we have like the 5 SSVs, the system state variables. We want to ensure that the limits that we choose for every mode are actually appropriate. And that's going to be through a lot of time and experience when we're simulating these different variables, how they change within the Python simulation. The next thing is finalize the data budget. I believe it's on track to be finished by around mid-September, and then that'll allow us to jump into 2 projects. Number one, the ticket process, which is something I already alluded to, ensuring that we have the number of tickets, ensuring that we can actually go through all the steps and solve the FDIR problem, and as well, it allows us to expand the front end, because now that we know all the telemetry that we're going to display, we can really get the front end finished in advance, which will allow us to test and will give a lot of advantages to us in the future. And the last thing is the component selection. So we're pretty close to finishing all the requirements. I know the work in RF is going well, so we can actually determine what that's going to end up looking like, and then that'll allow us to cascade and solve the rest of the requirements. And the last thing I can do right before the Q&A is just give a little bit of an update on regulatory. That's something we've been spending a lot of time doing, ensuring that we're getting it done well in advance. There's 3 main broad categories of the licensing we need, which is like frequency licensing, imaging licensing, and export licensing. So in terms of frequency licensing, that's something that we have to pretty much do through the ITU, and it's figuring out how we can be eligible with them, especially considering the size of our organization. That's some of the difficulties we've had with that right now. The next thing is that once we deal with Canadian licensing, they'll also need the specs of our ground station, and that's something that we fully also don't have yet, so we're kind of working together on this. But we have to go through Global Affairs Canada and to actually be allowed to take these images through space. So this is something that we need to get done. The last thing is the export licensing, which is pretty much the ability to actually send this to the US so it can get launched, because it's going to be deemed as an export. And apparently this is one of the most straightforward ones, hopefully. So we need to give Global Affairs Canada a description of the satellite, which is something that we're also working on as all the design tools get finalized. And then we haven't really been able to start that yet, as not everything is fully finalized. But that's the update on the regulatory. So I guess now we can go into Q&A if anyone has any questions. Yes.
Spoken to, I'm guessing, about security.
No, we haven't.
Computers or the security in place for them.
We have not yet. That's something that we're getting.
Also, GAC is going to want to know about what your security looks like.
Yes. Okay, good to know. Thank you.
Less tasking authority, how's that instituted?
Yes.
So you said export is pretty easy, and that's probably true, but
yep.
If for some reason you have to come back, you should plan ahead of time.
Okay, perfect.
That's much tougher.
Okay, good to know. Good to know. Yes.
Is the intent for the ground station to be useful for future missions as well? Okay.
Yes, that's also a big driver behind our decision. So part of that is because we're using the S-band now, there's a good chance that our future missions will also have to communicate through that frequency. So we have to build that not only for this mission, but also next mission. So it's something that we're going to need to ensure that it's done well and that we do a good job with it. The other thing is one benefit with OpenMCT is that we hope it's something that's going to be updated in the future, and it gives us a lot of flexibility in terms of being able to customize it for future missions. Okay. So that's also been a big driver on our design for that.
That's awesome to hear you thought of that already. Yeah.
More of a fun suggestion than anything.
Yes.
So obviously a lot of the factors that go into building a ground facility are weather.
Yes.
Weather with your big antenna. There are a lot of reasonable construction materials that are completely transparent to RF. Yeah. Has there been any thought given to, let's make a dome so you don't need to worry about wind, rain, snow, or whatever else happens in Canada? And do you think you can transmit directly through it as though it's transparent?
No, but that might be a good idea. We'd have to do more research into different materials. It'll also depend on where we choose to put the ground station, because I don't know if we can put a dome on a roof, but it actually could make things a lot easier.
Just like glass is the easiest one, but ADS is pretty much transparent as well.
Okay.
And as far as thermoplastics go, it's probably one of the nicer ones to work with.
Yeah, that's really neat. One of the reference designs we looked at was almost a mobile ground station that was S-band. So if we can follow that reference design, because clearly it's been done before, that's definitely something that the dome could work well with. Any other questions? Yes.
This is a suggestion.
Yes.
As you are developing grant, integrate them as soon as you can into your system testing. class that level at the latest.
Yes.
Earlier we can, and try to do your testing sort of as flight representative as we can.
Okay.
Over the air tests rather than cable tests. Or people learn that radios are terrible things. And they're bad with and you will learn a lot out of that. Also, it will again give you a reasonably well-tested software stack. You don't want to be bugging key bits of your operation software with the spacecraft.
Yeah, that makes a lot of sense. Thank you. Any other questions? How are we doing for time?
We're behind.
Like, do you want me to rush or?
2 more questions.
All right, 2 more questions if anyone has one. I can check here. Any lessons from the development of the Herring ground station that you were using for Finch? I think the big thing is that since they've done it before, they're a good source of knowledge. So we've kind of looked at their designs, looked at what they've built, and we've been kind of using that to base it. But it's also interesting because we have an S-band frequency. Our dish is going to be completely different. So what they have to consider is also very different. I think one thing that we've kind of anchored to is the idea that it's going to be on a rooftop of a building, but obviously that's still something that we have to change. So we kind of want to avoid also just anchoring to everything that they've done, because the nature of this one, because it's going to be a long-lasting thing for the future of UTAT, is to ensure that we're really solid with their design choices on this one.
Also, sorry, did you have the radome, like over the?
Yeah.
Yeah.
Like there's no reason it has to be visible spectrum transparent. It could be a literal dome, and you can just have your pointing working as long as it's RF transparent. That can protect you from wind, and suddenly your antenna system has to be a lot less resilient to be long living.
That makes sense. Any last questions? I think I answered the one on here. All right, that's perfect.
All right. Last presentation of the day. My name is Ian. I am the data processing lead, and I'm going to be walking you through everything data processing related for Finch. There's the agenda. I'll skip that, not important. I wanted to recognize the team we're working with. Great group of individuals, very smart. And part of what makes my job so much fun is I get to go in every week and talk to really smart people about really cool things. So that's the scope of data processing. Essentially, once Zach gets the data cube downlinked, decompressed, he sends it over to us, and then we have to get it to a point where it's usable by science. So that means we have to correct it and then also georeference it so that it can actually be used for science. So for requirements, the key thing is to remember the mission requirement, which is that we want to, 1, have an image of the targeting site, 2, be able to perform spectral unmixing, and then we get, for that's all in service of crop residue cover estimates. So that means, I guess, a couple of key things is our data needs to be readable, usable, as accurate as possible, but it also needs to be georeferenced. So that means we need to actually know like which pixel in the image corresponds with which area on the ground. So that sort of informs basically the pipeline in general. On the left, that's the data quality requirement. We want to have data that's ready for retrieval, and that informs all the different corrections that we want to do, such as correcting for thermal noise, converting from digital to radiance values, correcting for other things in the sensor, and a host of other corrections that I'll go through once we get to the pipeline. And then the other thing that data processing does is we respond to some of the technical limitations of the satellite itself and try to do what we can on the ground to correct for those. So in this case, you might have heard in optics earlier that we're aiming for that 90-meter spatial resolution, but there's a bit of a crunch on the actual focal length that we can have in the satellite. So this is where we're considering sort of a super resolution approach to see if we can artificially increase the spatial resolution of the images on the ground. Oh, sorry, I was for this slide. So for this one, is there a back? Yeah, so this one was just all of the requirements of the sensor itself sort of inform the data cube that we're working with. So the size of the data cube, the spectral resolution, and the spatial resolution, that informs the data we're working with. So we want to keep that in mind when we're creating the data processing pipeline and make sure all of our corrections are tailored for not only data cubes of that size, but of that spectral range and resolution. And this was the super resolution correction I was talking about. We're doing what we can on the ground to help out with the spatial resolution of FINCH, because not only do we need that 90-meter spatial resolution for our scientific objective of spectral unmixing, but also the better spatial resolution we can get, the easier time we'll have for actually locating the image on the ground, which I'll get to at a later point. Another thing that drives one of our projects is we're developing a sensor model on the ground that models the satellite itself, and that's driven by the pointing accuracy from ADCS, which is actually good to hear that, I don't know if Kang's here, but I heard it got better results than expected. But still, we're leveraging the pretty good pointing knowledge from ADCS to actually identify where the satellite is pointing, and then use that to reference or georeference our data, regardless of the actual pointing accuracy itself. And again, I'll get into that later on. And again, just to point out, those are some of the higher level requirements for the data processing pipeline. But the nice thing about the pipeline is it's very element-wise, so each correction is pretty isolated on its own, and each correction as a project in itself has its own requirements. So there's the pipeline as it currently stands. Orange is projects we're going to be working on, yellow is projects we're currently working on, and green is projects that are mostly done. So we've got about 9 corrections and then a couple of peripheral components that feed into those corrections as well. And I'll just go through those real quick right now. So for radiometric corrections, these are ones that we haven't started yet, but we're going to be correcting for thermal noise in the sensor. That's the dark noise correction. And then response uniformity, which is where we want to make sure that every pixel in the sensor gives the same output for the same input. And then also response to linearity, which is making sure that our conversion from digital values to radiance values is uniform. And that's important to making sure that we have the as accurate data as possible that reflects what's happening on the ground. So we haven't done those yet, and I've labeled here which corrections require what kind of data. So a couple of those corrections require data collected in the thermal vacuum chamber. So that'll be happening probably next summer or whenever TVAC happens. So we're not worrying about those now, but that'll be further in the future. Defective pixel correction, this is another one. As we've learned, the sensor actually comes out of the factory with some broken pixels, and they automatically correct it. I guess it'd just be a nearest neighbor thing when they send it out. So we want to get rid of that automatic correction so we can see what we're working with. And then we want to characterize that on the ground, so that's the first step. And then we also want to characterize that on orbit as well to see how the sensor degrades due to the environment of space. So currently, right now, what we're doing is we're thinking of finding a pretty uniform imaging site. So we're thinking somewhere in the desert right now, and I think we have a site located. And we just take a single image, and then using that image, you can see which pixels are dead, stuck, or not responding. If we will investigate this further, but if we have enough ADCS pointing accuracy, we're considering what's called the side slither method, where you actually rotate the satellite, and then you're taking overlapping images, and that provides a better idea of how the sensors actually degraded over time, as opposed to just directly taking one image over a pretty uniform area. But we'll be investigating that further down the road once we figured out all the ADCS characteristics of the satellite. So this is the de-striping project, which we're working on right now. Because the FINCH mission uses a push broom sensor, you can get striping artifacts in the spatial dimension, like you can see on screen. And the current approach is we're using machine learning based approaches to actually get rid of those striping artifacts. And this is a preliminary approach preliminary results we've gotten. I believe this was just using preloaded weights. But for this project, what we're doing is we're developing a data augmentation pipeline to, for now, we're augmenting existing hyperspectral data sets from the internet to create more data, and actually we're going to be training these models from the internet, but eventually we might be using Nmap data or data we get from the drones further down, which might give better training results. The other thing I should mention is for this project we're using models from the internet, so we've got a repository of different models, and the plan is to look through all of those, test with different ones, and then go forward with the model that seems to work the best for FINCH. Adding on to that, super resolution is sort of a sister project to de-striping, because the current plan is to use a similar approach, a machine learning approach, to do what's called single image super resolution. And the idea is that you can train a model to upscale the spatial resolution of the image with a 2 times increase. So similar idea with destriping, we found a lot of models on the internet, and we're sort of looking at the capabilities of those. And we'll choose which one seems to give the best output. And we can also leverage the data augmentation pipeline that we've developed for destriping. So that has an additional use over here. For the single image super resolution, a lot of these papers were doing 2 times and 4 times upscaling. But the drawback of increasing your spatial resolution upscaling, especially with the single image super resolution, is that as you increase the amount of upscaling, you decrease your peak signal to noise ratio, which is the primary image quality metric. So essentially, I guess as you increase the spatial resolution upscaling, the model is guessing more and more about what it's seeing, and so your data actually becomes less and less accurate to what's actually on the ground. But the other options for single resolution is we're going to keep it open for the multi-image super resolution technique, which would combine multiple low resolution images into one high resolution image. And this is a technique often used with cell phones where it'll take a burst of low resolution images and increase the resolution. And we've seen 1 or 2 of these where it's done on satellites, but we're not entirely sure how we go about doing this for FINCH. So that's why for the data gathering requirements on board, we're planning to be able to store 2 data cubes at a time. So we can essentially take 2 low resolution images, and if we can figure out how to get it working on the ground, combine that into a high resolution image. And that would bypass some of the constraints with single image super resolution by, I guess, producing more accurate data to what's on the ground. So that bypasses one of the problem with the peak signal to noise ratio. So now we're on geometric corrections. This is the SMILE and keystone corrections, and these have to do with the way that the light from the optics actually reaches the sensor itself. So the SMILE correction, that's a shift in the spectral dimensions that occurs because of the way the light hits the sensor. And this is the one that we've mostly done, and in this one we're identifying how much these spectra are shifted by identifying key spectra or key features in the spectra and comparing that to simulated spectra that we've simulated with a software called Modtran. And once we've identified the shift, we correct for that. And that's just in the debugging stage, so it seems pretty promising that we'll finally get that one worked out. The sister correction to that is keystone, which is similar, except instead we're looking for a shift in the spatial dimension. And by doing that, we're using what's called differential keystone at this point in time. So that's comparing, basically comparing 2 adjacent bands to see what the shift is between those, and then extrapolating that out and correcting for that. So those 2 are, SMILE is done, keystone is in progress, and that's where we're at with those. And then the final correction of note is the orthorectification and sensor model corrections. So this actually started out with the project was called georeferencing, that's putting the image somewhere on the Earth. And then we figured out we probably need to do orthorectification for that first, which is correcting for the geometric distortions to the satellite's perspective of the Earth, because it's not always pointed directly down at the Earth. And then one of the ways that you can do orthorectification, one of the ways that we chose to, because of our ADCS constraints, is to actually develop a sensor model. So we're using models on the ground. We're also using telemetry from the satellite to produce a series of coordinate transforms that transform basically the position of the sensor in the satellite itself and relate that to the surface of the Earth. So we're developing that project, and hopefully that should be able to tell us exactly where every image we take is on the Earth. And that should at least assist with being able to perform georeferencing in the end, which is placing our image on the Earth. Because one of the problems with our spatial resolution being so big is you can't really see a lot of objects to do manual georeferencing with a 90 by 90 meter resolution. Like you wouldn't be able to really see a road or maybe large buildings, but it'd be tough to actually place the image somewhere on the Earth. So going forward, I sort of been discussing the peak signal to noise ratio, especially with the destriping and super resolution projects. But it's worth considering how image accuracy metrics such as PSNR and there's other metrics are affected holistically across the entire pipeline. Because obviously machine learning approaches affect those, but even other resampling approaches such as SMILE and Keystone both perform resampling, and we want to know how those affect the accuracy of the data. We want to be able to determine to what extent the image we have at the end is an accurate representation of what's actually going on the ground. And of course, geolocating is another thing. We're thinking about landmarks, and we want to see what our spatial resolution can get to so that we can actually locate the image on the ground, because that's honestly a make it or break it step for the, at least for the level 5 mission requirement, where we actually have scientifically usable data, because we need to have the data on the right spot on the ground in order for it to actually mean anything. So that's just a brief overview of destriping, or the data processing pipeline, and I'm happy to take any questions at this point.
I'll take Max as usually Dylan. I really like how that was presented, and you organized that really well. It's very clear what the concerns are going forward with it, which is awesome. And I think you've mapped out a lot of the concerns that do need to be rectified, which is great, because this is the right time to do it. This is the right time to identify. One thing I might suggest is in your data pipeline diagram, is a positive bit. Yeah, I can be positive. Sorry. During this bit, one thing I might suggest is this is fantastic from the perspective of the process that any given data item goes through. What might be useful as either sort of appendix diagram or something along the lines of that is what the data product starts with and what the end product is, not in terms of like the one processed data cube, but if you look at any JWST data, for example, their outputs will be a package of each of these things has an output, and it's like, cool, we've appended all of them, because the science payload require people to be like, oh no, I need to look at this versus the striped image that wasn't processed, because they have their own metrics to run on them, and they can do comparisons that way, because that actually in some ways alleviates each of those additional steps in the data quality degradation that might occur from them, from affecting the science package that you've provided upon capture. And framing it that way is very helpful for giving a sense of here's what's in, here's all the different variations of this that come out. And one good way to think of that is even if you were to do like convolution passes on the images to do edge detection or things like that, you would still have that as an output in the final package along with the original, along with whatever, because each of these tells a different story, and those are very useful, especially altogether. So this is great. I might also suggest you get something on every from here in addition to it processing.
So what I'm understanding is for every step, push the output of that step off to the side and keep that there in addition. Okay.
Exactly. That's part of the final data package, because you never know what of them will be useful later on. And granted, having a pipeline means that it can run a subset pipeline and achieve the same thing, but you may as well say, well, we've done the processing pass formally, here's everything.
I guess the other thing I'd mention for this is there's some metadata that isn't explicitly referenced. So again, like the sensor model, we're using, I think, GNSS and other telemetry from the satellite, and then also other models. So if I was going to go for an approach like that or a diagram like that, I might also include like other metadata that gets included as well, especially at the end, so then people can see how you got there. I was even thinking about things like including the weights for the models we use and that kind of stuff at the end.
The other thing is, in terms of geolocking, you mentioned one of the difficulties is putting the image that you take on the Earth and going that direction. Is there any opportunity for digital focusing of the camera itself on flight in order to, for example, start by taking a low resolution but very wide picture? And since your center point is where it would be anyways, you're not changing the center focus, you could effectively have overlay of like, okay, wide field, oh good, we can pinpoint that to North America, and then zoom in, because you always know it will be X pixels on the larger one.
I think zooming is probably a pay firm question. I will say I think our swath width is a couple, like 20 kilometers or something like that, which I think should be good enough for ballpark sort of area, especially if the area we're looking at is fields no more than a kilometer on the side. So I think in the end we will have a lot of sort of space on either side, but I don't know if digital zooming is something we can do with the camera, or I'm not sure.
This question's for in the data processing, since you're doing all this on the ground, you're somewhat separated from the satellite's path of flight, which a lot of people, that's like a big bottleneck for both subsystems. So for this, of the pipeline, what are the things that you want to get perfect before the satellite went to flight?
I've been thinking a lot about that, especially since like data processing doesn't really pose any blockers for other teams. So especially when I was talking to David about our transition to phase C, data processing is kind of exempt from that, and we're working in parallel. And the other thing is there's a lot of what design that goes into the satellite where it's like that's the best you can do. Like especially optics, you can't develop more, you can't get more space in those 30 centimeters, right? So does it really matter if our super resolution works or not if we can't actually get better spatial resolution anyway? But like you said, it might be nice to have super resolution down pat before the thing launches so we can test it and see how that works. So that being said, I'd go back to those the two corrections that I pointed out earlier that were informed by external requirements, which would be the sensor model and the super resolution, just so we can see how much those augment the abilities of FINCH before it goes up. And then everything else that doesn't necessarily, like all the other corrections that we're just gonna have to do anyway, those I wouldn't worry about so much. So I'd say sensor model, ortho rectification, and then super resolution.
To his point, are there any of these functionalities necessary for the checkout phase of this mission, right? Like after launch, when you're checking out that all systems are working, are any of these in particular absolutely necessary to make sure? Because those would be maybe not bottleneck for the flight teams, but bottleneck to checkout and say, great, we are now in operation, nominal operation.
Yeah, I mean, it's sort of the same response. There's not a lot you can do with the satellite once it's up there. So I would say off the top of my head, no. I think the only one that's time sensitive to when the satellite is actually up there is sort of our defective pixel correction, because we want to be able to quantify how the sensor degrades throughout the mission. But there's nothing that's like required to run. Like you could get the data from FINCH and then develop and run this whole pipeline 10 years after the mission or something like that. It's not super time sensitive. So let me just checking for correct questions online. Data processing related to super resolution, but also a question for payload in general. By spatial resolution, do you mean the ground sampling distance or ground resolved distance? So my understanding of spatial resolution was the size of the pixels we're working with. So right now we're working with 90 meter by 90 meter pixels. I don't know if anyone, yeah. Ah, okay, yeah. So ground sampling distance, Abir says. Are we allowed?
Okay, sure. Sorry, just to follow up then, because ground sampling distance is always going to be better than your ground resolve distance, right? Because your point spread function, how it maps onto your pixels is what you're actually getting resolved. So I've seen super resolution used before to get your ground resolve distance to kind of match that ground sampling distance as much as possible. But if you try to extend past that ground sampling distance, that's when you start getting into the range where things aren't always radiometrically accurate.
Okay.
So it might be a good idea to consult with your customer or whoever you're working with to make sure that they have some accuracy requirements on, you know, how much you can do this.
Did you catch that, Abir? Okay. Are you allowed to image a desert in terms of regulatory? Do you need approval to image each specific site? I believe the imaging site we chose, I think it was in Niger, I think. And I think that's a common site for calibrating satellites, but I would have to follow up with the regulatory team on that, I think. Is your destriping algo independent of dataset, i.e. if you train it on one data in some random place on Earth, will it work in another data somewhere else? So that's a good question. If we had the data process or the destriping project lead here, he's a lot more knowledgeable about this stuff. I'm sure he can answer. I would say we would like to have data that's closer to what we expect from FINCH, and especially if we can get that Nmap data further down the line, that'll be an image or an image of the same imaging site. That would probably result in the best results. But I guess short answer, I'm not entirely sure. The long answer is we will be able to try a bunch of different things and see what works best. Data processing ops is a commissioning phase, a part of your mission ops plan. It could maybe help iron out some of your concerns about super resolution and calibration. Commissioning phase, Zach, is Zach still here? there, commissioning phase. Does that? Zach shakes his head. I guess Zach would have to follow up on that one.
Sure. Do you want me to, like, are you familiar with it?
I'm
Or
not.
would you
Zach,
like
are
me
you
to?
familiar with? Zach's not familiar with the term, so.
Essentially, it's a phase of the mission before you start releasing your data to the public or to your customer, where you're just collecting the data, sending it down, and making sure that things are running properly. So you could use that phase to kind of compare the images that you get, and try your super resolution and try your calibration, to kind of tweak how often you want to calibrate, as well as tweak, just see if your super resolution works relative to the Nmap kind of ground truth data. And if those radiometry or signals that you're getting there are kind of correlated, you can start actually delivering your data with a bit more confidence.
Yeah, I guess Rosie could maybe expand on this, but our sort of customers, we're working with, again, that farm in Manitoba, and we've got a team out there who might be doing some data collection on the ground, so either by hand or by a drone. And that's, I guess, sort of the only customer we have, and that they'll eventually want data to compare it to. And in that sense, the Nmap data that we've been scheduled to collect is sort of the backup if we can't get usable data out of FINCH. So I guess.
It'll still be valuable to have in terms of for like, yeah, it's just like a secondary source of data that's far better quality.
Yeah, I think Nmap's supposed to have a 30 meter by 30 meters pixel resolution. So I guess that's what happens when your satellite isn't confined to a loaf of bread size. Super resolution from the literature review, how accurate have they been? How much distortion did it add for the multi-image method? What is the max temporal difference between the two images? Like, should it be taken X seconds apart? So for the literature review, for the single image super resolution techniques, I think the PSNR was just above 30, which meets our requirement for the 2 times increase, but it was like generally below 30 for the 4 times increase. So that's why we went with 2 times as a figure. But again, it's important that we look at the whole pipeline holistically, because I'm sure destriping is going to decrease the PSNR. Smile is going to decrease the PSNR. Anytime we resample or do something like that, it's going to decrease the PSNR. So that's one of the areas of future inquiry is how does the image accuracy change across the entire pipeline as a whole. Max temporal difference between the 2 images, not sure at this point in time. I think David sort of brought up the multi-image super resolution approach, and the idea would be to take essentially 2 images simultaneously, so there wouldn't be much of a temporal difference, because I guess, again, it's a push room scanner, so you can take one scan line for one image, another for the other image, like a little bit apart, and then do your next scan lines sort of in pairs, and that would get you 2 images once put together that are just slightly shifted from each other, and that would probably work for the technique.
Okay, I just want to say that when I was looking into it, taking 2 pictures close apart, oftentimes they had 2 sensors doing it because they were very close together and the satellite is traveling pretty fast. So you're not actually imaging the same place in that moment.
Yeah.
That's why the temporal resolution is really important. This difference between these 2. Yeah, you should look into how they do that 2 image thing better.
Yeah. No, that's why we've got the single image approach as like the baseline, and then anything beyond that is that's if we can figure out all the technical aspects to it. So, any more questions?
For image processing pipeline, does it need the full data queue before it can start, or can it work on partial data queues, like missing weight, missing bands, missing blocks within a band? It's going to take a long time to download that.
Yeah. So I guess this gets into some of the more technical parts of how we're actually going to pass the data down. It's possible we'll have missing scan lines. So we're expecting that. We haven't really considered missing bands, only because on the technical side, I guess to me, it hasn't occurred that might happen. But again, the other thing is, like, I feel like at least the understanding I have right now is that the data processing pipeline doesn't need to run synchronous with FINCH, because once we've got the data downlinked and decompressed, it's not going anywhere.
No, what I'm going at is, eventually you will presumably download it all. But,
Yeah.
Given the constraints I heard earlier about the comms restrictions, sort of unpleasant to have to wait 2 weeks
Yeah.
before you can get an image.
Yeah.
If I've gotten some data now, can I do something with that data right now other than just look at it on the screen?
Yeah, I mean, if off the top of my head, the dimensions of the data cube are just variables in all of our code. So I don't think we're coding for it right now, but you probably could just change those numbers if you had like a truncated data cube. But again, things like missing bands, I don't think we're planning for that right now, but it could be worth looking into. I think that's it then.
Okay, all right, well, that brings us to the end. We're gonna have as a last bit here, a team-wide Q&A. So the way this will work is we'll go through the Zoom questions, as well as any in-person questions, and I'll get the leads to come up down to answer them. But before that, who wants a quick 10-minute bathroom break? Okay, 10-minute break. Let's do it. We'll come back at, what time is it now?
4:02.
We'll come back at 4:10. 4:12. It's good. I'm kind of tired. Okay, we're back for Q&A. Sorry, I'm struggling here because we didn't actually go through and remove the ones we answered live. So, question, I think that was answered live. Okay. 263, does the MCU have any special DSP instructions that can be used to accelerate the algorithm? From Bruno. I think, Kevin, you might have already answered this.
Yeah. So we actually have...
Do you want to come up to...
Yes, I will. Yeah, so we haven't specifically looked into hardware encoding, hardware accelerating on the MCU just yet, mostly because we're not at that stage necessarily. And I doubt that. Okay, at this stage, I'm not quite sure if the actual computational time of the compression algorithm is what will consume most of the overall like compression time, because we expect a decent amount of latency from the SD card itself. So when we're doing this over 409 million data units, it really adds up. SD card latency is what we expect most of the time to be simply. Yeah.
Awesome. Thanks, Kevin. What I'll ask is for you guys to upvote the questions you want answered. That way I can sort by most upvoted and go through these a little quicker.
I think we've covered most of them, like during
Okay.
I think most of the ones that we skipped were the ADCS ones. Like the, yeah.
Okay, so let's tackle a couple of those then. Do you want to come up, Ken?
Is there worth in doing that synchronously? Yeah.
Or are there questions we want to answer in person then? Yeah.
Will your instrument survive a sun stare?
A sun stare?
Stare.
Stare? So
For whatever reason, it points at the Borsec points at the sun.
Oh, for the star tracker?
A while.
We haven't really talked about that to the suppliers.
I think it means for the payload.
Okay. Oh,
like
oh.
if the ADCS gets stuck such that the sensors point.
Or it's just not working and the spacecraft slowly drifts across the face of the sun.
Do you have a name for that?
Yeah.
No, it might happen in kickoff. It might happen when the spacecraft's off.
We'll be doubling in this point at the sun.
So yeah, the question was if can the sensors withstand staring for Well, yeah, we're not entirely sure about that. That is something we will have to.
I imagine the slit would be the first thing that get
Right.
one.
Yeah.
Not the sensor itself, but
Yeah, I mean, we are losing a lot of light on the way in, and then also diffracting it out to cover a larger area. So
It's very large for very large.
yeah, and it's a fairly thin slit too, right? Expecting to be. In the past, we had looked into like a deployable lens cap, but we just said that was too much risk for us. Yeah.
But if, on the other hand, it turns out you will melt the system,
Yeah.
that's the risk of the mission because the ADCS has to continue. Or hell, just detumbles across the face of the sun.
Sure. What kind of analysis do people usually run for that? Is that part of stock?
I honestly have to take the lens and take it outside.
Okay.
See what happens. If that catches fire,
That could be a fun test. Yeah. All right. Yeah. Any other questions? Again, anything goes as far as any team or higher level questions. Yeah, Ian.
I've got one. This is about power. I noticed in that one of the diagrams where you had like a lot of the connections of the different subsystems, there were a few things where they were connected. The power in particular was not connected directly to the EPS. It was like there were some intermediary bits and pieces. I want to say like the sun sensors did not have a direct connection to the power system. They were like being powered from like the ADCS port. And there might have been one or two other things on the payload where there's like a piece that's getting power from another board, and then that's getting power from the power system. It's not all individually switched. Is that is the case, I guess? And like, why did you choose to architecture things that way versus just having everything on its own switch that you could power on?
Yeah, I mean,
Or do you want to come to the screen?
Yeah, so essentially, I mean, I can't speak to the other diagrams you may be referring to, but the way that I understand it is that we have, the ADCS has 2 voltage buses. They have 5 volt and a 3.3 volt, and that goes to the star tracker and the COTS module, which I think incorporates all of the, like the sun sensor, the IMU, and like kind of like the whole, all the rest of the ADCS components.
Okay.
So we kind of have like per subsystem, we have like a load switch and a power monitor that goes to each.
Speaking for the payload specifically, we do have load switches and current monitors on all of the individual subsystems. That load switch might not be on the EPS board, it might be on the tail board just due to proximity reasons, but each one will have its distinct switch so we can control every individual bit.
Yeah, I don't know if that answers like your concern about.
Yeah, it's not necessarily a concern, more just like I was wondering what the reasoning for doing that was doing everything on the power board.
Right. Yeah.
It might be that like the COTS module, that's how it's set up for whatever. That's totally fine.
Yeah, I think the COTS module has like a 5 volt and a 3.3 volt bus. So, but yeah, that's generally how we're doing it, is separating it by subsystem. Yeah, that's. Unless there's more power questions, I can stay.
Are there any questions that the team has for our advisors today?
I do have one.
Yeah, go for it.
Thank you. I don't know if anyone has information about the ideal like window of like state of charge for the batteries, because I've kind of just been going off of like I don't want to discharge them too deeply, but I don't know if there's like an optimal range. Our mission is only like 1 year, but okay. So like keeping them at 100 is not like an issue. Okay. Okay. Because I thought that could cause the capacity to decrease.
As long as you don't try to overcharge.
Yeah. Yeah. No, we do have like a like constant current to constant voltage charge controller. So
we normally back off by
right. Yeah. Okay. Perfect. That was my question.
Anyone else have questions?
I have some questions from online about the payload specifically.
Yep, go for it.
Yeah, so the first one is your special range requirements 900 to 1700, but your GRISM is only sensitive to 1600 to 1700. So how does that work?
I'll be able to tackle that one.
That is a good question, which is something that I did want to investigate. So in terms of like knowledge transfer, I was informed that it was because the main, I guess, wavelengths that we were looking at were between 1600 and 1700. But I don't know how valid that is in terms of actually making that the spectral range for the VPH GRISM.
I see.
So that is something that I was considering, or that I was going to look into. But yeah, thanks for bringing that up.
Yeah, okay. Because if the GRISM is not sensitive to the 900 to 1600 range, you're not going to get the right diffraction onto the sensor. So you might miss out on a huge chunk of that spectral range that you actually want if it's valuable for the spectral mixture analysis process.
Yeah, that's fair.
My second question about the payload was about the focuser.
Mhm.
Have you experimented with the focuser? Like I don't know what the lab setup looks like. Like with the detector and the focuser, have you experimented with those?
As in, like, have I tried actually focusing light on the sensor?
Onto, yeah, like just using a focuser. Have you tried focusing light onto a
Yeah. So,
detector? Yeah.
in the preliminary part of our like FLIR-TAU optics integration, we didn't have like our specific focuser, obviously the one that we're sourcing, but we did just have a lens that was lying around in the lab that we used to try to get an image in the FLIR-TAU, and it did work out.
Nice, nice. Yeah, that's good. Experimentation's good. Yeah, just the problems that you sometimes get with the focuser is like you're focusing too much power onto too small of a space, right? So you're getting some blooming. So I guess when you're sizing it, you would have to make sure that whatever focuser you're also getting is just confined to that space. There's no extra blooming or diffraction on your CMOS face. But yeah, it's good that you've already experimented with that. And the final question was just about I didn't see mention of it. So I saw mention of like stop analysis, which is like a bit more detailed design. But have you made alignment budgets or wavefront error budgets to generate the requirements for this stop analysis?
Yeah, that's a good question. I think I saw it in the Q&A as well that you'd asked that. We don't have a requirement right now for wavefront error, and that was something that we were looking into. In terms of like MTF as one of our other performance metrics, we don't think that we will be able to come up with a requirement. I've read a couple of papers, and there's like a huge range of values, which doesn't really help. But in terms of wavefront error, like that would be our like one of our first steps in stop analysis is actually coming up with a requirement that we can verify, or at least check against in stop.
Yeah, I wouldn't worry too much about the MTF. Some missions don't have an MTF requirement, and it's fine. But yeah, wavefront error can be pretty important. So yeah, that's a good thing to focus on.
Will do. Anything else?
Not for me. Great job, guys. Looking really good.
Thanks, Aiden. All right, I think we can wrap it there. So once again, big thank you to the advisors for coming down today and giving us your feedback. I'm sure the teams will very much appreciate it. We know that this is a very ambitious mission. That's part of the fun, is taking on that challenge. So big round of applause to the team and big round of applause to their advisors as well. All right, thanks guys. We'll catch up after the big hiatus. Thanks guys, if you're online. Thanks for dropping in. Good seeing everyone again.